Well, hello everyone watching, and welcome to the 11th episode of Bad Apologetics, a series where me and James Fodor look at some of the claims of apologists. Today, we're going to be taking a look at the digital physics argument, which is an argument that Inspiring Philosophy has used in several debates and made a series on his channel, which basically argues from quantum phenomena to the existence of God. So this is a bit of a weird one. It's very different, I suppose, from the normal sort of natural theology that most people are probably going to be familiar with, like the Kalam cosmological argument, teleological arguments, and stuff like that. It relies quite heavily on specific interpretations of quantum mechanics, and it's not even exactly clear what it's saying, but we'll get into some of that. I think James has put in a ton of work on this one. What are your initial opening thoughts?
I didn't want to do it. Nathan made me do it. He made me do it. So yeah, this is going to be a bit of a rough one. So strap yourselves in. There's a lot of quantum mechanics and relativity and weird quantum consciousness stuff that IP likes to appeal to. And I'll be sort of trying to unpack some of that. There's so much that he puts in his videos that I won't be able to respond to every little claim that he makes or every paper that he cites, but we're also not doing every single video he's done on this, but I've selected some that I think are most representative of his argument and the key claims that he makes. And I think I've got a good selection of things to show you about how he sort of misrepresents and misinterprets a lot of the results that he's appealing to. Before we start, I do want to say some nice things about IP, because I'll be saying a lot of nasty things. One thing that I appreciate is that he, Michael, is agreed to do a debate or discussion in a couple of months about some of this stuff, which is the first response we've had to any of these sort of offers. So I think that's really exciting and really positive that he's willing to do that, because a lot of people, that we criticize are not willing to sort of step forward and have the discussion. So I really appreciate that. Another thing that I appreciate about what IP does is that he is willing to sort of do his own research and think for himself and develop his own ideas. Unlike a lot of apologists or YouTubers that we talk about, who just sort of parrot things that they hear some of the leading people like Craig or Lacona or whoever say, which gets a bit old. So at least IP is not doing that. And so I do appreciate that. And you can see the effort he puts in his videos. So I think there are some good things here. But unfortunately, there's also a lot of bad, because he does, I think, misrepresent a lot of the science and draw faulty conclusions from it. Also, his arguments in this area are very hard to follow. I spent so many hours, literally lost sleep trying to work out what the hell he's saying in some of these. So I hope you appreciate the sacrifices that I made to do this. So yeah, this is a first pass. Hopefully we'll be able to do some more discussion about this when I get to chat with Michael about this in a couple of months, and I'll sort of have a bit more time to think about it. But yeah, hopefully you find this interesting. And one other thing that I'll say is that one of the purposes that I think of this is to not just show that some of the problems with the arguments that IP makes, but also to try to show what the science actually does say and what the relevant questions are, what the state of the evidence is, which is obviously something that I think is really interesting and important as being a big enthusiast of science. And I just, want to encourage other people to learn more about that as well. So it's there's an aspect of science communication here, as well as trying to dissect the arguments.
Yeah, I think this is maybe going to show like a key difference between you and me here as well, because you're like, oh, how does this make sense? And it's all these words that you're saying are like hooking into concepts that you want to like try and understand scientifically and stuff. Whereas like for me, he'll just say this stuff and I get triggered like by it being quantum BS, but I'm not like, because I don't have that conceptual understanding of a lot of this quantum stuff. Like I guess I don't get as triggered about the science being wrong. So I think it's going to be really interesting. I could tell you were getting like really frustrated over the week because you want to like go down all those rabbit holes and like figure out what was going on at rock bottom.
Yeah, well, the thing is, to my knowledge, no one's challenged IP about this. He's done a few debates about these sort of issues. We're calling it digital physics, but there's sort of a grab bag of related issues. He also sometimes talk about the cosmic consciousness argument, the emergent universe. They're slightly different, but all closely related. Yes. So we'll tease out what all that means. But he's done a few debates on this. We'll look at some of those, at least parts of those debates. But I mean, to be honest, I was really unimpressed with the quality of most of those debates. It looks like that. Well, I mean, I suppose there's different ways you can interpret this. Maybe people are just more sensible than I am and have avoided trying to go down every rabbit hole that IP sort of develops for us. So, yeah, no one's really challenged him on the details of any of this stuff that I'm aware of. And I think that it is important to do that, because there are a lot of people, maybe we'll see some of this on the videos, who just eat up everything that he says and just, seem to accept it as correct. Which, I think is an issue if it's leading people to misunderstand science and get wrong ideas about what science says about the world, and to not think critically about it. Even though, again, I do applaud the fact that IP is sort of bringing these ideas out and encouraging people to learn more about it. But then if people are learning wrong things and not thinking critically, then that's sort of bad. So, hopefully we can improve the discourse there a bit.
Yeah,
but
I think
sorry, go ahead.
Go ahead. I was just going to say, I do think it's good that IP promotes this kind of like scientific thinking. He pushes people to look at scholars and things when it comes to like looking at the Bible, and does a lot of cool work pushing back against like young Earth creationism and stuff like that. So I think maybe from my point of view, it'd be really cool to see IP like back away from some of this stuff if it's not right scientifically, and then that would bolster, I think, his credibility in the other scientific stuff, which would help to push back again. Like, because people can be Christians for different reasons, right? And but also hold like a worldview that's compatible with like what our best sciences tell us. And I think that someone like IP could be great for doing that. And so I hope he'd like take the kinds of criticisms that we're going to give today and sort of integrate them into his Christian worldview. If he ever watches us. 7 hours.
Well, we'll see. One other thing I was going to say is that this video is going to be a pretty heavy stuff necessarily. Interestingly, it doesn't seem to put people off IP's channel. A lot of people really like it. So hopefully it won't put people off this video, but you've been warned. So if you're expecting, I mean, I guess we're generally pretty heavy anyway, but this is going to be more intense. And for that reason, we're starting off with just an intro video to some of the key ideas of quantum mechanics, just to, I guess, help to set the stage a little bit. So this is not from IP. This is just a video that I found that maybe have helped to introduce some of the key ideas.
Our universe is an amalgamation of different objects following a wide spectrum of sizes, ranging from the smallest particles to the jumbo astronomical objects. Being able to perceive the nature and behavior of all these sizes has been one ultimate goal of mankind since ages. But as a single medicine cannot cure all the diseases, similarly, a single scientific theory cannot work well at all the scales. So, where we can efficiently describe the motion of a billiard ball or the motion of the planets around the sun, using the same laws we cannot describe the behavior of smallest entities in the nature. This is where quantum physics comes into picture. But what it really is, what led to the development of this theory, and how is it different from classical physics? This is Q&A, and here is the answer to the question, what is quantum physics? To understand what is quantum physics, we need to go more than 100 years back in time. We had pretty much figured out how the world works. We could explain the motion of objects around us, the waves on strings, the ripples in the pond, and even the motion of the planets around the sun. But when we think we know everything, nature throws us problems. There were 3 major events that gave birth to quantum mechanics. The first was in 1900 when a group of bulb manufacturers approached Max Planck. They wanted to make their bulbs more efficient. This required a better understanding of the famous black-body curve. Planck was confused on how to solve this problem. After a lot of brainstorming, he came up with an assumption. He said, energy in the form of light can only be emitted in discrete amounts. It cannot be emitted continuously. So 1.4 units, 3.5 units, 6.2 units, etc. were not allowed. Planck did not realize the importance of this hypothesis. 5 years later, Albert Einstein, who back then was a struggling third-class patent clerk in Switzerland, realized the importance of Planck's work and used it to explain the photoelectric effect. This was the second blow to classical mechanics. The third and the final nail in the coffin of classical physics came from Niels Bohr. When we pass electric current through gas to ionize it and observe it through a spectrometer, we see very fine spectral lines. Their origin could not be explained by the existing theories. Bohr attributed these lines to the jumps made by electrons from one level to another. His theory was the first leap to explain the structure of the atom. So far, so good. But if this is what all quantum physics is, then why is it considered so weird and difficult to understand? Well, the answer to this lies in the physical interpretation of some of the offbeat concepts and principles involved in this. So now, let's have a look at some of the most interesting ones. Number 1. Quantum tunneling. Suppose you have a bouncy ball with you and you are hitting it at a wall. What happens? It keeps on coming back to you and you keep on hitting it. But there comes a point when it just disappears at the wall and then appears on the other side of it. Spooky, right? This is what quantum tunneling is. Technically speaking, a subatomic particle can pass through the potential barrier greater than its energy. Fun fact? This is the reason behind our existence. It is the basic principle involved in the production of nuclear energy in the core of the sun. Number 2. The wave-particle duality. In our daily lives, or in the realm of classical physics, a particle is a particle and a wave is a wave. A particle cannot act like a wave, but in quantum physics, it can. At the smallest scale, the wave nature of the particles becomes noteworthy. The last and the most interesting one is superposition. This means you can do exactly opposite things at the same time before someone looks upon you. That is, if you are a quantum particle, you can rotate clockwise and anti-clockwise at the same time before any measurement takes place. So, the Schrodinger's cat is both alive and dead until we open the box to check. You might be wondering, what am I even saying? But this is quantum physics and even the weirdest is normal here. And this is why Niels Bohr said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Share this video with your friends. See you in the next episode of Q&A.
So hopefully that was helpful to give a flavor of some of the key differences between classical and quantum mechanics. I mean, there are other videos you can look at. That one was of a manageable length for our purposes here. One of the important things to understand, which I don't think they explicitly mentioned in that video, was the concept of the wave function. Now, we have talked about this, I think, in episode 1, actually, when we talked about quantum cognition and dualism, so the wave function is basically we'll call it a quantum object, which describes some sort of system. So you can think of that as just like an electron in a box, for example, or an electron around an atom or something like that. The wave function describes the properties of that electron in that context that it's in. So that would mean things like its position, momentum, angular momentum, things like that. And there are techniques that we have for being able to extract that information, either experimentally or sort of using formal techniques. So I mentioned that because there'll be a fair bit of discussion about the wave function going forward. So basically, just think of that as a mathematical thing that describes what's happening to a system. And there are further questions about like how to interpret that, which we'll get to. I'm just thinking if there's anything else that I wanted to say at the outset. I think those are the main points to be addressed. Obviously, there's a lot more specific things that we'll get into. One of the issues with what IP talks about is a lot of the stuff he discusses is very advanced. And although I did 4 years of physics, including a year of postgrad physics, I only touched on some of these things and others didn't talk about them all because it's basically research stuff that's still being debated, like interpretations of quantum mechanics and recently proved theory, things like that. So even if you read fairly good books on quantum mechanics like this one here, this is Introduction to Quantum Mechanics by David Griffiths. This is a book that I used at third year level. It's a very clear introduction to the key principles of quantum mechanics. So I'd recommend it if you're interested. It's mathematical, but it's not like ridiculous level of mathematics. So it's quite reasonable. But the point is, even a book like that won't really discuss most of the issues that IP is raising here. So it is pretty advanced stuff. So I'll sort of do my best to explain, to my understanding, based on the reading that I've done, how IP is, well, what he is saying, and then how he's sort of misrepresenting the results and what they actually do say, or when it's unclear, I'll sort of mention that as well. But as I said, I don't have a full understanding of all this stuff, and some things I didn't have a chance to look in detail into. So please forgive me for that.
Yeah. Well, I have even less of an
I
have even less of an understanding, so that's great. I'm remembering, I think the last time I did any physics that was anything like this is like 5 years ago. So let's see how good that memory is. But in terms of just the basic stuff, like the stuff that's being shown in that video, for example, how much is based off of sort of shaky interpretation stuff, and how much is kind of settled physics where we're fairly confident, that this really is the case in reality?
Well, things like superposition and quantum tunneling and the double slit experiment, those are all established phenomena.
Yeah.
And like Schrodinger's cat is a tricky one. That's an example of superposition, but it also relates to how you think about superposition of macroscopic objects instead of like microscopic quantum objects. That will become relevant in some of the discussion. That's still disputed depending on how you interpret the quantum mechanics. Many of the ideas that IP is going to appeal to sort of start with those, but then expand upon them, and it attempts to draw pretty specific conclusions on the basis of them. One of the very important aspects that IP talks about a lot is the so-called measurement problem. So actually, it might be good to preface that a little bit. So that's the first video we're going to look at, but I don't think IP does a very good job at explaining what the measurement problem actually is. So I'll try to give us a short view of that that's not too technical. So traditionally, quantum mechanics has kind of two sides to it. There's the side that describes how the wave function evolves over time. Remember, a wave function describes the quantum properties of a system, like, say, an electron around an atom, to take a simple example. And you can describe the evolution of a wave function using something called the Schrodinger equation. Also mentioned that in episode 1. So it's an equation that just says how the wave function evolves. It basically is a wave equation. So it describes how the how the quantum system evolves like a wave spreading out over time, to put it very loosely, and how it can interact with other things. So that's what a lot of quantum mechanics is about. But there's this other sort of side of quantum mechanics, which is about what happens when you make a measurement, say, of the momentum or position of a particle at a particular time. And when you do that, at least traditionally, what happens is that you collapse the wave function. So the electron, for example, goes from being a sort of a probability cloud that you can't say exactly where it is. It's sort of distributed across space. It goes to being at a definitive location at the point you measure it. And that's called wave function collapse. It goes from being sort of spread out as a wave to being localized as a particle.
Can I stop you at that point? Sorry, to ask a question, though.
Yeah, sure.
Like, is that idea of like the probability cloud, is that part based on interpretation, like your philosophy of like probability and what that means in reality? Like, is there a real probability, or like the dice sort of only lands on one side sort of thing? The electron has to be in one of the orbitals, or is it not based on interpretation? That's kind of settled. That's
a standard part of quantum theory, which is called the Born rule. The Born rule says that if you take, that's BORN, if you take the wave function of a system and then basically square it, you get the probability of the, again, simplified, but you get the probability of the particle being at a particular location. So if you sort of integrate over a space and the square of the wave function, you get the probability that the electron is in that space at the time you make the measurement. So that link between the wave function and measurement is given by the Born rule, and that's a standard part of quantum mechanics. And really, any interpretation must be consistent with that, because that's how we make a link between, like, the Schrodinger equation, which describes the propagation of the wave function over time, and actual measurement results. Because you don't measure the wave function directly. It's sort of a theoretic, well, again, whether it's real is an interpretation question, but it is at least a theoretical construct which you can't necessarily measure directly. You sort of use it to describe the system, and what you make measurement of is like particles being in a particular state at a particular time, like this location or that location or this spin or whatever. And yeah, they're connected by the Born rule and this notion of collapse. So the wave function goes from being sort of distributed and probabilistic to being discrete and sort of definitively in this state at a particular time. Now, how that collapse occurs is not agreed upon. So that is part of what is meant by interpretations of quantum mechanics, which we'll get to a bit later. Because basically, as I said, there's sort of this dual aspect in the theory. There's the evolution of the quantum state, and then there's the measurement, which collapses the wave function. And according to standard or the classical interpretation, which is called the Copenhagen interpretation, basically when you make a measurement, when you interact with the quantum system, it just sort of collapses the wave function, and now it behaves like, sort of like a classical object, in that, and it has a definitive position at that time. It's not spread out. And the collapse process is not described by the Schrödinger equation. It's just something outside the theory that just kind of happens. And people have most people have thought that this doesn't really make a lot of sense and the theory is incomplete. And that's where the interpretations of quantum mechanics come in, which we'll talk about a bit more later, which try to say what's actually happening here. But all of this is important because this is the measurement problem. How is it that you go from the quantum mechanical wave space to a collapsed wave function of the particle being in a specific location when you measure it? At the moment, well, at least according to the traditional Copenhagen interpretation, there's not really an explanation for how or why that occurs or what's going on. It's just like, well, that's how it works. And you can use it for making experimental predictions and testing them with theory, so it's good enough. But at least a lot of people increasingly want to have more of an explanation as to what's actually going on there. And so the measurement problem is essentially that problem, and answers to the measurement problem are trying to answer what's happening when the wave function collapses and how does that all fit together.
And so I remember, like, in the 2000s, growing up, watching a bunch of weird documentaries where people were talking about how, like, consciousness, like, causes that collapse and stuff. And I'm guessing that this is,
that's where IP's headed. So this might be a good point to play the video, and I'll just sort of interrupt when I see fit, and we'll see how we go. One problem is that IP is these videos overlap a fair bit. So like they have different titles, but they talk about similar things. So there will be some repetition, but that's not necessarily a bad thing because these ideas are tricky. So we may sort of come back to some ideas, but that's the nature of this. So we'll start with this one.
Normal speed, do you think? Or
let's go with normal speed. They're not too long.
Can we solve the measurement problem, or has physics encountered consciousness? To understand the measurement problem, let's start with the basics. In the paper on decoherence and the measurement problem,
I know already starting it, but that initial sentence had me a bit confused. Can we solve the measurement problem, or has physics encountered consciousness? Yeah,
well, I'm going to say that's clearly a false dichotomy, but we'll see what he means by that.
Yeah. Okay. Yeah. So I'll let it get off the ground before. I just thought, like, it's already. I'm like, what? Hang on. Okay.
Maximilian Schlauhauser points out the problem we have in quantum mechanics. Particles exist normally in a superposition of possibilities, described by the wave function, which basically means, as Rosenblum and Kuttner point out, that particles normally exist as several mathematical possibilities rather than one actual object, like how we experience them in reality. So how do particles go from a mathematical state of possibilities when we are not observing to one physical object when we observe? Well, this is the measurement problem. It seems in the absence of observation, particles exist in a superposition of possibilities rather than one actual thing. But when we observe them, they are not in such a state. Something happens when we look and causes this change. The wave function on its own, which describes these possibilities, is completely deterministic. But as Henry Stapp points out, it fails when an increment of knowledge occurs. Then there is a sudden jump to a reduced state, which represents the new state of knowledge. This jump involves the well-known element of quantum randomness. So something happens between these two states. As Schlauhauser points out, we are missing a mechanism of how this occurs. Thus, without supplying an additional physical process, say some collapse mechanism, or giving a suitable interpretation of such a superposition, it is not clear how to account, given the final composite state, for the definite pointer positions that are perceived as a result of an actual measurement, i.e., why do some seem to perceive the pointer to be in one position, but not in a superposition of positions? So how is it that what we observe is different than what the wave function actually describes? How is it that collapse happens to one definite state when we observe? The practical way this is carried out is through interaction with a particle or system of particles that has already collapsed. One can measure a particle with the use of a measuring apparatus and interact with it. This will cause collapse through interaction because the state of the particle has been disturbed. This is a decoherence effect, and some argue this can fully explain collapse on its own and solve the measurement problem. However, this doesn't really solve it, because if we were to use one particle to collapse another, what was used to collapse that particle, and so on and so on. It was Niels Bohr that pointed out we cannot specify the wave function of an observed particle separately from the other particle that is used to measure it. In other words, the wave function of a particle cannot be unentangled from that of whatever is used to measure it, and so on and so on. Basically, what this means is when one photon is measured by another, they entangle. If one particle measures another, it inherits part of its wave function, so to speak. And that particle, which is supposed to be measuring, cannot be fully explained without what it is measuring. So you need another measuring device to collapse that initial measuring particle to a definite state. But then you need something else to collapse that measuring apparatus as well, and so on and so on. This creates a chain of material objects in a superposition of measuring, which is known as a Von-Neumann chain. Since quantum laws are what truly describe all material objects, some other particle or measuring apparatus is always needed to collapse the next one in line. You keep going back until you get to something that would be non-local, outside the entire material system, which escapes this chain by not being bound by the same physical laws, and is able to cause final collapse of everything in the chain, which is argued to be a conscious observer, something beyond the material, with the ability to collapse the entire physical system. So this decoherence theory, the idea that physical interaction of particles and the environment will cause collapse without the input of a conscious observer, cannot solve the measurement problem. And advocates of decoherence theory openly admit decoherence alone cannot fully explain why there is a collapse to one definite state, or even derive the Born rule for that matter.
All right, let's stop here. Let's stop here for the moment. So in terms of his description of the measurement problem, I think it could be a little bit clearer, but I don't have too many objections to that. So this notion of decoherence is a little bit subtle, but I mean, the basic idea is that many people will say that, I'm just thinking about where the best place to start. Many people will say that when you interact with a quantum state, with say a measurement apparatus, then you will cause the collapse of that quantum superposition because it interacts with the measurement apparatus. I mean, and that's the idea of decoherence, that the different states, the different possible states that are described by the quantum system sort of decohere from each other, sort of separate from each other, and you get one outcome. And that happens when the system interacts with something else outside the system, namely some sort of measurement apparatus. So some people say that is sufficient to account for the notion of collapse. Now, although whether that is correct is disputed. Actually, I think I might show a survey here to illustrate that point, because even physicists disagree wildly about this. I will share my screen to show you this.
Yeah,
this is actually mentioned in a later video, but I think it might be good to bring it up now to illustrate the point that I'm making, because I don't really want to, that's not what I want to share. I don't want to make a claim that's too strong here, because I don't think it's actually clear. This is, as far as I know, the best survey we have about what physicists, or mostly physicists, think about interpretations of quantum mechanics. This was done at a 2011 conference about the quantum physics and nature of reality. So basically quantum foundations, I think they call it, a quantum interpretation of quantum theory. Yeah, to our knowledge, it's the most comprehensive poll of quantum foundation views ever conducted. I think there are about 30 participants, most of them physicists, a few philosophers there as well. So again, this is not really great evidence, but it's much better evidence than just asking one individual physicist or playing clips from popular documentaries, which IP likes to do a lot. So this is just illustrating that there's not a lot of agreement here. And what I wanted to illustrate here is this, well, at this point, is this question here, the measurement problem. So you can see that there are quite a few different answers here. Note that the percentages won't necessarily add to 100, because respondents could select multiple options because they're not necessarily mutually exclusive. So we have some people saying that the measurement problem is solved by decoherence, but most people don't think that's true. Most people think it will be solved some other way. Some people think that it's a severe difficulty, but most don't think it's a severe problem. Some people think it's a pseudo problem, and then some people don't agree with any of these. So basically, it's sort of all over the map here, except for most people don't think it is solved by decoherence by itself, although there's a small percentage who do. So from my understanding, I don't think that decoherence by itself does solve the measurement problem, although I do think that it is relevant to respond to some of the things that IP will say later on about observation and things like that, because there's a misunderstanding about what observation is. But I think the measurement problem is still a problem. Basically, from my point of view, comes down to how do you go from the Schrodinger equation quantum system to the collapsed system where you observe the electron, say, in a single state, like a single position at the time you make the measurement? What is happening there, and how do you sort of connect those two states of affairs? I think that that's still an issue in terms of we don't have an agreed upon theory or explanation as to what's really happening there. So I think that's all I wanted to share at the moment. So I'm just having a quick look. Yeah, there's some more we'll look at later, but that's what I wanted to illustrate there. So most of physicists would agree that, although not all, but most would agree that decoherence by itself does not solve the measurement problem. So in that sense, I think IP is correct, though you will have some people who disagree. I want to emphasize that. So where IP, I think, starts going wrong is when he starts talking about the need for something outside of the physical system. And then he starts talking about minds. So, I mean, at this point, he's not even established that minds are outside of physical laws. Most physicists would think, like most neuroscientists, that the mind is itself ultimately reducible to quantum interactions, in the molecules in the brain. But putting that aside, I think that IP is incorrect in saying that the fact that decoherence doesn't solve the measurement problem somehow implies you need to draw on something that's outside of the quantum universe, something that is like non-physical. Because really the measurement problem is just an issue of trying to understand the logic of quantum mechanics. There are different interpretations of quantum mechanics, which I'll get to a bit later. They all have different explanations as to how the measurement problem can be resolved, or how it's a pseudo problem, or whatever. They have different things to say about it. So I don't think there's agreed upon answer here, but to answer it, there's no need to appeal to anything outside of the physical world. I don't actually think that would be a good answer, as I'll explain a little bit later. We just need basically a mechanism to explain what's happening between the sort of the Schrodinger equation and then the collapsed state after it interacts with some sort of measurement apparatus. There are different ways to address that. They're often reasonably technical, which is why I don't want to start explaining them now, because I want to wait until we talk about interpretations of quantum theory. All I want to illustrate at the moment is that IP has just sort of jumped to this assumption that there has to be something outside of the physical universe. But that's false. You just need a mechanism or a theory and explanation for what is happening, going from one sort of state of reality to another, essentially. And yes, most physicists would agree that decoherence is not by itself the be-all and end-all of that, although it's part of the answer. But to just say, oh, it has to be consciousness because that's outside of the physical is just a gross leap. He doesn't really justify that.
So I don't know if this would be the right point to mention this. Maybe later on would be. So say if you think it would be more appropriate then. But in terms of that Von-Neumann regress problem that he's trying to solve by positing like a conscious observer as well. So what IP wants to say is that God's observing everything, though. And then it kind of becomes unclear to me how anything could be in that like probabilistic state, because surely everything is being observed by God. So everything must have been collapsed on IP's worldview if God's observing everything.
He does actually address this later, and I don't think his response is very good. But yes, hold that thought, because that is a problem. See, there are big problems. So one issue is that he misrepresents the physics that he's talking about. Another issue is that even if you sort of go down the line of the explanation he's presenting, I think there are major problems with it, independent of the evidence he presents. And so that's a very good point, and we'll get to that in a bit.
Should we continue that at this point? Mind Onion, who I think is doing a PhD in physics, has said, you're explaining this stuff really well in an area where he usually sees people muddying the water. So props for that, James.
Well, I'm doing my best. Let me know. Let me know if I make an error. But let's keep going with the video.
I removed the thing.
Hello? Oh, yeah, we're back. I can't
Are you
hear
okay?
anything.
Oh, sorry. I muted the audio so you didn't get the echo problem, and forgot to unmute it. So we'll replay that little segment. Sorry, everyone.
At some stage, we still have to apply the usual probability rules of quantum theory. Claims that simultaneously the measurement problem is real and decoherence solves it are confused at best. Decoherence arises from a direct application of the quantum mechanical formalism to a description of the interaction of a physical system with its environment. By itself, decoherence is therefore neither an interpretation nor a modification of quantum mechanics. Now, why would they say this? Well, many physicists, like G. Grubel, in his paper The Quantum Measurement Problem Enhanced, have pointed out initial state environmental effects cannot explain the occurrence of definite experimental outcomes. The environment lacks the ability to choose between the possibilities of the wave function and choose one to be actual. Plus, the environment is also described by the same quantum laws and has the same problems already specified. This is why Stephen Adler says, decoherence in the absence of a detailed theory showing that it leads to stochastic outcomes with the correct properties has yet to achieve this status. Even in preferred states predictability, classicality, and the environment-induced decoherence, Zurich refers to the observer being involved in the ultimate collapse. Something beyond the physical system, not described by quantum laws, needs to initiate this final or ultimate collapse. Stephen Barr explains it like this. The observer is not totally describable by physics. If we could describe the mathematics of quantum theory, everything that happened in a measurement from beginning to end, that is, even up to the point where a definite outcome was obtained by the observer, then the mathematics would have to tell us what the definite outcome was. But this cannot be, for the mathematics of quantum theory will generally yield only probabilities. The actual definite result of the observation cannot emerge from the quantum calculation. And that says something about the process of observation, and something about the observer eludes the physical description. So what is special about a conscious observer?
Okay, pause there. I need to comment on that. So I think Barr was one of the physicists who adheres to that. There are a few physicists who are on board to some degree with IP's consciousness causes collapse.
Well, he's a Christian as well, I think, a Catholic.
Oh, I didn't know that. Yeah. So he can. So the thing is, sometimes he quotes from physicists and they're saying basically mainstream stuff, and then sometimes he quotes from physicists like that who are saying pretty fringe things. So there are some physicists IP can appeal to agree with at least some of the stuff that he's saying, although they'd probably articulate it better than he does. But the point is, it's not always easy to distinguish that unless you're sort of careful. So what Barr was saying there, I think, is basically fine because, at least in the way I interpreted it. So Barr is saying that there's something about, so remember when the collapse of the wave function happens, or as far as we can tell it happens, there's something outside of the physical theory that we need to account for what is happening there. And I think that's essentially correct, because remember, there's no aspect of quantum mechanical theory that tells you like how it is that the system collapses from being in a superposition of different states with different probabilities to one specific state when you make the measurement. According to the traditional Copenhagen interpretation, that's just how it works. And we can describe the probabilities of different outcomes, but there's no particular explanation or reason that can be given for why you get a particular result on a particular occasion. And so that is outside the physical theory. It's not specified by the theory. Now, some people think that there's deeper theories that will give us an answer. Other people don't. So that's disputed. But it's the point there's when Michael is saying that, or at least, I mean, I don't know the exact context, but if he's, to the extent that he's representing mainstream physics, all he's saying is that the theory doesn't say anything about how collapse occurs in a particular instance and why it collapses to a particular state. He's not saying that there must be something non-physical that's outside of the system. I mean, he may think that, and certain people think that, but that doesn't follow from the other things that he was saying. So there's just a subtle difference here about the point being made, and it's easy to miss that point. So what were you saying?
Well, just I remember that something he said, and I'm paraphrasing, was like that the system itself can't choose which outcome to collapse into, which
that's right.
Which is right, but it seems to be like, like the idea of choosing. Does it have to choose which outcome to collapse into?
Well, and I would say that's not the best language to use, because if we're giving a mechanistic theory, then choice is probably implies an agent, right? And I mean, unless you sort of presuppose there's an agent, it's not clear where that fits into the theory. Right. Yeah, and again, so in the Copenhagen interpretation, there's nothing in the environment that will specify which state it will collapse. The wave function will collapse into when you take a given measurement. So yeah, I think that's correct. Different interpretations may have something to say about why it collapses in a particular way and then others don't. But yeah, the notion of choice, I think, is a red herring here.
Yeah. Okay. Shall we carry on?
Yeah, let's keep going.
Apparatus cannot do. Well, apart from not being described by physical laws, the observer has the ability to put the right questions into nature and yield a result. As Henry Stapp says, the observer in quantum theory does more than just read the recordings. He also chooses which questions will be put into nature, which aspect of nature his inquiry will probe. I call this important function of the observer the Heisenberg choice, to contrast it with the Dirac choice, which is the random choice on the part of nature that Dirac emphasized. According to quantum theory, the Dirac choice is a choice between alternatives that are specified by the Heisenberg choice. The observer must first specify what aspect of the system he intends to measure or probe, and then put in place an instrument that will probe that aspect. In quantum theory, it is the observer who both poses the question and recognizes the answer. Without some way of specifying what the question is, the quantum rules will not work. The quantum processes grind to a halt. The interaction chain stems back from an observer's ability to make a Heisenberg choice, which derives a random Dirac choice back from nature. This is how we get one actual outcome from the possibilities of the...
I'm just pausing it there to...
Sorry, go ahead.
I want to say... I mean, like, it might just be that I'm loosely following what's going on, but there is a lot of stuff being, like, thrown out all at once. And it's very difficult to, like, critically sort of to understand what's actually going on and being said, you know, like at the same time as...
I find it very difficult. I've got a decent amount of physics background. So let me try to break it down what he's saying here. I was about to suggest pause it. So I don't think he really needs this language of Dirac choice and Heisenberg choice. I'm pretty sure that's idiosyncratic anyway to whoever he was quoting. Okay. But so now I've got to remember which one is which. I think it was, so the Dirac choice, can you just bring up the previous slide just to make sure? Yeah, okay. Okay. So when he says Dirac choice, what he means is you start off with the wave function quantum superposition, and then there's some sort of interaction with the environment, a measurement is made, and the system collapses into a specific outcome. So like the electron is in a superposition of being in different places, and then you measure it and it's in one specific place. That's what this means by Dirac choice. It means the choice, and again, we're using that in a loose term, it doesn't necessarily connote a conscious agent at all, about where the particle actually is. So as far as we know, that is random, although it does depend on your interpretation of quantum theory. So that's sort of standard collapse of the wave function is the Dirac choice. Now, this Heisenberg choice is really a choice about what to measure or how to set up your apparatus to make a particular measurement, because there's different things you can measure. For example, you can measure the position of an electron, or you can measure the momentum of that electron at a given time. And it turns out you can't measure both of them at the same time to arbitrary precision because of something called the Heisenberg uncertainty principle, which I won't try to fully explain now. But I think that might be why he's calling it the Heisenberg choice, just because we make a choice, or the observer makes a choice about how to measure the system or what observation to make, and that will affect what you measure and what the system does. Now, the way that this is articulated by IP, with where he talks about observers, where he's got this image of a brain there, or a head that represents a mind, and he's talked about that. This is really misleading, because when we talk about an observer in quantum mechanics, this doesn't mean a conscious mind. I mean, obviously to interact, like to actually know anything, there's got to be a person in the chain somewhere, right? Because otherwise we can't report on quantum outcomes. But that's not actually critical for the quantum mechanics per se. It's critical for us understanding the quantum mechanics, obviously. But an observer really, in this sense, is just anything that's interacting with the quantum system to cause a collapse of the wave function. So you can think of this as like a detector that just detects the electron position. It is observing the electron and collapsing the wave function and measuring it in a particular place. So we generally set up experiments, and so we choose where to put things. But again, nature can do that as well. If there's a particular environment where the electron is, if the electron interacts with that environment, then the setup of that environment will determine how the wave function collapses, and then what state the electron actually ends up being in. So the notion of observation here is really about interaction with of a quantum system with its environment, and how that collapses the wave function, and sort of what states result from that. It doesn't it doesn't necessitate anything about a conscious observer. Now, the confusing thing is that most of what we know about quantum mechanics comes from experiments that we set up. And so there is a connection there, obviously, because we have to design the experiments. But this is all happening in nature all the time. It's just that we can't, like, it's much more complicated, and we can't extract the experimental results from how it goes up in nature, obviously, because it's not controlled, and there's more moving parts than we can like understand. So generally we work on very abstract, simple systems to determine these results. And that's where it gets a bit confusing, because there is like an observer constructing the thing. But for the logic of quantum mechanics, no conscious mind is necessary. This all happens just when there's quantum processes that interact, or decohere is a related word, with their environment. And that collapses the wave function, or that's related to the collapse of the wave function, which is the Dirac choice. So again, to summarize again, Heisenberg choice is like how the experiment is set up, and Dirac choice is what the wave function specifically collapses to. Now, it's really not surprising if you describe it this way. Obviously, the setup that a quantum system interacts with is going to determine what happens to that quantum system. That's really not surprising. That's a little bit like saying where you place a ball on a slope determines how fast it rolls down, or like how fast it's going when it gets to the bottom. Right. Well, that's not surprising. There's nothing mystical about that. It's just the environment that it's in determines how it behaves. And that's essentially what is the physical content of the Heisenberg choice here. There's nothing that, I mean, you can interpret it as being a conscious mind if you like, but there's nothing that requires you to do that. And I would say that it's unnecessary and superfluous to assume any conscious role there. It's just how it's set up such that the environment is set up such that the quantum system interacts with that environment. So does that clarify a bit about what's happening here?
Yeah, I think I want to ask some questions along those lines, though, because I think that when I was doing A-level physics in the UK, this is something that goofed up when I first came to trying to understand quantum stuff. And like when we're looking at, like single photon double slit experiments for the first time, that equivocation of the use of observer, like, does it mean conscious observer, or does it mean like a camera that is set up, or some kind of photon detector that's set up, which isn't actually conscious? Really, like I started to think along those lines of like, oh, there has to be a conscious agent detecting. I mean, like I didn't really have a understanding of philosophy of mind at all either at that point. But I'm thinking, like in these experiments, my understanding was that there's actually quite a lot of these experiments, and I think Mind Onion has said something similar as well, where it's non-conscious detectors that are measuring the collapse. Could you give like a few examples of those sorts of things if you're aware of any off the top of your head? If not, don't worry, because I'm not aware of any off the top of my head. So if you've got some to hand, that's
well, actually, we're going to look at one of these later when we talk. Is it the next video? Let me check. Yeah, the next video is the delayed choice quantum eraser experiment. So that's a specific an experiment that has detectors. So in this experiment, there are I think they use lasers that shoot one photon at a time, or special lasers that can shoot one photon at a time, and then they're detected by screens. I don't know the physical construction of the screens that detect photons, but I mean you can think of a CCD. I think they're probably just variations of that, a charge coupled device, just like you're in your camera. It's just a physical object that's able to detect when it's dissolved by a photon. That would be an example of an observer, or it could be a system of electromagnetic fields that can detect changes in, like when a charged particle moves past. Another example might be you might have seen pictures of tracks in bubble chambers where you see the spirals of the particles. Yeah, right. I think that some of them actually use gas, I think, or water. I don't know the details of that, but that system would be another example of an observer, because when it interacts with that, it would collapse the wave function. So it's really just any physical device, or apparatus. It may help if I share the Wikipedia on this, which just briefly. Why can I never find what I want? Oh, yeah, it's because it doesn't show the tab. So I actually have to share, what is this thing called? A snapshot? No, that's the
application
StreamYard.
window.
So I share StreamYard, and then I can move to this. Is that working? Can you see this? Observer quantum physics? Yeah. I'll just move
Might need to, can you zoom in? Yeah.
Is that better?
Yeah, I can see it at least.
Yeah, I'll do one more. So this is a short article, but it gets the point across. So some interpretations of quantum mechanics posit a central role for an observer. blah, blah, blah. The term observable has gained a technical meaning denoting a Hermitian operator that represents a measurement. I won't explain what that is, but that's a technical, that's a theoretical concept there. Now, this is important here. The prominence of seemingly subjective or anthropocentric ideas like observer in the early development of theory has been a continuing source of disquieting philosophical dispute. A number of New Age religious or philosophical views give the observer a special role, place constraints on who or what they can be. There is no credible peer-reviewed research that backs such claims. As example, such claims, I don't know who this is, a physicist apparently. The crucial feature of atomic physics is that the human observer is not only necessary to observe the properties of an object, but is necessary even to define those properties.
Right.
Oh, a deep ecologist. Okay, there you go. They tend to be into this stuff. So what I wanted to show here is what Werner Heisenberg has to say about this. This is what I mentioned. This is the sort of this is the standard interpretation of quantum physics that you'll get if you do pretty much any mainstream course in these. Most textbooks present the Copenhagen interpretation, often without saying that that's what they're doing, which does lead to a bit of confusion. But anyway, so here they talk about observers and measurement a lot, but it's just a physical process. So here's what Heisenberg said. Of course, the introduction of the observer must not be understood to imply some kind of subjective features to be brought into the descriptive nature. The observer has rather only the function of registering decisions, processes in space and time, and doesn't matter whether the observer is an apparatus or a human being, but the registration, the transition from a possible to actual, so that would be collapse of the wave function, is absolutely necessary here and cannot be omitted from the interpretation of quantum theory. Here's another example. All unambiguous information concerning atomic objects is derived from permanent marks, such as spot on a photographic plate, caused by the impact of an electron left on the bodies, which define the experimental conditions. Far from involving any special intricacy, the irreversible amplification effects of the recording of such objects rests on there being an irreversibility inherent in the concept of observation. So again, that's basically collapse of the wave function. The description of atomic phenomena has in these respects a perfectly objective character in the sense that no explicit reference to any individual observer, and therefore with proper regard to, ignore that, no ambiguity is involved in the communication of information. So really an observer in this sense is just anything that collapses the wave function, I think, if I were to put it in a short sentence. And it's what we use to conduct experiments to register effects of quantum systems. So we're talking about physical apparatus here. Obviously, to report these, a conscious person needs to look at them and write a paper, but that's not what is meant by observation. It's the physical apparatus that is making the observation in this sense, not the person who reads that and writes a paper about it. Yeah,
someone jokingly said the collapse happens when the conscious observer looks at the data.
Well, if no one reads the paper, does it ever collapse the wave function?
Yeah. Right. Shall we continue on?
Yep.
The wave function. Only the observer has the ability to choose, give a Heisenberg choice, between possibilities. Non-conscious measuring devices cannot. John Gribben and Paul Davies say in their book, The Matter Myth, the observer plays a key role in deciding the outcome of the quantum measurements. The answers and the nature of reality depend in part on the questions asked. They were, of course, building off of Niels Bohr, who once said in reply to Einstein, "To my mind, there is no other alternative than to admit that, in the field of experience, we are dealing with individual phenomena, and that our possibilities of handling the measuring instruments allow us to make a choice between the different complementary types of phenomena we want to study. Denying the observer plays a fundamental role simply doesn't make sense, and the majority of physicists realize they have to accept this." A recent poll demonstrated that over 50% of physicists...
This is the paper that I just showed you.
The observer plays a fundamental role.
So let's look at this here. Go ahead.
No, I'm just saying it's interesting considering what you would... Is it going to show the decoherence?
I don't think so.
No. Yeah, it doesn't look like it.
Well, this doesn't actually support what he's saying either, but he sort of spins it in a way that it does. So this is a question about the role of the observer. So again, these are not mutually exclusive options, or not all of them are. So is a complex quantum system, I would generally agree with that, should play no fundamental role whatsoever. It's really unclear what that means. What does it mean, no fundamental role? But some people don't like the role of an observer, even just in a purely like a mechanical sense in quantum theory. They would prefer one that there are some interpretations of quantum mechanics where the observer doesn't actually collapse the wave function, where there's it collapses itself, very loosely put. We'll get to those later. But see here, plays a fundamental role in the application of the formalism, but plays no distinguished physical role. So this is, I would say, the mainstream view, so much as there is one. That is, you need something that collapses the wave function for the formalism to work, because, as I said, there's a critical distinction between the Schrodinger equation, which describes how the wave function evolves over time, which is deterministic, and then the collapse part, which was described as the Dirac choice before, which leads the wave function to collapse into one specific state. So that's what is meant by, I was just getting to that. So that's what is meant by it's important in the application of the formalism, but plays no distinguished physical role. I think the way I would describe that is that there's nothing special about the observer physically. It's just something else, essentially, what you might call the environment. So there's a quantum system and then its environment, and the whatever is doing the observation, like whatever detection apparatus, is part of that environment. So one way that you can describe this in terms of decoherence is that macroscopic objects like a physical detector have many more internal degrees of freedom than quantum states. And a degree of freedom is just like a way that the system could be different. So think about like a molecule could be slightly to the left or slightly to the right. And, my microphone would be the same. In fact, the molecules are jiggling all the time because of thermal energy. So that's a degree of freedom, right? Actually, lots of degrees of freedom. And macroscopic objects have huge numbers of those, whereas quantum objects have very few degrees of freedom by comparison. Right. And so, again, I don't fully understand this, but I think the basic idea is that when a quantum system, like a single electron, say, becomes entangled with a macroscopic object, almost all of the degrees of freedom are subsumed within the macroscopic object. And so basically, it's like that we don't see the different possibilities of the quantum object because the macroscopic object is so large compared to the quantum object. And because almost all of the physical degrees of freedom of the macroscopic object are kind of look like they're indistinguishable to us. You can't see the difference. And so it's basically like, this explanation is a little bit unclear, but it's sort of like the microscopic object gets subsumed in the quantum description of the macroscopic object. Almost all the states of which are indistinguishable to us at a macroscopic level. So there's some probability.
Can I describe back to you what I think I heard you just say, and
Sure.
then if I've not got it right, you can elaborate. So you're saying like we've got this mathematical description of the degrees of freedom of the particles, and you said that when like something at the quantum level in size engages with some like a macroscopic object, then in terms of the description, all we can really talk about is the degrees of freedom in the macroscopic object from our point of view. Is that right?
Yes.
Is that,
yeah. And whereas for the single particle, there's a decent probability that it could be here or it could be there, for like my microphone, there's almost no chance that you're going to find it move slightly to the left. Like there is a probability, but it's so tiny because of the size of it. Like the size right. matters in the quantum world. So this is not an answer to the measurement problem because it doesn't explain how the collapse occurs, but it's a description of decoherence, how a quantum system becomes entangled with its environment and becomes sort of classical as far as we can tell, because it sort of gets subsumed into the larger macroscopic object that it entangles with. So that's called decoherence. And so that is what is being referred to here, that the measurement plays an important role in the formalism because it sort of has the effect of collapsing the wave function and causing the decoherence, but it doesn't play a distinguished physical role because it's quantum like everything else. It's just, we interact with very large quantum things differently to very small ones, I guess is the simplest way to put that. Now, if we move to D here, people who are saying that the observer plays a distinguished physical role, such as quantum consciousness causes collapse, is 6%, which I think is 2 people in this survey, or 1 or 2 people. Right. So it's a very small percentage of people. And I mean, this is one survey, but I think that's indicative of the field pretty generally, that there are some people saying this, but they're a small minority. And I would say that C is correct. So you do need the idea of an observer for the formalism to work, but it's not you don't need an observer in a sense that it's something that's outside the material universe, for example. It's just something that collapses the wave function.
Yeah.
Now let's see how IP responds to this.
Role in the application of the mathematical formalism, but then only 6% accept any physical role, which means they accept the math tells them one thing, but deny the philosophical conclusions from that math. And this really isn't justified or logical, especially if the mathematics can only make sense if the observer plays a fundamental role. Why deny the object?
I mean, that only works if you equivocate on observer, right?
Well, it works if you have a preferred interpretation of quantum mechanics, which gives you an answer to the measurement problem, and IP does, right? But the thing is that he hasn't really defended his interpretation. He's just going to say, well, you need to address this question, which I think, well, I mean, most physicists aren't really interested in this sort of aspect of it, but some are. And I think that, yeah, there are questions to be asked here. The measurement problem is a real problem. In fact, most people in this survey agree with that. Although I would say that this was a conference on, a quantum foundation, so there would be a selection effect there. Physicists who use quantum mechanics as a sort of just a descriptive tool are less likely to go to a conference like that. But even so, yeah. But the idea that what IP is saying is that the theory tells us one thing, and then you're sort of ignoring the clear implications. But that's just false, right?
It's Romans 1, James.
Yeah, well, maybe it is. What the theory is, the theory is incomplete. This goes back to one of the earlier quotes, that the theory doesn't tell us how this collapse occurs, or it doesn't have a clear resolution for the measurement problem. In order to provide an answer, you need to go beyond what the theory says. You need to interpret it, and that's where the different interpretations come in. Now, IP has his preferred interpretation, but instead of saying, well, other people have their own interpretations and let's compare them, he's just basically saying that his is the only interpretation allowed, because everyone who chose option C agrees with basically agrees with a different interpretation of quantum mechanics than he does. Because basically option D, that like consciousness plays a role, is just one type of interpretation. There are many others that don't hold to that. So it's just wrong for him to say that there's a clear interpretation of the quantum mechanics here. He has his interpretation, which leads to the conclusion that he's drawn. Other people have theirs that doesn't lead to that conclusion. And he hasn't really actually compared the interpretations. He just says that because other people disagree with him, then they're sort of not following the evidence. Well, but without explaining how he gets to that conclusion from the evidence.
Yeah, it doesn't, just because 6% say that consciousness does play a role, it doesn't give you the warrant just from those statistics to like say, well, here's what the rest of them actually think about it. You'd need those questions to be there in the survey and have them checking the box and answering.
Well, it actually was, right? Option C says that most of them don't agree that consciousness causes collapse.
Well, yeah, but I mean, in terms of offering those alternative explanations as options as well.
Right. Well, the survey actually does. So maybe now's the time to start talking about that a bit. So let me pull that up. Yeah, that's a good point that you raised. So, oh dear. Share screen, snapshot. Okay.
There we go.
So let's jump to. Which one was it? Here we go. What is your favorite interpretation of quantum mechanics? So I have prepared something that I'll show you in a moment, which is a list of some of the main interpretations. It seems that every source gives a slightly different list because it's a bit subjective in terms of how you combine some results or whether you include some as subsets of others. I would say there's something like a dozen mainstream interpretations of quantum mechanics, and most of them are included here. I'll explain some of what these mean in a little bit, although I certainly don't understand the details of all of them. But I just want to bring out some of the main points here. First of all, here's the Copenhagen interpretation. That's the mainstream sort of old school interpretation. It's still a clear, plurality here, although information theoretical is pretty closely related to Copenhagen as well. So I would probably include a lot of that under this. Although I don't think they have. Oh no, they do have quantum Bayesianism. Okay, so that's a different thing. The Everett, which gets a lot of press, is the many worlds interpretation, which says that any possible collapse that can occur does actually occur, but just in its own universe. That has some degree of popularity, but it's a clear minority.
Why aren't we talking about the de Broglie-Bohm interpretation, James?
That's here, but no one at the conference.
I know. That's why I said it. Just
you can't interpret the 0% as being like no one supports it. It just means that no one at the conference happened to. So, but there are people who defend all of these. It's just that they're all kind of minority views because apart from Copenhagen, which generally most people work with, no one really agrees. Now could that be because it's what's taught in the textbooks, like you said as well? I think probably that's the case. It's just what most people are familiar with. Many quantum physicists don't really know much about these interpretations. I was never really taught anything much about them apart from Copenhagen, because for most intents and purposes, it doesn't matter because the formalism is the same. It's just a subset of people who are actually interested in these questions. Anyway, I'm trying to see it doesn't actually even have the Von-Neumann, I've forgotten the name of it. Let me pull up forgotten the name of it. Wigner, that's right. The Von-Neumann-Wigner interpretation, which I think is what IP is advocating for. That's the conscious minds cause collapse. That's not even really here. That would be under other, I guess. But the point is that different interpretations here give different answers to the question as to what's the answer to the measurement problem. Now, maybe at this point, and so you see that most people don't agree with IP, maybe I'll share this for you. And we're not going to go through this in detail. This is partly just help me. And this is sort of work in progress because I need to... Wait, why is it coming up with that? I need to understand this better myself. So, I mean, you might not be able to see all of that. Maybe I'll zoom in a little bit. This is a spreadsheet that I sort of based on Wikipedia, but have worked on a little bit, describing some of the main interpretations of quantum mechanics. So I've got 11 here, but you'll see slightly different numbers in different lists. So let me just summarize a few key points here. So basically, these interpretations are trying to answer questions like, is quantum mechanics actually deterministic, or does it have true randomness as part of it? Is the wave function real, or is it just like a tool that we use to describe our ignorance? Right. Are there any hidden variables that determine what's happening at the level that we can't like measure, or not? Does the wave function actually collapse, or is that just an appearance of collapse that occurs because of limits of what we can observe? Does the observer play a distinctive physical role in the collapse? That's actually the question that asks. So you can see here that was asked in that survey. You can see here that most interpretations don't give the observer a causal role. One that does is the Von-Neumann-Wigner interpretation, which is consciousness causes collapse of the wave functions. That's basically what IP is defending, although I don't think he calls it that. Many minds interpretation is even crazier, in my opinion. It's basically many worlds plus consciousness causes collapse. It's like each mind makes its own world. Yeah. So according to many worlds, there's no such thing as wave function collapse. Whenever there's some sort of whenever there's sort of some sort of quantum measurement, all possible outcomes are physically realized in a different world or universe.
Yeah. So that's like a modal realist sort of, yeah.
It's a bit like that, yes. Yeah. So there the wave function is real. Observers don't play any critical role, but the wave function never collapses. It just sort of splits into different universes. So the many minds is kind of like a combination of the two above it. And some of the others that have an observer role is these two down here. And this is a bit misleading because the quantum Bayesianism interpretation says that the quantum state isn't actually real. It represents the degrees of belief of an agent about the outcomes of different experiments. Right. So it's actually more of an instrumentalist interpretation.
That's interesting.
Than the sort of it's not really causal. It's not saying that the agent like causes the outcome. Yeah. It's just that the agent's necessary to make any sense of what's even happening in a quantum measurement. It's the agent asking questions.
Epistemic access. Yeah, the agent's epistemic access to the facts about the state of affairs, the quantum stuff.
Well, and I think it's sort of agnostic about the underlying state of things. So it would say that there's no objective wave function because the wave function is a description of the degrees of belief of an agent. So it's not something that exists in the world. It's something we kind of impose on it, I guess, or we use to describe our ignorance. So I would call that an instrumentalist interpretation in the sense that it doesn't say that quantum mechanics like describes reality the way it really is. It's sort of like it's just our way to understand what's happening, whatever that might be. So that's a new interpretation, which is kind of interesting. Now, I prefer more realist interpretations, and we'll talk more about those in a little bit because this is a main point of contention. Does quantum mechanics describe reality as it really is in some sense, or is it a way of describing our ignorance or predicting experimental outcomes or something like that? The Copenhagen interpretation, the mainstream one, is pretty agnostic about the realism question, so it doesn't really care. It's more about, well, can we use it to predict experimental outcomes? So I've bolded the interpretations that I personally find most interesting or intriguing. So you can see these three ones here. I might just mention them in passing. I'm sure there'll be viewers who are like, no, that's rubbish, but these are just my preferences here. So the de Broglie-Bohm theory, which is also called hidden variables, says that there are hidden variables that actually determine the outcome of the quantum system. So that is, when the wave function collapses, there's something that determines what state it collapses into. It's not it may appear random to us, but there's some sort of underlying causal processes that determine that. And those are called hidden variables. And so it believes that there is such a thing as a wave function and it does collapse, but it's sort of deterministic because it's determined by these hidden variables that we can't observe. So I think that's quite interesting because it gives an answer to how the wave function collapse works, that it's determined by these underlying factors that we can't definitively measure. One issue there is that it turns out that if you go down this road, quantum mechanics must be local. We'll talk about what that means a bit later on. I don't want to go into that right now. Okay. Sorry, I should have said non-local. It must be non-local, which some people think is a problem. Whoops. Now, a couple of other interpretations. We've already talked about these ones. Objective collapse is, I think, quite interesting. If I had to pick one, I might pick this one. This says that this also augments the Schrodinger equation with something else, but instead of hidden variables, it's basically these. It's sort of like frictional terms, if you like, that basically cause the wave function to spontaneously collapse after a certain amount of time, and this causes it to be localized in space. And so basically what this means is that the bigger the system, the more quickly the wave function collapses, and it does so spontaneously. So this is why it's called objective collapse, because there's no role really for observers here, and it's not that the wave function collapses when you interact it with the environment per se. It'll spontaneously collapse by itself. And this actually makes testably different predictions to like the Copenhagen interpretation. And people are trying to see if that can be falsified or not. But at the moment, it's still a live option. You'll see here that it's non-deterministic because these work randomly. So that's one difference with the hidden variables, which says it has the underlying determinism, whereas objective collapse says no, and there's no hidden variables. But it also says the wave function is real. Transactional interpretation is a bit crazy. It says that not only is there a wave function, but there's also like the complex conjugate of that goes backwards in time, and you can think of what's happening as a sort of a transaction which between the two, which transfers momentum and energy. I didn't fully understand that by any means, but it seems like it's quite interesting in the way it gives an objective description of what happens during a wave function collapse. Again, it's non-deterministic and says the wave function is real. There are other interpretations that don't say as much. So consistent histories is one that's got more popularity, which says there's no such thing as a real wave function. It's just a description that we use to like predict experimental outcomes. And so no real collapse of the wave function. So I think those are the main ones that I wanted to mention at this point. So the key takeaways are that there are a lot of interpretations of quantum mechanics. Most working physicists would be Copenhagen interpretation or something similar, but there's not a lot of agreement here. They pretty much all make the same experimental predictions, although some of them can potentially be tested, but it's still a work in progress there. And one of the main differences between the interpretations is whether the wave function is something that's real or whether it's a tool that we use to describe our ignorance of the state or the experimental outcomes. Another is whether the wave function really collapses or not. So under the many worlds interpretation, it never collapses. It just sort of splits into different worlds. But then under like objective collapse, it does collapse. And also whether there's an intrinsic role for observers. So for some, like the Von-Neumann Wigner and the many minds, there is a role. But for many others, there's no intrinsic role for observers. So the issue here with what IP is doing is that he's just sort of pretending that these interpretations don't exist. I should say he does have two videos on this, one where he looks at many worlds and one where he looks at the de Broglie-Bohm interpretation. I decided not to look at those today because I had enough, got enough to look at. But he doesn't really talk about any of the others. And I mean, I kind of agree with him. I don't really like many worlds for a variety of reasons. So the point is that if you're going to say we need to answer these questions, like of the measurement problem and so on, you can't just sort of imply that no one else has answers to these questions and it's only the quantumness causes collapse option, because that's just one interpretation, which I think has major problems, which we'll get to. And really what you need to do is sort of work with these different interpretations and describe the pros and cons and try to work with how could we decide. And most physicists don't really bother that much because we can't really decide at this point. Most of them are pretty much experimentally equivalent. Or if they can be distinguished, it's very difficult. We're still trying to work out how to do that. So I just think that IP is really overstating any case he might have here by just saying, oh, well, there's a measurement problem, so we must account for this by consciousness causes a collapse. when there are other options as well that he doesn't even really address.
Yeah. I'm just trying to figure out, someone in the chat has been studying us and has finally figured us out. That's going to be a distraction. No idea.
That's an interesting comment. I don't know what that means.
There we go. Right. So shall we play out the last minute of this video?
Let's continue.
Yeah. Okay, cool.
Obvious conclusion that follows. Henry Stapp rightly points out why physicists deny this philosophical conclusion. It's metaphysical prejudice. Some are trying to hold to metaphysical beliefs about the world that quantum mechanics and the role of the observer challenge. One must ask whether it is really beneficial for scientists to renounce for all time the aim of trying to understand the world in which we live in order to maintain a metaphysical prejudice that arose from a theory, classical Newtonian mechanics and materialism, that is known to be fundamentally incorrect. The fundamental role of the observer is even harder to deny with the experimental confirmation of the Kochen-Specker theorem in 2011. This shows that the outcome obtained by an experiment crucially depend on how the experiment is done, meaning we are not passive observers. Outcomes are happening based on what we input into nature. As one paper explained, the Kochen-Specker theorem states that non-contextual theories are incompatible with quantum mechanics. Non-contextuality means that the value for an observable predicted by such a theory does not depend on the experimental context. So when we perform experiments, we are not just passively observing how nature progresses, but are actively affecting what the outcome will be by how we observe things. As they say in the New Scientist magazine, the values you obtain when you measure its properties depend on the context. So the value of property A, say, depends on whether you chose to measure it with property B or with property C. In other words, there is no reality independent of choice of measurement. So the Kochen-Specker theorem directly demonstrates the outcome depends on what we experimentally put into it. As Anton Zellinger says,
the Kochen-Specker theorem talks about properties of one system only. So we know that we cannot assume, to put it precisely, we know that it is wrong to assume that the features of a system which we observe in the measurement exist prior to the measurement. Not always, I mean in certain cases. So in a sense, what we perceive as reality now depends on our earlier decision what to measure, which is a very, very deep message about the nature of reality and about our role in the universe. We are not just passive observers.
Thus, the conclusion necessarily follows. The philosophical implications of the measurement problem cannot be ignored. As they say in the quantum enigma, quantum theory thus denies the existence of a physically real world independent of its observation. The measurement problem is only a problem if one cannot accept the observer plays a fundamental role in shaping physical reality. We are not passively observing the world, but actively involved. As Rosenblum and Kuttner say, physics has encountered consciousness, and our view of the universe will never be the same.
All right,
let's talk about that.
The conclusion necessarily follows.
Yeah, let's talk about the Kochen-Specker theorem. So this is not a result I understand especially well. Oh yeah, the comments are quite interesting. I can't quite read them from this view, but
sorry, I'll let me.
For lack of a better word, when I watch the videos initially, most of what says go over my head, but if you're able to bring it down to my level as well, some videos, I usually go and research as best I can myself. Yeah, you shouldn't really take on too much of what he's saying here, other than as an invitation to explore more, because he mixes up sort of truth from opinion, truth with opinion, and I think out misrepresentation in a way that's quite hard to tell the difference between them.
This is by far the best video on YouTube on quantum theory.
Yeah, he IP also relies on a book called The Quantum Enigma, which I probably should read and do a review on at some point, but it's received criticism but because of basically spreading quantum woo kind of ideas. But anyway, so let me talk briefly about the Kochen-Specker theorem. So this is not a result I understand in great detail, but the basic point here is actually not really that new from what we've discussed before. It relates to a concept called quantum contextuality. IP didn't use that term, but that's what is the broader concept that's being appealed to here. And the basic idea was explained by the physicist at the end there. It's basically that it seems, according to these theorems and results that we've been establishing, that at least for certain types of systems, there's no fact of the matter about what state the system was in prior to a measurement being made. So the outcome depends on the context of the series of measurements that you make, or the experimental setup would be another way to put that. So I was trying to think of a good analogy here, and one that might help is that if suppose I want to go out for dinner and ask someone, hey, what do you want for dinner? And they say, oh, pizza would be good. Now, you might assume that they wanted pizza all along and that they just revealed their pre-existing preference to me. But maybe the fact that I asked them what they wanted was what triggered them to sort of think about it and give that answer. So it's not like they previously wanted pizza and then they just declared that to me. It's like my asking them triggered that response. And maybe if I'd asked in a different context or phrased it differently, perhaps, they would have said something different. Now, obviously, that's only an analogy. That's not literally what's happening here, because that involves minds. But it just occurred to me that might help illustrate the point here. And this should be surprising. When they're saying like what we measured, so the measurements that we make depend on like how we measure or what questions we ask, that just means the way we set up the experiment. So if you make one measurement, then you might get a different result to if you make a different measurement. And they could be inconsistent with each other in the way that like you couldn't have measured both of them. Or it might depend on the order that you make the measurements or something like that. So it just means that the outcomes that you get are not just straight out read-offs of properties that pre-existed your measurements. They may be sort of constituted in part by the measurement. The double slit experiment, which we'll get to a bit more in the next video, is kind of like this as well. So this really isn't that surprising given, it's a little bit surprising the extent of it perhaps, but it's basically part of quantum theory that systems interact with their environment, and the way that they interact with the environment determines what experimental results you get. Again, the delayed choice quantum eraser experiment, which we'll get to in the next video, is just a good example of this. So it's not really fundamentally new here. It's mainly sort of exploring the extent and the exact constraints that this places on interpretations. So again, when IP here is implying that this is some sort of conscious observer dependent phenomenon, it's nothing to do with that. It just means that quantum mechanics operates in such a way that the way a quantum system, the properties that you measure from a quantum system depend on how that system interacts with its environment. If the environment's different, then you get different results. It's nothing to do about a conscious observer or like the questions we ask. The question we ask just means like how we set up the experiment. That's what matters. It doesn't actually matter what we're thinking in our minds, right? It's not a consciousness point. And this will become clear in the next video, where he explicitly, I think, confuses the notion here of what's actually doing the work here.
Yeah, it seemed to me like the work that was being done by that sentence was meant to be like I don't know, I guess sort of like we're creating reality, like in some sort of mystical sense.
Yeah.
Like the questions we ask, like almost like a law of attraction type thing or something like that. Maybe that's just me. I could do it, but it seemed like that was being implied, at least by like the like the world's more magical than we thought. There's it's like what you think manifests reality or something, but that could be my interpretation more than what's being connoted.
No, I think it is kind of related to that. It's misunderstanding what it means by like context and what it means to ask a question. It sort of means by an experimental, it's confusing an experimental setup, which basically means a configuration of nature with something about our intentionality, which is really not anything to do with it. Obviously there's an indirect relationship because we set up the experiments, but if the experiments just somehow poofed themselves into existence, it wouldn't really, it would still be the same.
Yeah, it's not like our sort of thinking about it. On the one interpretation, I suppose our thinking about it was causally linked. But in terms
that's
of what's
IP's
being said
interpretation.
Yeah.
So he's entitled to that interpretation, but he needs to defend that against alternate interpretations and problems of that interpretation, which we will get to. What he's doing that's, I think, incorrect is implying that these results provide evidence for his theory, which they don't, because I think he's misconstruing the nature of an observer.
Right.
And sort of pretending that no one else has thought about the measurement problem.
Well, then, if we move on to the delayed choice quantum eraser experiment, I always find as well, I find, like when when things get worded like this, it makes it sound like a mystical, spooky thing as well, like quantum eraser. Like,
I don't think it's named very well. Other people have pointed this out as well, because there's not really erasure going on, but I mean, it sort of is. It depends on how you interpret it. I think the first half or so of this video is reasonably good, and then when the interpretations come, it gets pretty bad. So we'll
let's do it.
We'll see how this works.
The results of the delayed choice quantum eraser experiments can be mind-boggling in many ways, yet many people misunderstand the implications because they don't understand the experiments. So I'd like to explain the most famous one from 1999 and share the shocking implications of the experiment. But first, we need to understand what a delayed choice quantum eraser experiment means to do by modifying the original double slit experiment. So if you don't know what the double slit experiment is, I recommend stopping here and watching this video on it. Now, if you already understand the original double slit experiment, then you know the implications of placing a measuring device at one slit. Without the measuring device, when we shoot photons through a double slit, we
Isn't the original double slit experiment is just showing that in waves there's interference patterns, right?
I thought he explained that. Maybe we should actually look at that video quickly, or you could just explain it. It's fairly easy to explain.
Just that basically, as you've got these waves that pass through the slits, they sort of the peaks and troughs of the waves sort of superimpose with each other, because there's two waves coming through each of the slits in a way that creates a pattern on the board where they're hitting. So you'll see like if you have two waves coming through the slits, you'll see like multiple. I forget there was a word for it that has gone out of my head. But you see these interference patterns basically. Now the idea was then that so if you shoot a single photon of light through, then you should just see these two slits, but you see the same interference pattern still as you shoot through one individual photons one at a time.
Right, and so the sort of strange aspect of that is that when the photon is emitted by the laser, it is emitted as a single particle. When it's absorbed by the screen or the CCD or whatever, it is absorbed as a single particle, as a discrete unit. But the fact that you observe an interference pattern, if you do this many times, seems to indicate that as the photon passes through the slits, it's acting as a wave, because you only get an interference pattern because of the diffraction of the waves as they pass through and they interfere with each other. You don't get that if it's like you're shooting billiard balls through. So this is an example of sort of the wave-particle duality of quantum mechanics. It seems like the photon's behaving like a particle when it's emitted and absorbed, but a wave as it passes through the slits. And further, you can modify this experiment by placing detectors so that you can tell which slit the photon passed through. It turns out when you do that, you destroy the interference pattern. So it seems that if you force...
That's cool.
Yes, that's important for the delayed choice quantum eraser experiment because it builds on that. So there's the standard double slit where you just have a photon, it goes through, you get an interference pattern. If you then add a detector to one or both of the slits such that you can tell which slit the photon goes through, then you destroy the interference pattern. So you just get like basically one band behind each of the slits, but no interference between them. So that is what you'd get if you just threw billiard balls through. So basically, if you force the photon to interact as a particle, then you get a particle, you get results that are consistent with that, essentially. If you force it to interact as a particle by making a measurement through the slits with a detector there, then it will also act as a particle on the detectors behind or on the far side of the slits, the double slits. Now, what the delayed choice quantum eraser experiment does is builds on that again by basically making it such that you can detect which slit the particle travels through, but erase that information after the fact selectively. Like you can sometimes do it and sometimes not. And so, yeah, some people misinterpret this to be a sort of retrocausation, but that's a misinterpretation. Anyway, we'll see how this works because IP goes through the experimental setup. But basically, this is building on the basic double slit experiment to see how far we can push this idea of what happens if we sort of work out where which slit the photon is going through, but then like erase that information somehow, and what happens there. So one thing I will say is you notice that in these illustrations, he showed that there are these eyes that are like looking at the double slits that you showed him before, and we'll see again. This is representing an observation, but it's very misleading because it makes it look like that it's like some sort of observer just peering at what's happening. And that's not what an observation is. See, the eyes that you see here make it seem like that you can observe observe the slits without interacting with them, because it's not causally, it's not connected to those slits. It's just like an eye looking at it. But that's not how quantum observation works. You need a detector that physically interacts with the photon as it goes through the slit in some way. So, and that is actually what causes a collapse. It's not like just it's not like it doesn't work in the classical sense that you can watch something without affecting
action at a distance.
Yeah, well, it relates to that concept. But if you think of this classically, you're going to get a misinterpretation, because you can look at things, you can look at water waves passing through slits without affecting them, but you can't watch photons passing through slits without interacting with them. And so the way that you see the eye here is sometimes representing an observer that's just sort of seeing without affecting it. It is misleading. Whenever you observe something, you're affecting the system. It's sort of like
because just for sorry, you go. I was just getting, for an eye to see, light needs to actually hit the retina.
Exactly.
Right?
Well, no, it's first got to bounce off the thing that you're seeing and then hit the retina, and that's actually that's the key part. If you're talking about a single photon, then if you bounce a photon off I mean, that's not how they do it, right? But you can imagine that that's going to affect the system. So it's like if you imagine, if you throw a pebble in a pond, you get the ripples coming out, right? If you throw two pebbles in a pond, the ripples will merge into each other and they'll diffract and there'll be an interference pattern between them. But I can see that just by looking at it. It doesn't really affect the ripples. But imagine if in order to see the ripples, I needed to point a stick into the water to somehow detect the ripples. But that's going to make its own ripples, right? So that's an analogy to what's sort of happening here. To make an observation, you have to affect the system, which changes the system and thereby affects the result. So if you think of it that way, these sort of results are much less surprising. If you think of it as this like disembodied eye that's looking at things, it doesn't make a lot of sense. But that's why I'm saying that this visualization is misleading, although it's helpful in some ways. But just bear that in mind when we're talking about an observer here. It's like a detection apparatus that is interacting with the photon, not some eye that's just looking from the side.
Yeah, no, that is a really important point, because at first when you said, when you put an observer on either slit, it causes this different behavior afterwards. So I was like, well, there's clearly some intentional causation. Is it like that's where my head immediately jumps to. But then when you think about it, it's like, you can't like see a photon like without that photon either hitting your eye or something else hitting that photon and bouncing back. Like you can't just like see a photon in and of itself. Like that just isn't how sight works. That's really so like, of course, to be able to observe it at either of the slits, it's going to have had to interact with something, and then that's a really good.
So I wanted to say at the outset, because these animations, although they're helpful for other aspects, are misleading in this respect, and I think that's part of how IP pushes leads you to the result that he's wanting, because he shows these animations without commenting on the fact that it's sort of making that implication without explicitly stating it.
Right. Well, let's
keep going.
Without the measuring device, when we shoot photons through a double slit, we can't then know which slit they went through or which path they took. So in other words, we cannot know the which path information. Now, for reasons we'll discuss later, because we can't know which slit it went through, the photon acts as a wave and goes through both slits, interfering with itself and creating an interference pattern. But when we add the measuring device at the slit, we can know which slit it goes through. However, because of this, a different pattern emerges. Instead, we get what is called a clump pattern, meaning we know the which path information, because we looked to see which slit it went through. The very act of obtaining knowledge of which slit it goes through means it only goes through one slit, and changes the result in how the electron acts. Now, delayed choice quantum...
So that's all fine, except for the misleading part of the eye that I mentioned. You're muted.
Sorry. If the graphic showed, like I don't know, like the eye shooting another thing out that hits the ball and then comes back, that would be very different. Whereas when it's like that, you sort of develop this belief about intentional magic, like staring at a goat and killing it, sort of.
Yeah, exactly. Which is why I wanted to comment on that, because I'd noticed that it's quite misleading in these. But otherwise, the animation is quite good. It seems that they're actually shooting electrons at the screen, which is just it doesn't matter that much, but just as a detail there.
Well, I think I saw that. I think I was shown that animation in like high school physics, for example, and I think that is exactly the type of thing that led to me developing some like false beliefs about like consciousness causing like the collapse, which because I never like questioned or thought about like what's actually going on there in observation. So
yeah, exactly. But apart from that, I'm broadly happy with how he's described it so far. So we're about to get to the delayed choice part, which is the novel aspect here.
Eraser experiments are pretty much the same type of experiment, except for one big exception. They look to see if our observation is really what is causing the particle to collapse. Perhaps there is something else doing it, and we can trick the system into showing us it. So instead of placing a detector at the slit, two are placed past this, where the particles land. But just before the particles land here, it is pulled away and the two cameras capture the results, after they went through the double slit. If they observe a wave, then the particle went through the double slit as a wave. And just observing or knowing the path information doesn't cause them to collapse to particles. So perhaps one could argue what is causing collapse is something else, like interaction from a physical measuring device. But on the other hand, if they collapse to a state of particles at the moment of detection, then even though they went through the slit unobserved and should produce a wave pattern, the very act of observing instantly transforms them into particles. But not only that, a back history is loaded up so that particles went through the double slit instead of a wave. Well, in 2007, this thought experiment was put to the test, and the results showed that if the film is pulled away, we observe particles. Observation instantly collapses them to particles in one definite position and loads up a back history, so they went through the double slit as particles. Once we have the knowledge of the particle's position, we know the which path information, and this causes a clump pattern instead of an interference pattern. See, observation is about knowledge, a conscious observer having knowledge of the system, and this is what is argued is what causes the particle to have one definite position. The act of observing is the mechanism for collapse. This is better demonstrated from the famous delayed choice quantum eraser experiment from 1999. As you can see,
let's pause here.
But I'm going to break this down.
Okay, so this diagram here is good. The way he just described it is quite confusing. He'll break down this diagram in a pretty good way, with one exception that I'll mention. But just at the outset, he's already sort of mentioned the problem here. Oh, sorry, he's mentioned the point that is problematic, where he said observation is about knowing, and that's just false. Observation is about collapsing the wave function, which means interacting with the quantum system. That's what observation is. We already talked about this before. You can interpret that as relating to, as somehow performed by consciousness if you like, but it's not an established fact. And in fact, it's a minority view that that's what's happening. What observation simply is just some sort of interaction with some environmental aspect that's not part of the quantum system that you're describing at that point itself. So I think this point in itself is the main issue that IP is getting wrong here, to say that observation is about knowledge, because it's not. In fact, if it were, then God should have collapsed all the wave functions, because he presumably knows everything, right? So again, he does address that point later. I don't think his response is very satisfying. But even aside from that, that's just not what observation means. So this is a diagram which I'm assuming he got from Wikipedia, because it's taken from the original paper and put on Wikipedia. But it's a very good diagram. It's a bit confusing to first look at, but he's going to explain it and add some animations to it, which make it reasonably clear. So we'll let him describe what's happening here. But again, basically think of this as a double slit experiment. So that's what's on the left here with the laser and the two slits. And then we're splitting up the light with different prisms and bouncing it with mirrors. And it's going to land on one of these 5 detectors. Well, more than one, but these D0 through D4 are 5 detectors. And the coincidence counter is just like a computer that's measuring these things. And the lines represent different paths of light that are passing through the different paths. So this experiment is set up in a very specific way, with the prisms and the mirrors placed in certain locations to achieve this particular result, so that you can sort of erase the which path information. So IP is now going to explain how that works.
Well, but before we do go through that, so IP he did offer a bit of his interpretation of what's going on, though, in terms of like, I don't know, I'm probably not using the right terminology, like something like backward causation type thing. The problem is, I think that a bit more. Well, yeah, I think the problem is, though, going into this experiment, that could like anchor you into like these false beliefs, similarly to like how the eye, like offering a commentary on the eye and its intentional, like mysterious capacity to interact with the photon can like anchor you to forming these false beliefs and thinking that a certain thing's happening that isn't. Maybe it might be worth sort of explicating exactly what he meant by that, because like I think if I'd missed that detail,
I don't
about
think you
the
can.
photons,
I
okay,
don't think it makes any sense. This idea of loading up a back copy. He talks about that a bit later on. I don't have a clue what he's talking about there.
okay,
That's, I think, his idiosyncratic interpretation, which I
Okay.
think is just wrong. There are some people who are saying that you can interpret this experiment as like retrocausation, backwards in the past. That's a minority view. But even that is, I don't think, the same as what IP is saying about the idea of loading up. I think that's relating to his idea
Yeah,
the universe
loading
is a
up.
simulation, and there's somehow
Right.
like a copy that you can make, because we haven't got to that part yet. We're getting
Yeah.
there. These things relate to each other, but they're distinct. So
Okay.
I think that's where that's coming from. But it's just, yeah, I would call it nonsense. Like, I don't even know what it would mean to talk. But yeah, well, I'll go through that a little more when he goes to that again, because he sort of goes to that again in more detail at the end of the video.
Let's do that then.
On an attempt to simplify what is going on here so we can understand it. I'd also like to thank Ross Rhodes of bottomlayer.com, who is a great commentary on this experiment and was nice enough to reply to my emails and helping me write this. His article about the experiment was actually reviewed by Dr. Kim, who ran the experiment, so it is a pretty trustworthy article. The experiment begins in the top left corner, with the laser firing two entangled photons either through slit A or slit B. Now it is truly random which slit it will fire through, and because we have no measuring device at either slit, we cannot know which slit the laser fires through until they pass through and are detected on the other side. So at each firing, it will either go through A or B. Now the first prism splits the entangled photons and sends them in different directions. The top one goes to detector 0. Now if the photons only hit D0, we don't know the path information, since when the photon arrives, it could have either come from path A or path B. So because we don't know the path information, it should produce an interference pattern if it only came here. If we could place a measuring device at the slit, we would know the path information. But with just a result from D0, we don't know the path information. So because of the lack of knowledge we would have about the system, the particle would act in a way as if it goes through both, becoming the wave of possibilities it could have been, instead of one of these possibilities, if we knew the definite path information. But the other entangled photon goes the other way, and because it is entangled, it will affect the result of its twin that went to D0. Now the other photon from either A or B goes through the prism and hits either BSA or BSB. At both of these, there is a 50-50 chance it will either pass through or bounce off and go to either D4 or D3. Now if the photon hits either one of these detectors, notice what happens. We obtain which path information, because the only way the photon could hit D3 is if it came out of B, and the only way it could hit D4 is if it came out of A. There is no way a photon that came out of B could hit D4, and vice versa. So if a photon hits D3 or D4, we will know the path information it took, and we will get a clump pattern. Now if the photon randomly passes through BSA or BSB, it will either bounce off here or here, and it has a 50-50 chance of passing through BSC or bouncing off of it. So if the photon passes through BSA or BSB, we lose the path information, because if it hits D1 or D2, it could either have come from A or B. We can't ever trace the path information back to A or B. So when they hit D1 or D2, we should get an interference pattern, demonstrating the photon went through both slits, since we don't have definite path information. Now here is one of the important implications of this experiment about what is causing collapse. Some argue physical interaction from the detector is what is causing the collapse, but if that was the case, D1 and D2 should cause collapse every time, but that is not what happens. If a photon makes it to D1 or D2, they always display an interference pattern, yet every time a photon hits D3 or D4, a clump pattern is formed, but the only difference is what we, the observers, know about these two stations. Because of the experiment setup, we know that if a photon hits D3, it will always be a clump pattern, showing the photon only went through one slit. If it hits D1, we know it will always be an interference pattern, showing that the photon acted in a way as if it went through both slits. But the only difference between these two is what we, the conscious observer, knows about the system. Our knowledge of the system causes different results in how the photon will act. If it was all random,
should we pause there or a little bit?
Yes. Okay. So this is the key misstatement here. He says the only difference is what we, the conscious observers, know about the system, and that's just false. I mean, it's trivially easy to show that that's false because you can trace through the different paths of the photons and show that the ones that end up at detectors D1 and D2, which are the ones that will show interference patterns, are different to those that end up at D4 and D3, which will not show interference patterns, because those are the ones that can tell you which slit the light went through. They're different paths, and they're differently related to the slits ultimately where the lights came from. So basically, this represents a different experimental setup. It's sort of like two experimental setups superimposed into one. In one, you can determine. Well, again, I should probably avoid using that language because IP will jump on that. In one, the which path information is, I guess, encoded in the setup or available to the setup, whereas in the other one it isn't. So it's not. The thing is, it makes no difference whether we conscious observers watch this or not. The results are going to be the same. It's about how the experiment is set up.
So could
see the paths are not the same here. See at D3 where there's no D3 and D4. Let's look at D3. There's no interference pattern at D3. It gets the cont pattern. Now, why is that? Well, look, because light only reaches D3 from the blue slit.
Right.
There's no light that gets there from the other slit. So there's nothing to interfere.
Yes.
To get an interference pattern, you need light from both slits. So of course there's not going to be an interference pattern. Whereas at the other one, there is an interference pattern because you do get light from both slits.
Because you get red and blue. Okay.
Yeah. So there's a physical difference between the experimental setup insofar as it relates to those two detectors.
Yeah.
So it's just not correct to say that the only difference is what we, the conscious observers, know. First of all, there's a physical difference that I've just showed. Second of all, it doesn't matter if anyone knows about this or not. It would show the same results.
Yeah.
So it's really nothing to do with that.
Yeah, it's not to do with us knowing that we've set up the experiment in this way.
No, it's purely about how the experiment
our knowledge
is set
of
up.
it. Our knowledge of it causes there to be an interference pattern here and not here. It's that the light physically cannot interfere because there is only okay.
Yeah, and so this goes back to the mistake that IP makes, which is to say that collapse of the wave function or measurement is about knowing or knowledge, whereas that's not true. Collapse of the wave function or measurement is about essentially physical interaction with the environment, related to but not the same as decoherence. Now, again, we don't have a full explanation as to how it happens, like the mechanism of it. That's where the interpretations of quantum mechanics come in. But we know that that's what it is, or what gives rise to it. Well, I guess objective collapse theories are a little bit different there, but they're consistent with the formalism. So he's just wrong about saying that this key statement here, the only difference is what we, the conscious observers, know. It's just hard for me to understand how he can say that when the circles are around detectors that have a different connection to the rest of the experiment through the photon paths. Like, it's just clear that they're not the same.
The conscious observer knows about the system. Our knowledge of the system causes different results in how the photon will act. If it was all random and not caused by our knowledge, we should get some clump patterns at D1 and some interference patterns at D3. But that is not...
Why would we get all interference? Why does he say that?
Sorry, why does he say what?
So he just said if it was just physical,
we should get some photon will act. If it was all random and not caused by our knowledge, we should get some clump patterns at D1 and some interference patterns at D3. But that...
Why would we? Well, he said all random, which I suppose is different from all physical. But I don't understand why he's saying
I don't know either. It doesn't make any sense to me. The interference pattern comes from the fact that there's basically, that there's not an ability to distinguish which slit the photon went through. And so effectively it's going through, you can think of it as going through both slits and interfering with each other. That's the basis of the interference pattern. I just think he's wrong when he says if it was purely physical, we'd expect there to be some of each. That's not right.
Well, he said if it was purely random, which maybe he means something different by that. Like if the outcomes were random, if the outcomes are random, maybe we'd...
Well, remember, the outcome of a single trial is random because you don't know because these half mirrors here, they transmit 50% of the light and reflect 50%. So on any given trial, you don't know which way it's going to go through. In terms of the what you've got, your BSA and B and C. So half the photons are going one way and half are going the other way. So you don't know a single trial which way it's going to go. I mean, that itself is a quantum interaction as well, although it's being presented in this way here as a sort of a macroscopic object. But I guess there must be a way they can do that without collapsing the whole wave function. Again, I don't know that level of detail about the experiment. There would have to be a way that they could do that. But anyway, so I don't really understand why he would say that should be an interference pattern in D3, because when there is witch slit information, that effectively is equivalent to saying that there's been some interaction along the pathway whereby if you want to think of it this way, the photon has been forced to act as a particle going through the slit, and therefore is not going to interfere with itself as it goes through the slits. So therefore, you won't see that interference pattern.
That is not what the experiment shows. We always get a clump pattern at D3 and D4 because whenever a photon hits here, we always know the path information. And we always will get an interference pattern at D1 and D2 because we can never know the actual path information. So the photon acts in a way as if it goes through both. Whereas at D3 and D4, the photon only goes through one slit because we know the path information. The particles act
at D3. So he's saying at D3 and D4, the photon only goes through one slit because we know the information. That just doesn't make sense to me. That just seems to be the way that the physics of the possible trajectories that they take observes.
So the point that what's different about this experiment is that it seems like the witch slit information can be erased by something that happens afterwards, which is not actually D3 or D4, it's D1 and D2. Those are the surprising results, because it seems like, well, whether it went through one or both slits should happen at the slits. It shouldn't sort of happen at D1 or D2. But it turns out, and this is actually the interesting point about this experiment, in my opinion, not the point that IP is making. The important point is that an entangled system is delocalized, which means that you can't just ask what's happening at the slits independently of what's happening at D1 and D2. They are linked together because the system is entangled. It's all one quantum system. When it collapses, that's no longer true. But until that's the case, the system's entangled together. And this gives rise to, or I think this is an instantiation of what's called non-locality in quantum mechanics. And I mentioned this before when I looked at the interpretations. I think the standard view is that quantum mechanics is non-local, but there are some dissenters about that. A standard example of this is if I have an experimental process that produces one spin up electron, one spin down electron, and then they travel in opposite directions, and then I wait a year and measure one of them at my space station or whatever, and I see that it's spin up, I immediately know that the other one must be spin down, even if it's 2 light years in the other direction. And that's instantaneous sort of communication in a sense, but and appears to violate, it violates locality, which is to say that effects like that only occur locally. But it turns out it doesn't violate special relativity because you can't use this to send information. The reason is because you can't control whether it's going to be spin up or spin down on any given case. Nor can you communicate that to the other guy that's measuring the other electron. You'd have to send a signal to them, and that would still take 2 years to get there, right? So you can't use this to send information, so it doesn't violate special relativity, but it does violate something called locality, which some people think just should be a thing because it just seems weird that you can have these non-local, interactions. But I think that's the most straightforward way of understanding what's happening here, although, again, it does depend on your interpretation of the quantum physics. But basically, it's a non-local effect. When the system is entangled, you can't think of the photon as passing through a slit and then doing this and then doing that. The whole thing is sort of one quantum system over the extent of where it's interacting. And then when it's collapsed, the whole quantum system collapses, and then you'll measure the photon at a particular point, on one detector or the other. So that is a non-local effect because you can work out where the photon went through without having to trace it over its path. And that's what seems to give rise to this strange phenomenon where we can erase the which path information after the fact. But I think the better way to think about it is simply that the system is entangled. Sorry, not entangled. It's in a superposition of states prior to you're making a measurement. So prior to collapsing the system, it's in a superposition of different possibilities. The way that collapse occurs determines the results that you get. So if that collapse is made by detector D3, that will get you one set of results. If it's made by detector D1 or D2, that will get you a different set of results, because those detectors interact with the system in a different way. And you can see that with this diagram here. They're not linked to the system in the same way. D3 and D4 cannot get photons from they can only get photons from one slit. So they're effectively interacting with the system in a different way than D1 and D2. But you have to think of the whole thing as a delocalized quantum system prior to collapse, or at least I think that's the most straightforward way to look at it from this point of view. Again, if you have a different interpretation of quantum theory, then you might say something a bit different to what I've just said. But I think that would be something like the standard view.
Well, I think for people who are listening, for people who are listening, they can basically see these at least two competing explanations of what's going on being offered, because we've heard like IP's commentary, which is that our knowledge about the system is what's actually causing these different observations, and then we've heard also your alternative explanation, which is that it's the different way that the experiment is set up. The information, it gets like distributed differently as a result of that, and people can, I suppose, weigh up which of those they sort of find more plausible with their background information about like physics and the way the world works and stuff like those sorts of things.
Yeah, essentially. But I do want to emphasize that so IP is entitled to interpret the experiment how he likes. There is an interpretation that is consistent with what he's saying, but he's wrong to say that the experiment implies his interpretation. That there's a difference between saying that he can use his interpretation to understand it, and the experiment is evidence for his interpretation, because it's not. Precisely because there are other interpretations.
It's equally, it's equally evidence for.
Yeah, exactly. And it doesn't distinguish between them
in a way that correlates to our knowledge. See, what causes collapse is knowledge, and knowledge requires a knower. Sir Rudolph Peirce said, "The moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result." You see, the quantum mechanical descriptions is in terms of knowledge, and knowledge requires somebody who knows. Now, the other implication is even more mind-boggling, because the photon knew beforehand where it would end up. How do we know this? Because of how its twin acts at D0. The twin photon registers at D0 before its entangled twin ends up at a detector, and whatever registers at D0 always correlates to wherever its twin ends up. So if the twin hits D3 or D4, D0 always registers a clump pattern to correlate, and always an interference pattern if its twin lands at D1 or D2. So either the photon has a highly complex computer built into it, so it can know the future, or we have an idealistic picture of reality, and our knowledge.
Okay, let's pause right there. So this particular statement is false. When he says that at D0, which just detects the photons straight from the prism without going through the rest of the apparatus, that always shows what he calls a clump pattern. Well, it's actually different to that. If you look on the Wikipedia page, it shows you what it looks like. Maybe I should actually bring that up.
Me to bring it up? Yeah.
Yeah, you bring it up, because I always get it wrong. And I checked this with a couple of other references as well, and it really just seemed that IP just is wrong about this point. And
delay choice quantum eraser is the one you want, right?
Yeah, and if you scroll down to the experiment of Kim 1999 and look on the diagram on the left, simulated results. Just down on the left there, that one. Oh, yep, there. If you click on that, so these are the different receptors. So or detectors rather. So D0 is the one that he was mentioning there. Note that what it says here is that you never get an interference pattern at D0. And I think the easiest way to understand that is if you look at R1 and R2, see that they're offset by 180 degrees. That occurs as a result of the mirror that's used to reflect the light in different paths. So there's a phase shift there. If you added those onto top of each other, you'd get something like D0 because they're offset. That's what you see at D0, because it sees all of the photons, whereas 1 and 2 only see half of them.
That's cool.
So you never actually see an interference pattern directly at D0. You can infer one by looking at R1 and R2 and then sort of work backwards to see that, well, there would have been an interference, but only if you observe like half the photons. So basically, like there's two interference patterns superimposed on top of each other at d0, but they're offset by half a wavelength essentially. So they you can't actually see them. And that's important because it means that by looking at d0 by itself, you can't actually tell which slit not only which slit the photon went through, but you can't tell if it went through one or both of the slits. So d0 doesn't give you that information because of the way the experiment's set up. Only looking at the R receptors gives you that information.
Yeah.
So this idea that like the photon knows where it's going to go, that's just not true. Like photons don't know anything, but also the description would not, when this system is entangled and in a, sorry, I should say superposition, when it's in a superposition of different possibilities, the system doesn't know how it's going to be collapsed. That's something that happens externally to that system, which then collapses it, like when it interacts with a measurement device, and the system then goes into a single state, which then we can detect. There's no sense in which it sort of knows what's going to happen, and you don't need that to explain these results. It's by interacting with the system and collapsing it in slightly different ways, which detectors 1 and 2 do differently to 3 and 4, that you get the different results at the different detectors. Now, what's interesting is that you have this delocalized effect which shows that basically the photon didn't go through one slit or the other and then interact with the rest of the system. The whole thing is entangled together and is collapsed sort of in one go when it's ultimately detected. And so that gives rise to sort of a non-local effect where it seems that you can have an effect non-locally. So an effect over here something that happens over here in an instantaneous way. That's the general view about sort of what's happening here. Though, again, there are minority views that say something a bit different.
Okay, shall we keep going with this video then?
Yep.
Get through a bit more.
By loading up a back history to correlate with our knowledge. John Wheeler said, "It begins to look as if we ourselves, by a last-minute decision, have an influence on what a photon will do when it has already accomplished most of its doing. We have to say that we ourselves have an undeniable part in shaping what we have always called the past. The past is not really the past until it has been registered. Or put it another way, the past has no meaning or existence unless it exists as a record in the present." An experiment from 2012 took this a step further and brought back in the conscious free will of the observer. To understand this experiment, picture two entangled photons are sent from either station A or station B and separated. The first from each pair is sent to one of two different measuring devices here. Observers Alice and Bob are each stationed here, but do not look at their measuring devices yet. Both of the other entangled photons go to a third measuring device, where Victor is. How Victor chooses to measure the two particles determines what Alice and Bob see their entangled photon as. This happens even if Victor decides, after Alice's and Bob's...
I zoned out for a second on the chat. This isn't an experiment, right? This is him just saying this is like a corollary of his... This is what his hypothesis was.
Yeah, I don't actually know what this little part of the video is for, because he talks about another experiment just after this, which I feel like is the actual point he's getting to. But anyway, so just... But
this is just him describing what he thinks happens. Like Victor chooses...
I think so, yes.
The way reality happens. Yeah, okay.
Devices have measured them, but before Bob and Alice actually view the results. Therefore, a conscious choice affects behavior of previously measured but unobserved particles. Asher Perez, who developed the original thought experiment, says, if we attempt to attribute...
Thought experiment. So yeah, it's just thinking about how that works.
Objective meaning to the quantum state of a single system, curious paradoxes appear. Quantum effects mimic not only instantaneous actions at a distance, but also, as seen here, influence of future actions on past events, even after these events have been irrevocably recorded. John Wheeler's original thought experiment shows the implications of this. He explains by asking us to imagine a distant star that emits a photon billions of years ago and sends it towards Earth. However, on the way it must pass a dense galaxy. Gravitational lensing will make the light bend around the galaxy, so the photon can take one of two paths around the galaxy. Billions of years later, upon reaching Earth, an astronomer chooses to use a screen type of light projector that encompasses both sides of the surrounding space, without focusing on a specific region. Therefore, the photon will land somewhere along the field of focus, without anyone being able to tell which side it took. So it will display an interference pattern, demonstrating it took both. However, The astronomer could choose to measure the incoming photon with a binocular apparatus and focus on the left side of the galaxy, while the other side focuses on the right side. In this second case, how the astronomer chose to measure means the photon could have only taken one path and would display a clump pattern. So in this thought experiment, how we choose to measure now affects how the photon acted billions of years ago. Our choice affects how the particle...
You see, I feel like I mean, I've definitely not got the depth or level of understanding that you have when it's coming to read all this, James. But like with my limited understanding, like that seems like what I'd expect with my model, without thinking that my knowledge is somehow causing what's going on. So I'm not sure why IP concludes from that thought experiment that therefore, he says our choice affects how the particle acted in the past.
I think that's a misdescription, right? So generally it depends on your interpretation of quantum mechanics, okay?
Yeah.
Sort of the standard view would say something like this, as far as I can tell, that...
the Copenhagen interpretation.
Yeah, something like that.
Okay.
What was I saying? Yeah, something like this. So first of all, obviously our choices can affect how quantum behavior manifests, because our choices affect what devices we construct, which interact physically with those quantum systems. So it's not surprising that we can do that. It's just like, again, where you place the ball on the hill affects its speed when it gets to the bottom. Like, that's not surprising. But when it comes to the path of that photon around the galaxies, say, as far as I can tell, if you could set that up correctly, then that would be the results I would expect you to get, because it's just a different variation of the double slit, really. But the thing is that what I think is wrong to say is that we're affecting the path that the photon took over its journey, because that would be to say that there is a defined path for the photon prior to it being collapsed, which is generally, and this is where the interpretations come in, but generally you would deny that from a quantum theory. You would say that there's no defined path, and that it exists as a superposition of different states until you collapse it, or until it is collapsed, at least. And so the way you physically interact with that photon, or the way it physically interacts with something else, can determine how it collapses, and therefore whether you get like the interference or the clump pattern. And that shouldn't be surprising. Collapse is about interaction with the environment. The way in which the quantum system interacts with the environment can affect the way it collapses. I think at a superficial level, that makes perfect sense, right? And so that's really what's happening here. There's no sense in which the photon, like you determined in the past which path the photon would take. It doesn't have a well-defined path, and you can only even sort of say something about that once it's been collapsed. Prior to that, it's in a superposition of possibilities.
So what if you took one of those other interpretations? So like, the ones that were saying it's kind of like our description, but there's no real, what did you have in your table, like ontic wave function or something? Or
that's right. So
there is.
Well, a lot of those would just be agnostic about saying anything beyond what we can say. Like quantum Bayesianism, for example, as I understand it, would just say that it's a descriptive tool to use to make predictions about our observations. I don't think it would say anything about the path of the photon if that's not something that can be observed. Yeah, indeed, that's generally how the Copenhagen interpretation also works. There's actually some people who say that hypothetical experimental results have no outcomes. That is, it doesn't make sense to say what would have happened if it did differently, because that's not an observation or a measurement that actually takes place. And so they just deny that there's any answer to that question. That's one possible interpretation. That would be more of a non-realist interpretation. The more realist ones say there's sort of a fact to the matter, but we'll have a different way to explain it. So like objective collapse theories would say that objective collapse theories, for example, might say that it's actually impossible for that photon to travel so far without collapsing its wave function. Now, I don't actually know, because I don't know the details of like how long that takes, but that would be another possible answer to the question, that actually you just can't have a wave function that remains uncollapsed traveling that far, because there's sort of an intrinsic there's intrinsic effects that will cause it to become collapsed. The hidden variable theory might say that there's some hidden facts about which way around the photon went that we can't know, but are sort of determined under the behind the scenes. So that's really going to depend on your interpretation of quantum theory. But this interpretation that IP is giving, that there's sort of retrocausation in the past caused by conscious observers, is really, I mean, there's actually two things there that are fringe: the observer part and then the retrocausation part. I mean, yeah, you can probably find some physicists who are saying that, but it's, first of all, not, I think it's definitely a very fringe interpretation. And second of all, it's just not incumbent on you to interpret the results that way. It's just how he's choosing to interpret them. The results don't establish that.
Yeah. Right. I think this is just going to end out.
Acted in the past. So the factor of time.
It's actually important to see how he ends out these videos, because that's where
Okay,
he sort of
yeah.
punches with what he wants to take away from them.
That's true. Yeah. Because I guess like, yeah, there's like a sentence of like the core proposition, right? Which is the like controversial sort of thing. And then the rest of the before thing is just kind of loading up to that. So yeah, it is.
The particle acted in the past. So the factor of time has nothing to do with quantum mechanics. And the interesting thing about this is, John Wheeler based this on the mathematics of quantum mechanics. Mathematically, this is what was predicted, and the exact same result is what we see when we put it to experimental test.
Okay. Right.
A little unclear there. So anyway.
Is that the next video, or is it the...
No, I don't want to do that one. The next one is quantum physics debunks materialism. Which, by the way, it doesn't. But so I should say we're sort of building up. I sort of started with the more, I don't even know what the word is to use. We're working up towards his more outlandish claims. Let me put it that way, at least from my point of view. So at the moment, we've basically seen, I think, some incorrect or at least unjustified leaps based on particular experiments to his preferred interpretation of quantum mechanics, which places a causal role for a conscious observer. He hasn't explained how that's supposed to work. Again, we'll get to that. There's a lot of criticism to make of that. But at the very least, he's overreaching what you can infer from these experiments, because basically I don't think these experiments give you a preferred interpretation. They're consistent with really any proper interpretation of quantum mechanics. So that's what we've seen in the previous two. Now we're moving to something a bit more extreme, I think, where he's going to say that quantum physics debunks materialism.
It's how those previously sort of shakily established conclusions are then used to like leverage the rest of the worldview.
Exactly. Plus, he brings in some other stuff as well. So I think there's a little bit of repetition at the start, and then he makes some new claims. So while you're playing the first few minutes of that, I'm going to dash out and grab some food.
Yeah,
so problem. So just go through that, and then I'll be back in a couple of minutes.
Cool.
At the beginning of the 20th century, many physicists believed the completion of physics was near. Only a few minor issues needed to be sorted out, and all of physics would be known. The Newtonian deterministic universe would finally be understood. But this was radically changed when the subatomic world was studied in depth. Max Planck calculated that electrons could only radiate in chunks of energy, or in quanta, instead of gradually losing energy over time. Each quantum or chunk would suddenly radiate from the electrons, seemingly without cause or an impressed force. The discovery of these quantum leaps began the beginning of the strange study of quantum mechanics. How could these quantum jumps just suddenly happen instead of a gradual decline over time, like what we would intuitively expect? Later on, quantum jumps were found in more and more places and in more ways. Matter acted far more bizarrely than we expected. Discoveries and equations formulated to explain the bizarre quantum world began to baffle physicists. The universe did not seem to be fundamentally deterministic at the bottom level, but probabilistic. The mathematics essentially described that particles would exist in a state of a wave function, which is nothing more than a mathematical probability of multiple possible states of where the particle could be. But upon measurement from an observer, the wave function would collapse to one position. But that implied outside observers were necessary to collapse the wave function and bring about the physical existence of the fundamental particles that make up reality, which many scientists philosophically could not accept. How could outside observers be responsible for the actual result and the collapse of the particle, instead of us simply observing nature to see how it behaves on its own? How could the most fundamental particles of nature be dependent on our observations, instead of just acting independently? The famous double-slit experiment reveals how odd the rules of quantum mechanics are. Physicists were interested if particles acted like waves or little balls of matter. Using a single-slit and double-slit experiment, we can determine how they behave. For comparison, when balls are shot through a single slit, they would create a single band on the other side where they land. And when they are shot through a double slit, they would reveal two bands on the other side. However, when a wave goes through a single slit, it would reveal a wave-like pattern with intensity in the middle. And when several waves go through a double slit, they interfere with each other, creating an interference pattern. So shooting particles through a double slit should reveal if they act like waves or particles. In various double slit experiments, particles were fired through a single slit, and the results revealed that particles were acting like waves. The particles go through both slits, and the wave-like properties interfere with each other, causing an interference pattern. However, something strange happened when we tried to shoot one particle at a time. This way, multiple particles with wave-like properties cannot interfere with each other. Even so, when one particle was fired at a time, we still observed an interference pattern. The interesting thing that is happening is each particle is arriving at a specific spot on the back screen, meaning they seem to be acting like little bits of matter, not as waves of energy. However, after several particles are fired individually, an interference pattern starts to emerge. But how could that be if they are going through individually and not interfering with each other? The conclusion was reached. Each particle goes through not as a wave of energy, but as a wave of potentialities. A wave of all the possible paths it could take, interferes with itself, knowing which are the most likely landing spots and which are the least likely, and then collapses to one definite position once it is observed on the back film. In other words, all the possible paths exist simultaneously in a mathematical sense until the particle collapses to one location and it's observed on the back film. So physicists attempted to figure out what was happening at the double slit. They placed a measuring device there, but when they did this, the particles changed how they behaved and acted like tiny balls, revealing a pattern of two bands. The very act of observing at the slit, or having knowledge of the path the particles took, caused them to behave differently. What we chose to measure, whether to check to find out which slit they went through, or check to see which pattern they formed on the back film, determines the way the particles act and behave. Thus, physicists inferred nothing was physically certain until an observer made a measurement. This was the same conclusion we saw with the formulation of the Schrödinger equation. To better explain this, in the quantum enigma, Bruce Rosenblum and Fred Kuttner explain with a simple scenario representing what is actually happening. If we were to take an electron and isolate it in a superposition of two boxes and open one box, the electron would collapse in either one or the other. So if you don't see it in one, it will definitely exist in the other. However, if you were to take another pair of boxes and open them both simultaneously, the electron would come out of both as a spread out wave. It would display the wave of potentialities as an actual spread out wave, like what we saw with the double slit experiment when we do not place a measuring device to observe one slit. The key to understanding what is happening is that matter doesn't exist as a wave of energy prior to observation, but as a wave of mathematical potentialities. The waviness in a region is the probability of finding the object in a particular place. We must be careful. The waviness is not the probability of the object being in a particular place. There is a crucial difference here. The object was not there before you found it there. In other words, prior to measurement, experimental results and the mathematical formalism implies there is no physical particle there. Measurement causes the wave function, the mathematical probability, to collapse and reveal the physical particle, but nothing was physically there prior to measurement. As Heisenberg said, in the experiments about atomic events, we have to do with things and facts, the phenomena that are just as real as any phenomena in daily life. But the atoms and elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. The conception of objective reality of the elementary particles has thus evaporated, not into the cloud of some obscure new reality concept, but into the transparent clarity of a mathematics that represents no longer the behavior of particles, but rather our knowledge of this behavior. Many suggested this may only be the case with really small particles, but later experiments only demonstrated the same results with atoms and even larger clumps of atoms. When Anton Zellinger was asked where the limit was, his reply...
So just pausing it there.
Yep.
Because it seems like he's making a bit of a leap there. You know, when he wants to say, obviously we had the recap of like some of the claims and things that we went over in the other videos, and now he's sort of talking about, I suppose, whether our mathematical descriptions really represent reality or not. But he's also making the claim now about this not just applying to really small things, but applying to some bigger things as well. And I think it was it Carbon 60 or something. I didn't really read what that paper was to see.
Buckyballs.
Oh, is that what they are? Okay. And I don't know. Like it seems to me like the quantum stuff. I agree. Like there's weird stuff going on here that I don't fully understand, and like it'd be great to have more time to learn about. But where's he going with this? Where's he going with the idea that like bigger things, the quantum stuff applies to bigger things? What does he want? How does this get us to God? Or
well, we're sort of working our way there, but basically, he wants to say that sort of everything is quantum, and so everything is like this. So consciousness causes the collapse of the wave function, and sort of nothing is real in some sense. That's what I was saying before. Everything is this potentiality, but there's nothing, no physical object there. And he wants to say, well, actually, everything is like that, not just the quantum world. Okay. And then he's going to lead that into an argument for idealism and consciousness and mind at the basis of reality. But I wanted to make a comment about his claim that there's sort of nothing. I think he said there's no particle there, or there's nothing material there, something like that. Prior to measurement.
The fundamental particles, and the description. I'll go back to that bit.
So the thing is, I think that's misleading. It's true that there's no particle that moves on a classical path in the way that we think about, like a billiard ball moving across the table. So that doesn't exist because it's in a superposition. Yeah, here it is. Nothing was physically there prior to measurement. I think that's wrong. Something was physically there. It just wasn't a classical particle moving like rolling down a hill or something like that. What was there? Well, that depends on your interpretation of quantum mechanics. The Copenhagen would say, well, the wave function was there and then it collapsed. I personally would say the wave function is not a physical thing. It represents a physical thing, which behaves like the wave function, but is like there's a distinction between the formalism and the thing the formalism describes. I think the wave function should be understood as a formalism which describes an underlying thing, but it's not the same thing as that thing. And that is what was there prior to measurement. There's this sort of physical system that behaves sort of like a wave and exists as a superposition prior to measurement. And then when it is measured, it collapses into one sort of classical state, or technically an eigenfunction, an eigenstate of the operator, but that's the formalism part. But of course, people will say different things depending on their interpretation of quantum mechanics. That's just, I prefer a more realist interpretation. But whatever your interpretation is, clearly there's something there prior to measurement. It's just you'll describe it differently depending on your preferred interpretation. I don't think it makes any sense to say nothing was physically there, because then what are you measuring? That doesn't make any sense to me.
Yeah, well, I guess this is where the sort of spooky stuff comes in, because he wants to sort of say, he wants to give mind this primacy, right? So this is how it's debunking materialism, because you have changes in reality which are purely intentional, but with no underlying physical change. So I guess it debunks materialism, because like someone like you who's a reductive naturalist wants to say, well, you can't actually, because all of this higher order stuff is like an abstraction that arises out of more fundamental physical things. Well, you can't have the changes in the higher order stuff without the changes in the lower order stuff that it reduces to, whereas he's trying to say, well, you do actually have that sometimes, I guess. I
don't think he talks specifically about reductionism, but I think that's an idea that he's driving towards. I mean, and the idea here is that I think he's still thinking classically. He's still saying that, like, to be a materialist is to say that classical physics is sort of the fundamental building blocks of reality. And if there's nothing classically there, if there's no classical material thing there, think like an atom in a specific position moving on along a specific trajectory. If there's nothing like that there, then there's nothing material there. But that's just to confuse materialism. I don't even know what the view might be called. Like a classical materialist, like someone who believes that classical Newtonian mechanics is sort of all there is, to, I don't know, anyone who accepts physics developed in the last 100 years since the quantum revolution, which is to say that, well, no, that's not how it works. It's still physical, but it's just operates according to quantum laws at that scale, not classical laws. So it's not incumbent on me as a physicalist or materialist to say that, there has to be like a particle with a specific location following a specific trajectory for there to be something material there. That's just him imposing that, on the materialist.
I'm sorry. Yeah. So this is V put a bunch of squirty cream on top of my coffee with cocoa powder for those asking in the chat, and I breathed it in as I was trying to consume the cream, and it's given me coronavirus.
Yeah, I love the juxtaposition between me trying to explain these complicated ideas of interpretation of quantum mechanics
and just me being goofy.
Nathan choking on his coffee. I guess that's what the stream's all about, really. The juxtaposition.
Yeah, this is definitely a difficulty from flipping between like the physics to the philosophy, and also the sort of vagueness of like, well, naturalism, materialism, reductive material. Like there's like a panoply of views. Is panoply even the right word? Like
I would pronounce it panoply, but maybe you can say panoply. I don't know.
Panoply.
Chat will see.
It's one of those that you only ever. I've only ever seen read. Really, I don't really. I've never really heard it in common parlance, but it's like there's so much to say it debunks materialism. Well, like if all you need is a counterexample of one materialist who like believes in like this quantum stuff and thinks it's reducible to some like material stuff to like say, oh, well, it doesn't debunk it. And those people exist. So I don't really get, I mean, it's like, well, yeah, if we accept idealism and we accept all of IP's worldview, then yeah, it debunks materialism. But that's just like to beg the question, right? It's like, why should someone who doesn't agree with you accept it?
Yes, exactly. So that's the difference between him explaining how he looks at these things and how he interprets them, which he's entitled to do, and saying that these things provide evidence for his worldview. Because I think they only provide evidence for his worldview if they're sort of more likely under his worldview than competing worldviews, or his worldview provides a better explanation. Yeah. Now, he does get to that later on. He hasn't really done that so far. Some of his other videos explicitly try to do that, and I think that it gets worse as he tries to do that. But at this point, he's making, I think, false claims to have shown that his worldview is evidenced, when in fact, just other interpretations will say different things than what he will say. And he hasn't given us reasons for thinking that those other interpretations are wrong.
Right. Well, let's continue then, and
Experiments about it.
Skip ahead a bit.
Possibilities, rather than one of things or facts. The conception of objective reality of the elementary particles has thus evaporated, not into the cloud of some obscure new reality concept, but into the transparent clarity of a mathematics that represents no longer the behavior of particles, but rather our knowledge of this behavior. Many suggested this may only be the case with really small particles, but later experiments only demonstrated the same results with atoms and even larger clumps of atoms. When Anton Zellinger was asked where the limit was, his reply was budget. All of matter is governed by the strange rules of quantum mechanics. Even though decoherence produces the appearance of the classical world, the rules of quantum mechanics would still apply at the fundamental level for all of matter. Decades ago, when this was first discovered, many scientists could not handle the philosophical implications. It just seemed too bizarre to be true. Many physicists like Niels Bohr ignored the philosophical implications and encouraged the practical approach to quantum mechanics. In other words, do not worry about the philosophical problems, just focus on the fact that it works. But some, like Einstein and Schrödinger, were deeply troubled by the results of quantum mechanics. So in 1935, Einstein and two of his colleagues came up with a thought experiment to debunk quantum mechanics. They proposed if you placed two particles in a joint superposition and then separated them with a great distance, an observation of one would instantly affect the other, which Einstein called a spooky action at a distance. The point was that information between the two could not travel faster than the speed of light. So there must be some sort of undiscovered hidden variable that was actually causing the strange results of quantum mechanics, and not observation itself. That matter acted independent of observation and only appeared to be observation dependent from our perspective. However, in the 1960s, John Bell began to explore this thought experiment and proposed an inequality. If this inequality was shown to be false, then the local hidden variable theories would be falsified, and matter would be dependent on observation. This was put to experimental tests in 1982 by Alan Aspect, and the results confirmed Bell's predictions. Bell's inequality was violated. This confirmed what quantum mechanics was telling us. Prior to measurement, objects have no defined properties or location. The act of an observer creates the existence of the physical objects and the properties they entail.
Who deserves to trust their intuition more than Einstein? And Einstein's intuition told him, like everybody's intuition tells them, that things are really there when you're not looking at them. Well, he was wrong, right? That intuition is incorrect.
To avoid
Should we talk about the Bell's thing? Because, again, let me bring it up.
Yeah, IP is mixing a few different aspects here. So he said showed in one of his slides that either, if you jump back a bit, I want to get the exact wording he showed.
This one?
Maybe.
Yeah.
I can't see. Can you? I think it might have been that. No, jump forward a little bit. Yeah, the next one.
If Bell's
I think this
inequality
is
was shown to be false, then the local hidden variable theories would be falsified and matter would be dependent on observation.
Okay, so there are two consequences of this. What's the word? Antecedent here. So if Bell's inequality was violated or shown to be violated, then local hidden variable theories would be falsified. And this is a second consequence, matter would be dependent on observation. Okay, so the first consequence is true. The second is not, at least in my opinion.
You mean true as in a true truly follows from the antecedent? Yeah,
that's right. Yes. So Bell's inequality, I don't want to get into it's actually not that complicated, but it's more than we need to get into now. But the basic point is that if you recall when I talked about interpretations of quantum mechanics and I showed you that spreadsheet, one of the interpretations, which is called the de Broglie-Bohm theory or the hidden variables theory, postulated that there were these underlying variables that determined the collapse of the wave function and which state would that the system would end up being occupied when we make a measurement. So it wasn't actually stochastic, it was determined, and we just didn't have access to what these hidden variables were. Now, Bell's inequality has shown, or Bell's theorem, same thing, that if you want to have a hidden variables theory, it can't be local, meaning that you must have these sort of action at a distance that Einstein didn't really like. I mentioned an example of this before, when you've got the two entangled spin up and spin down particles and you measure one of them and you can sort of see what happens to you can tell what happens to the other one instantaneously. That's an example of this. And I wouldn't be able to explain how it shows this. It's something I want to read more up on, but the violation of Bell's inequality shows that local hidden variables, which only have a local effect, can't are not consistent with with a violation of Bell's inequality shows that you can't have local hidden variable theories, and Bell's inequality has been shown to be violated. So local hidden variable theories are out. All that means is that hidden variable theories must be non-local. And I mentioned this before, that some quantum interpretations are local and some are not. In my opinion, the non-local ones make a lot more sense of some of the results. Like we discussed this in the delayed choice quantum eraser. I think that thinking about the system as sort of delocalized helps to understand what's happening here. But, some people will explain it in a somewhat different way. So some people would say that, well, if you have these non-local dynamics, and that's just really strange, we want to reject any theory that gives rise to that. But I mean, it's just all about what you accept instead of that, right? And personally, I think that that's just the way the world seems to work at this point, that there's these non-local dynamics there. I think in general, most physicists would agree with that. I think that may have mentioned this in the survey. I don't remember specifically. But again, it's not a violation of special relativity because you can't transmit matter or information using these effects. It's just that all the effects are not locally contained. When there's like a collapse of a system, it has sort of an effect of something that's delocalized or potentially a long distance away from where the collapse occurred. And you can understand this as quantum systems being spatially and temporally extended and having and sort of being affected holistically by a collapse event. Again, that's one interpretation of it. I'm not saying you're forced to have that interpretation, but Bell's theorem doesn't force you away from any particular interpretation, other than it says that if you have hidden variables, you must have non-locality. So be it. That then hidden variable theories are now non-local. That's what the theorem has shown. Now, the second consequent here, which was, can you bring that up again? Matter would be dependent on observation. That just doesn't follow at all. I mean, well, either it's trivially true for all quantum mechanics, or it doesn't follow, depending on what you mean by observation. Any quantum system, any interpretation of quantum mechanics has to be consistent with the notion of at least apparent wave function collapse. Not everyone agrees that that's truly happening, but at least it apparently happens when you make a measurement, right? And so in that sense, observation is an intrinsic part of quantum theory. That's the question that was asked. Remember, is it that most physicists said it's part of the formalism, but it doesn't play a fundamental causal role. That's the standard view, right? So, I mean, pretty much everyone agrees that observation is critical to the theory, but most people don't think that it plays a fundamental causal role in the sense of like a conscious observer. And that just doesn't really have anything to do with Bell's inequality, as far as I understand. That's just part of quantum theory. So I just think there's a false dichotomy here, like that it's saying that if local hidden variables are falsified, then matter would be dependent on observation. No, all it does is rule out a specific interpretive option, which would be local hidden variables. So you can't have that. It's not a live option anymore. There are still some people who hold out because there are certain, in fact, I might show you this because this was mentioned in the paper as well.
Okay.
Now, where was it? Did I close this paper? Oh, yeah, here it is. So let me just find the question here, because I'm pretty sure they asked about this, Bell's inequality, because it's sort of also disputed how to interpret this. Yeah, here we go. Okay.
I think, again, though, I think for what he means in this conjunct on the consequent as well, silly logical language that makes everything confusing, I think he's equivocating on observation again, though. He means, again, I mean, from within his interpretation, obviously, he means conscious observation playing a causal role. But I mean, even if we were to kind of like grant him matters dependent on observation, in the sense that he means that, I think that observation here, could just mean like a photoelectric detector or whatever. Like,
exactly, and in that sense, any quantum theory will be consistent with that. If we just bring up the paper again that I've shared there, just to sort of show this, because it's not agreed on exactly how to interpret Bell's inequality. You can see that most physicists think that local realism is untenable, by which they mean basically the hidden variables when they say realism in this context, I think. And again, that's just to say that, well, if you're to be a realist about what's happening, so that the wave function is describing something that's sort of really existing in the world, then you can't, then you must have non-local dynamics. And so B there is people who say action at a distance is actually part of the physical world, which is different to some notion of non-locality. So I'm not sure I would even call that action at a distance, because I don't think it's correct to call it action. I don't think it's really exerting a causal effect. It's more just some notion of non-locality. That's probably what I would. So I would probably agree with C there. Some people say this D here, unperformed measurements have no results. That's the idea that, well, it doesn't make sense to ask, is that other electron spin up or spin down? Because we never performed that measurement. So it has no result. So that's another way you can get around this. But note, there are some people saying there are some loopholes to Bell's inequality, some basically technicalities to the assumptions made. And they've been tightened more and more in recent years, but there's still some loopholes that some people are worried about. So those are the people there who are saying, well, maybe there's a way around it. But most people think that, Bell's inequalities disprove local realism. And there's probably maybe some notion of non-locality in quantum mechanics, but people disagree about that. The idea that this somehow proves that, or what did he say it proves again? That there's, I keep forgetting exactly what he says. That matter would be dependent on observation. Again, if he means that in a sort of a non-physical or conscious type of observation, it says no such thing. It just has nothing to do with that.
Sorry, getting distracted by chat questions as well while you're talking. I need to multi-parallelize my thought processes. Okay, so shall we continue on?
Yeah, so let's move
Or
on.
more you want to say about that part? So where were we?
It's a misinterpretation of what Bell's inequality shows us.
So I think we were here.
Well, he was wrong, right? That intuition is incorrect.
To avoid this, many like John Bell propose the existence of non-local hidden variables and the existence of Leggett's inequality. However, in 2007, they were also falsified, this time by Anton Zellinger and his team. Then in 2013, the last testable loophole was closed, showing there are no classes left of testable hidden variables. The collapse of the wave function and the existence of physical particles clearly must depend on the observer, not on some unknown hidden variables somewhere in nature.
So recent experiments led by the group at the University of Vienna, Austria, provide the most compelling evidence yet that there is no objective reality beyond what we observe. So it's really the observation that creates the reality. What they found is that Leggett's inequality is violated as well as Bell's. Even if you allow for instantaneous influences, quantum measurements do not fit with the idea of an objective reality. So as they say in the magazine, rather than passively observing it, we in fact create reality.
And then on top of this, the Kochen-Specker theorem was experimentally confirmed in 2011. The philosophical implications also support the notion physical reality is not there without an observer, as Anton Zellinger explains.
The Kochen-Specker theorem talks about properties of one system only. So we know that we cannot assume, to put it precisely, we know that it is wrong to assume that the features of a system which we observe in the measurement exist prior to the measurement. Not always, I mean in certain cases. So in a sense, what we perceive as reality now depends on our earlier decision what to measure, which is a very, very deep message about the nature of reality and about our role in the universe. We are not just passive observers.
In other words, the Kochen-Specker theorem confirms the notion of reality is dependent on observation. You can't separate observers from reality, like the idea of watching nature play out on a stage. Our actions now very much determine the results, especially the collapse of the wave function and the existence of particles in their physical form. This only correlates with the conclusions of this study, which shows objectivity, determinism, and independence combined are incompatible with any theory about the universe, and not only with quantum mechanics, but with classical approaches as well. In other words, you can't have a universe that is objective, deterministic, and also independent from observers, as we once thought. All the data has confirmed this through multiple experiments. That reality.
Let's pause there. So I didn't look at that specific paper, the one that he just showed. That's another one that I'll get to in due course. But you have to be very careful when the results of these papers are summarized, because when they use words like objective and objective, deterministic, and I've forgotten the other one. There's often very precise ways in which those are defined in the context of that particular paper.
Independent, sorry.
Yeah, independence. Yeah, I think that one's particularly important there. And they're defined in a very specific way, and you can't just assume that they mean what they might mean in the way that you use them, or they might mean in some other philosophical context. So again, this excuse me. This is I don't know. I haven't looked at this specific paper, but this it seems to me pretty similar to what the Kochen-Specker theorem and the Bell's theorem are showing, that if you're going to have a hidden variables theory, it must be non-local, and that the results of quantum measurements are context dependent, so it depends sort of what you're measuring or how you're measuring it, and you can't always assume that there is a value that exists prior to the measurement. It sort of depends on the context of the measurement. That I think is probably what the independence is getting at. So these are just consequences that have been being drawn out in recent decades of quantum theory. And what IP is trying to do is imply that there's a lot that these results show more than they do, as in that there's like no reality outside of conscious observers, which they don't show. They show specific things about the nature of that reality, which is sort of inconsistent with our naive interpretations of how reality should be, because the quantum mechanics is weird, right? But you really have to press into the details, and we've been talking about some of that so far, and we'll go through more in due course about exactly what the particular results show. And generally, what it boils down to is that the outcomes you get as a result of quantum experiments depend on the way you set up the experiment, or the way the apparatus is constructed might be a better way to say that. There's no intrinsic role that's been shown for conscious observers of any kind. It's about the experimental setup that determines the outcome. And that shouldn't be surprising because it's basically just part of the physical world, right? The way that you interact a quantum system with the physical world affects the results you get. Some of the manifestations of this have been surprising in the particulars, but they do not support, in the way that IP is claiming, the peculiar causal role of conscious observers.
Asking extraordinaire. Yeah. So we were a bit further on from here.
Yes, I think so.
About
it's been
here.
hard to keep track.
Yeah, it is. This is the difficulty with this. I mean, maybe it's a bit of the nature of, you know, like the way we're doing this as well, because we're doing so much in one go. But like I do find this with the videos, like there's so much ground covered so quickly that it's very difficult to like critically assess the claims that are being made, and think about whether they're all like alternatives or whether, you know, this is like the best interpretation of like the data or explanation or whatever. That's like a consistent, but maybe that's like it. You're always going to have that push and pull between doing like 7-hour videos and doing like 10-minute thingies. So maybe that's not so much a criticism of IP, but I guess he could have done a fairer. I mean, like you're clear when you're giving your interpretation here, like this is the interpretation I subscribe to, but there are others available. And I guess IP could have done something like that, right? Rather than saying this is, you know, the objective sort of one ring to rule them all sort of
He's saying he wants to say that these results imply or are evidence for his interpretation, but they're just not. They can be interpreted differently depending on your interpretation, essentially. And he just doesn't acknowledge this point. That's the, I mean, Cam's mentioned in the comments that we haven't really gone through the details of, you know, the Bell's theorem and the Kochen-Specker theorem. And as I said at the outset, we're not going to be covering the details of everything. And I haven't had as much time to go through all of the details of that as I would like to. Hopefully we'll be able to bring some of this more out when I get to chat with Michael about it. But I think the broad point is applicable without having to go through all of the details of that, because what Michael is trying to do from these results is interpret more than they're even trying to claim. On the basis of, I think, fundamentally a misunderstanding of what a measurement is and what an observer is, because this is a key theme of many of his claims.
Let's continue on from here then. Oh, I muted it. Silly. There we go.
Where the measuring devices were separated by several kilometers. All this has led to the conclusion that physical reality is dependent on there being an observer to collapse the wave function. Now, as we said earlier, many have suggested and still attempt to say this is only true of the quantum world, but not the macro world. Pragmatically, this is true, but it doesn't change the fact that everything is built on atoms, the very particles that are dependent on observation. Thus, the fundamental nature of reality is dependent on observation. Second, the reason we do not see the result is because atoms are so tiny that their probability spread is so small we would never notice a change. Also, there are decoherence effects, as we explained in this video. And finally, even with these facts, we still have observed quantum effects with macro objects, if they are isolated from decoherence. In 2009, physicists at the University of California demonstrated quantum entanglement between two aluminum chips, big enough to be seen by the naked eye. In 2010, the largest object ever put in a quantum superposition was a small metal paddle, which was demonstrated to be in motion and motionless at the same time. We've actually seen this numerous times, so you cannot separate the quantum world from the macro world. As Anton Zellinger said, the only limit is budget. Others have opted to save the classical world.
I just want to point on when I comment about that. So I think most of the results he's showing there are fine. I haven't looked into all of them. The result about the paddle that he said is shown in motion and non-in-motion. From a quick look at that, I think that he's not quite describing that quite accurately, but I don't think it's enough of a big deal to get into. Physicists are trying always to show larger and larger systems that have quantum effects. So that frontier has been progressively pushed further. the physicists don't agree as to whether, in principle, any arbitrarily large classical system could exhibit quantum effects like superposition. If you adhere to an objective collapse interpretation, then at some point there would be a limit to how large a system could get before it would collapse, because that's built into the dynamics of that interpretation. So that is potentially falsifiable, and people are working on that. I think I have a preference for that theory because it just seems to sort of make more sense. But so it'll be interesting to see whether we get more data on that in the coming decades. But again, I don't claim to have a particular good justification. It's more just my sort of preferences. But yeah, so the point there is that whether an arbitrarily large object can, in principle, be shown to exhibit quantum effects, like the limit is budget, as that physicist said, that is not established. That's unclear. That's what Schrodinger's cat is supposed to illustrate. This idea that could a cat be in a superposition of two states? I mean, it could be that you could have large objects, but maybe cats aren't the sort of objects that can be placed in a superposition for different reasons, right? So that's still an open question, and it's going to depend on your interpretation of quantum theory. As I said, my leaning would be to say that there's a limit to that, but that's really just a sort of a general, I don't know, predilection. It's not that I could really defend that. So yeah, I just wanted to clarify there that I think IP is kind of overstating it, but the reason there is because he wants to say that this doesn't just apply at the quantum world, it applies to everything in the physical world. Because he wants to draw these idealist conclusions from the results that he's describing. So he doesn't want that to just apply to quantum. He wants that to apply to everything. But I think he's sort of premature in some of the points made there.
We have been joined for a short while by a wild Cam Spears.
Welcome.
Thanks for having me on.
No, is there anything you want to say, Cam?
Oh, I think you are both doing a great job so far. I think especially in emphasizing like the interpretation laden statements that Michael makes, and I mean how it's the case that there are obviously responses that people from other who defend other interpretations would make to many of the things that he says. But no, I think you're doing a good job. But I think the only motivation that I had to join a little bit earlier was about a little historical context of these things that IP is discussing, in particular the Bell's inequalities and the Kochen-Specker theorem. The thing I thought was relevant is that the development of this literature, both these theoretical results and then their subsequent experimental tests, they occurred like within this dialogue about quantum mechanics, about hidden variables theories. And so Bell's original theorem makes certain assumptions that are in line with the hidden variable theories of the day that were being proposed. So, for example, the local realism picture in which there is some particular variable that would be determining what the outcome of a particular measurement will be. And the chaos theorem it's a little bit different, but what it means is that when you see the violations of these inequalities, you have to go back and look at what the ingredients are of what the theorems put in to understand what the real implications are. And James pointed out really well earlier about how it's the case that given that these, one of the ingredients of Bell's theorem is about local realism, that these particular things that are in existence that would determine the outcomes are local things. That means that these non-local views, like Bohmian mechanics, aren't actually ruled out by violations of Bell's inequality. And yeah, that's all I wanted to mention.
Yeah.
Yeah, thanks for adding that. And IP did kind of mention the sort of dialogue between Einstein and some of the others in the early development. But I think that it is important to understand that all of these things have a often quite elaborate historical context. And yeah, we are skipping over kind of that, but we are kind of skipping over some of that. But it is good to bring that out. And I think that is one issue that IP doesn't. It often doesn't give a lot of context, historical or otherwise, for some of the results that he's presenting. And so can take a long time to sort of articulate what he's saying and then why the interpretation he's making of it is an
or
aberration.
maybe he presents like players from history as being the relevant people in the contemporary discussion, with which he would be arguing against if he was actually to, have some kind of debate with them.
Cool.
So let's finish out this one.
Continue on this one.
Critique these in other videos, and have shown they are either not complete or entirely ad hoc in their attempts to get around these implications. So what about Niels Bohr's approach? That the wave function is not real, but is just a mathematical tool which represents our lack of knowledge about the system. This was recently experimentally challenged, though. The results gave strong evidence the wave function is true for reality and actually real, not just an epistemic tool. The true nature of reality is the wave function, and observation causes it to collapse to physical particles. Some also try to suggest...
All right, so that paper there, which he... if you can pause it there. That paper there that he sort of went through very quickly is... let me try to pull that up. So measurements on the reality of the wave function. Yeah, here it is. I want to talk a bit about this because... oh, yeah, sorry, I got confused. Like, I haven't shared screen yet. No, that's his... him pulling it up. Let me show this. Okay, so this is that paper. There's still a lot that I'm digesting here because this is, I'm learning here as well. And this, the extent of the debate is very interesting to learn about here. Where's the, why won't it let me, oh, never mind. What was I saying? Yes, but what does this paper say? So IP says that it shows that the wave function is real. And I mean, I guess a naive reading of the title kind of does indicate that. But again, you have to understand the context of what's being discussed here. So again, I don't really want to go through too much here because it can get very technical very quickly, but let me just say a few things. So basically there is a dispute about how to interpret the wave function. I sort of mentioned this before. And there are some people, as it's saying here, who think that the wave function is sort of a real description of what's happening well, in reality, it's in some sense. And there are people who think that it is just a tool that we use to understand, well, to predict measurements, say, or to describe our own ignorance or something like that. And the language that this paper uses is, I think I'll show it here. So the difference between an ontic model and an epistemic model of the wave function. So an ontic model is one that says it's part of ontology, so it's like real. And then the epistemic model says it's just about like knowledge and predictions. So those are kind of the two key differences. Now, the way that's operationalized in this particular study, or this, because there's others that this relates to as well, this is sort of extending on previous ones, is basically can be described by this diagram here. So if you see the top one, it's sort of hard to explain what this is showing, but let me make a stab that hopefully it's relatively clear. If you think of this lambda here, the horizontal axis, as representing like the underlying hidden variable that describes the system, then, and each of these curves is representing a wave function. So basically what this is showing here is that a different wave function corresponds to a different underlying state of the system, and they don't overlap with each other. That's the ontic case. In this case, the epistemic case, you see that you've got the same underlying states of the system, but the two wave functions that describe those overlap with each other. Now, the best way to understand this, I think, is to look at this middle bit here. You see this, where I've got my cursor here. Imagine that that is like one underlying state of the system, like the way an electron is or something like that. Notice that these two wave functions overlap with each other in describing that same system. And what this means is that two different wave functions could describe the same underlying system. So instead of one underlying system, or like one underlying reality to one wave function, you've got one underlying reality to two different wave functions that describe that same reality. That would be what the epistemic view of the wave function is saying, that it's a tool that we can use, and therefore there's like different wave functions that could describe the same underlying reality. Whereas ontic would say, no, 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 one reality, one wave function, like this first one shows here. Now, the key point here is that, and let me scroll down a bit to establish
just a couple of questions on that, James. So what was mu representing? What was the amplitude of that wave for someone like me who has no idea? Okay.
It's just a probability distribution.
And could you say something to why we would expect to see those two sort of discrete waves versus like the overlap on the epistemic model? Like, I don't understand why you.
It took me a long time to work out this as well. It's because it's the claim that they're making about the way the wave function is. If the wave function is real, then you should have one reality gives rise to one wave function. If like the wave function is, well, as they say, ontic, that is sort of, if it's sort of part of reality in itself. If it's a tool, then you might have different realities that can both be, the same reality might be able to be described by two different wave functions.
Okay.
So there's not just one unique wave function that describes the reality. There's actually two different ones that can describe the same thing.
Okay. Yeah, that's useful. Thank you for.
Now,
sorry for interrupting your.
Yeah, no, that's important. It took me so long to work this out, but it all comes together when you look at this statement right at the end here. Recall that the ontological model framework, that's the model that they're using here, the one that I was just showing you, covers all interpretations of the quantum wave function in which there is an observer-independent objective reality underlying quantum mechanics. Within these realist interpretations, our results conclusively rule out the most compelling phi epistemic models, which means wave function epistemic models. So just skipping ahead a bit, if we hold to an objective reality, our results strongly suggest that we should adopt a wave function ontic interpretation of quantum mechanics, such as Bohmian pilot wave or the many worlds. So those are just examples of interpretations consistent with that. But the key point here is that this whole question already is assuming that quantum mechanics describes an objective reality that's observer independent.
Right.
And that is implicit in this horizontal axis here. Remember I said that you can think of this as like hidden variables that describe the system? But some people deny that that's even a thing. Like if you're a quantum Bayesian, you don't even talk about that. You're just like, no, the wave function just describes our epistemic status with respect to measurements. They would just reject that there's any such thing as this, or at least that we can say anything about it. So this might seem a subtle point, but what they're calling here as it is a subtle point, but what they're calling here is the ontological model framework. It only applies to interpretations in which there is an objective reality underlying quantum mechanics. That there's some sort of like hidden variables or underlying state that determines the quantum measurements. Not all interpretations even agree with that. So the point is that this paper doesn't prove that the wave function is real. It shows that if you assume that there's some underlying reality that quantum mechanics describes in a sort of direct way, then it is, then they argue that their results show evidence that there's a sort of a one-to-one relation between that reality and the wave function used to describe it. So that it's not, the wave function is more than just like a convenient tool. It like directly corresponds to the underlying reality if you assume that there is such a thing.
Right.
I hope that was helpful. It took me ages to sort of work out what the heck that paper was saying. And obviously it's embedded in a deeper literature there. But the point is, because I was like, what? This one paper is like answered that question? Because this is a pretty contentious question. No, it hasn't. It's like answered a subset within that question.
Yeah,
because they're already assuming that ontic interpretation.
Yeah.
Yeah, exactly. And if you want more detail, you can read through that paper and try to get the idea. But they're already assuming an interpretation when even doing that. And I think that comment at the end makes that very clear, although they specify this elsewhere. So that result there is, I mean, see, I don't even necessarily disagree that the wave function is like real. I lean towards that it is, right? That's consistent with the interpretations I prefer. It's just that paper doesn't show, I think, what IP was implying that it shows, which is that it seemed to be showing that you can't be like a quantum Bayesian or believe in the ensemble interpretation or something like that, where the wave function isn't like real. I don't think it shows that because they wouldn't accept the framework that the paper was using to establish that.
Yeah, I can't find a quote on screen of what IP was saying exactly, but
he just basically said that it shows the reality of the wave function, but you have to interpret that in the context of what it was looking at. It feels like he was just sort of Googling around terms like this and found this paper. But it doesn't show really what he thinks it does. It sort of, with certain assumptions, it shows that you can interpret it realistically. But part of those assumptions involve that there's an underlying reality that it is describing, which is part of what's assumed.
Right. Is there anything you want to say on that, Cam?
No, I haven't read the paper, so I think I'd be wading out of my depth there.
Yeah, me in this episode of
Well,
Bad Apologetics.
yeah, I'm as well, but that's why I had to read this paper like 3 times and figure out what the heck it was talking about. But I'm quite confident that IP was not correctly describing the results of it. Anyway, sorry, continue.
Your mention about him maybe Googling, something about the wave function being real and finding a paper and thinking that it suggested something, but he didn't quite understand it. That seems plausible to me. I've seen it in other cases, but I wouldn't know.
Evidence the wave function is true for reality and actually real, not just an epistemic tool. The true nature of reality is the wave function, and observation causes it to collapse to physical particles. Some also try to suggest that interaction and decoherence can adequately explain the collapse of the wave function, but we address this in our video The Measurement Problem and demonstrate this is not true, as interactions create a chain that eventually goes back to an actual observer. This radical implication cannot just be ignored by saying it stopped with the first interaction. The same quantum rules apply to the particles that make up the measuring apparatus. So you need something else to collapse the particles for that apparatus, and so on and so on. The chain keeps going back until you get to something that is not bound by the same rules. And as physicist John Von-Neumann identified, the only logical place to stop this chain is with the one who is ultimately performing the measurement, the conscious observer. These implications show consciousness is not a product of physical interactions in the brain, because if it was, it would also need to be collapsed as well. But the evidence implies the need for something, not bound by the same laws of quantum mechanics, which can cause the ultimate collapse for all of matter. Otherwise, there is no logical explanation for what causes collapse in the existence of matter. So if experiments show an observer is needed...
Just maybe to just pause on that bit, I'm not sure I completely followed the inference he was trying to make to consciousness not being reducible to physical matter. And then I guess in the back of my mind there, I'm always trying to reconcile what he's saying with the idea that God's observing everything as well, which I'm struggling with. Maybe one of you can help me out there if you had...
Well, as I said, he does respond to this. I don't remember in which video, in one of these. I think it might be cosmic consciousness. But he says, but I just think it doesn't work, because earlier, remember, he said, according to him, according to IP, a measurement is knowing. That's what he says.
Right.
And the thing is, God knows all of these outcomes, right? So it seems that he would have to say that God has already made like all of these measurements and has like collapsed all the quantum wave functions. So like, how can we then collapse them if God's already? But what he says is that God doesn't, like, God knows things in a different way to how humans know them, and he doesn't have to like perform experiments or something like that. That doesn't seem to work to my mind, because if he still knows them and observation is knowledge, then it's just knowing them that matters, not like how he knew them. But I mean, he could probably just always say, well, he knows them in a way that doesn't collapse the wave function. Like, I mean, how can I refute that? He could just say that, right? Like,
in a way where his explanation then just becomes a description of the phenomena. So it's ad hoc.
Pretty
it's
much.
Not, yeah, okay.
Because he doesn't have a theory as to how this is supposed to work. He just says, oh, consciousness collapses the wave function. Well, how and why? That's just the way it is, apparently.
Yeah, the detour into theology there is pretty difficult. But Nathan, were you trying to understand this idea of a Von-Neumann chain? This idea about why it is the case that what he's presenting is problematic for reductionists.
Yeah, I think I didn't really understand. He said he put a few sentences together in a kind of argument that concluded with something like, so consciousness can't be reducible to the physical, and I didn't really see how he got there. Yeah,
I think he's trying to say something like these von Neumann chains would go on forever were it not the case there was something of a different type than, stuff made out of quantum fields, for example, or, something describable within the mathematics of quantum mechanics. And, he wants to point to that being, something about consciousness, and that therefore the consciousness would have to be not described entirely by quantum mechanics.
I suppose I'm not understanding.
non-reductionist view. Or sorry, it's an argument against reductionism or materialism.
Why would it have to be a different type? Did he mention? Do you remember, or in your understanding?
I think he's trying to say that the collapse process would go on forever, and it would never.
But it can't go on forever.
Yeah,
So,
but there would never be something objective that it resulted, because it always requires sort of this one more step in the chain. So you need sort of like a final step in the chain that makes the whole collapse of the Von-Neumann chain objective.
Okay, but it doesn't necessarily guarantee that it has to be consciousness either. It's just it has to be something. Yeah,
but I think he wants to sort of link it to consciousness because of the fact that he's made these prior arguments about how it's the case that when we observe things like the double slit experiment, it's this consciousness observing the outcome that causes the collapse.
Yeah.
Now
Okay.
I have a lot of disagreements with him on there. I mean, I think the biggest one to mention is, once again, that different interpretations are going to approach this in a different way. It's not really a problem for Everettians, for example, at least in the way that he seems to imagine. But that's
Well, this is
how much time we want to spend on that.
Well, this is the interesting point, though, because I suppose from the point of view of demonstrating the way that IP isn't sort of fairly representing the domain of discourse here, it's like we've got two people who hold to different interpretations of quantum mechanics here. Yourself and James both have different interpretations of quantum mechanics that account for all the phenomena and don't imply this theism. So it's clearly possible, it's not just like there's this one fringe option, which is like a counterexample to what IP is trying to say, but there's like a plethora of different alternative views that people can go with, which explain all the data points. And
Well, IP himself made this point when he appealed to that survey outcome. And he said, well, the physicists aren't drawing the logical implication of their beliefs because of their biases and presuppositions, basically. And I mean, anyone can make that claim, but you can just say that about anything. Like, you can say IP is drawing his conclusion because of his biases, like
because of his background beliefs. His background
it's
beliefs.
just it's not helpful for the discourse. It doesn't really achieve anything.
To cause collapse, and all of matter is bound by these same rules, then the most logical inference is consciousness is ultimately and philosophically the cause of the collapse of the wave function and the physical existence of matter itself. Quantum mechanics, the very fundamental nature of reality, leads us to the idea consciousness is not physical and is more real than matter itself. The evidence infers there is no escape. We have to face the reality that the physical makeup of space-time is dependent on conscious observers. As Eugene Wigner said, the laws of quantum mechanics cannot be formulated without recourse to the concept of consciousness. Henry Stapp says, the solution hinges not on quantum randomness.
It's like, I don't know. I guess maybe
there is no escape, Nathan. There's no escape.
There's no escape. You just have to concede. There's no option for you.
Maybe I'm being uncharitable here, but it's sort of like, like Berkeley's master argument, where it's like, can you conceive of something which doesn't exist of a mind? Can you conceive of a law of nature without some conscious entity like interpreting semantically the content of that law? Maybe that's not. Maybe he's saying something different. Maybe what Wigner actually means there is you're going to have to account for consciousness in the mathematical descriptions or something like that, as opposed to
the interpretation that he. I was just going to say the same thing. So the interpretation that IP prefers is called the Von-Neumann Wigner interpretation, because they certainly Wigner. I know less about what Von-Neumann said, but definitely Wigner argued for this interpretation and had some odd views about this.
Very views of consciousness being very fundamental to explaining quantum phenomena. I think there's like a difficulty here with IP's presentation. He's attempting to argue that consciousness must be fundamental in our explanation of quantum processes, but he's doing so without. I mean, I guess that this is fair because he doesn't have like a debate partner along with him in the ride of the video. It's a one-sided presentation. But there are all of these difficulties arise when you try to make the claim that consciousness is somehow important in understanding the measurement problem. And the questions are like simple ones like, well, how does it work? And, like, how is it that you describe it? How much consciousness do you need? Are frogs sufficient to do such collapses? Et cetera, et cetera. And you need like a well-formulated theory that explains it, but I just don't really think he's presenting that. It's because it's when you actually attempt to articulate something concrete that you open yourself up to being criticized or it being pointed out. Okay, well, no, that's like actually a very ad hoc or complex explanation you're appealing to here. Now let's look at it in its theoretical virtues in comparison with our other available explanations. How does it weigh up? But there's none of that process going on here. And that is the exact type of process that you need if you want to make any headway in analyzing different views on quantum mechanics. You have to look at their different theoretical virtues and what they commit you to. And I don't think that's occurring. It's like almost being presented as if it's a deductive argument, but it's really not.
Yeah, exactly. And just a few other comments about some of the problems with the consciousness causes collapse view, apart from what consciousness is necessary. But there's also an issue with the localization aspect as well, because if consciousness is non-physical, then, is it spatially localized? I'm not exactly sure what IP would say about that. But because if it is, then it sounds like it's adopting, especially if it's spatially and temporally localized, it's adopting some of the characteristics of something that's physical. But if it's not, then how does it collapse a particular quantum system, but not a different quantum system? What is it exactly that is sort of specifying how that interaction occurs? And also how does it collapse the system? What does it do? There's some sort of physical effect there that a non-physical substance is causing. There's no theory about that. It's not obvious why it would have that property. It just seems to be something that's postulated without any explanation or theory. So I think it's a really bad interpretation of quantum mechanics. And I think there's a reason why it's in the minority. And again, I'm not saying that IP is not entitled to defend his preferred interpretation, but yeah, what we need, as Cam was saying, is comparison of the relative virtues and in issues with different interpretations, and a discussion of what IP's theory is actually trying to say and how it's supposed to work. Not just this idea that somehow you can deduce that it must be consciousness because of these various results that he's showing, where it's really a case of what theory best can explain or account for those results. Not that, it's not. I don't think you can get there deductively because there's just different interpretive options on the table.
Definitely. I think another aspect is that I don't quite see how inserting consciousness is really doing any explanatory work either, because it doesn't give any anticipated experience of which option in a measurement outcome, say, for example, in some superposition under measurement is going to obtain. It's still going to observe the Born rule statistics. And there's no account of why it is that the Born rule statistics will be what you observe on assumption of this consciousness causes collapse theory. And it's just another primitive in the theory, but that was already there to begin with before we appealed to consciousness. So it's a little bit confusing.
Yeah, that's another good point, actually, that I make about this, that the the Born rule, but also any conservation rules as well must be maintained if this is to be a viable interpretation of quantum mechanics. But if consciousness causes collapse, it's not clear why consciousness is constrained by having to collapse the wave function in a certain way that it obeys these conservation rules. Why couldn't consciousness just do whatever it wanted, right? And you can just say, well, that's just the way it is, but it doesn't seem to add any explanatory power to say that consciousness is doing this, but then it's constrained somehow by these other things. The only way that this might work is if the consciousness of God is collapsing all the wave functions, because he's doing it throughout the whole universe, and maybe for some reason I guess you could say that part of his creative power is to collapse the wave function in such a way that it maintains conservation of energy and angular momentum or whatever, although it's still unclear why it would do that. But that doesn't seem to be what IP even wants to argue, because later he says that, well, God doesn't collapse the wave functions, it's actually us as observers who collapse the wave function. even though everything's actually a part of a simulation in God's mind. So, I mean, we haven't got to that part yet, but I just don't see how it all hangs together. It seems very confusing to me. Yeah.
One of the ways to gauge, some potential difficulty in explanation is whether or not it's the case, like you're left with more unresolved puzzles, upon the positing of it. And I find that to be the case whenever you're attempting to appeal to these sorts of explanations. I'm just more puzzled at the end than I was at the start.
Yeah, the interesting thing is I'm seeing some similarities in sort of the reasoning process that's supposed to get us to this point of view, and the one that was used by the near-death experience type people that we were sort of reviewing a couple of weeks ago now, and last week as well, actually, on James's channel as well, when we did a follow-up. And it's sort of like, like here's this thing that sort of, it debunks materialists, it debunks naturalists, whatever. And so, and here's an explanation for it. But then there's no attempt to say like how that explanation is actually supposed to fit in with all of these other background beliefs that we're expected to hold about physics and the way that the world works. And, like you were saying about the conservation of energy, angular momentum and things like that. Like it's just not clear to me that this is the same with the NDEs when you say, well, like how is it that they were able to see from up there in the room, and why is it that they could see? Why have we actually evolved eyes? How does this fit in with my background beliefs about evolution? How does this fit in? Like if it's not spatially located, if it's not a physical thing, why is it spatially located at all? Why isn't it just everywhere? And it's similar with some of this quantum stuff where it's like, well, the consciousness, it's this label that gets invented, sort of like soul, I think, to deal with the phenomena. But then when you start raising these descriptions, you see the explanation becoming more and more ad hoc. Where it's like, well, in things of type A, it has anus, so it causes type A, and then in things of type B, it causes B. So then it just becomes a description of the phenomena, and the underlying explanation hasn't actually helped us to reveal anything about the underlying nature of reality at all. That this is a general pattern that I've seen when people are positing that like consciousness in like NDE experiences with this quantum experiments and things. You're muted, by the way, Cam, if you're trying to talk. Yeah.
No, just a family member.
Okay, shall we continue or anything else?
Yep, let's finish this out.
Yeah.
But rather on the dynamical effects within quantum theory of the intention and attention of the observer. Stephen Barr says, human beings are observers, and perhaps the only observers. This fact clearly has potentially huge implications for the question of whether the human mind is entirely reducible to physics and mathematics. The very fundamental nature of matter implies consciousness is not a product of it, but that the opposite is true. Physical matter is a product of consciousness, thus leading to an idealistic or dualistic approach to reality. The physical universe is a product of mind, and the very fundamental pieces of reality require an observer. The old view of materialism is inadequate in fitting the data. There are simply no hidden variables and no interpretation of quantum mechanics that cannot account for the data without being ad hoc. Reality is dependent on conscious observers. As Nobel Prize winner Eugene Wigner said, while a number of philosophical ideas may be logically consistent with present quantum mechanics, materialism is not.
I find it weird how like we see these graphics to do with like information theory that he wants to bring in at some point in the future as well, like binary symbols on the screen. I like there's so much going on.
Yeah, I think that little in bit sort of brought back the things that I wanted to say at the beginning before I came on, which is that it does for me feel like the thrust of the argument is against a form of materialism you would find few philosophers who call themselves materialists, who understand quantum mechanics or quantum field theory adhere to. Sorry, that wasn't quite grammatically correct, but what I'm trying to say is that, like, if you were to really talk with these philosophers of physics who call themselves materialists, they don't actually hold to the view that he's arguing against in the first place. It's more like, arguing against somebody from the 50s or something like that. But our view is, it's pretty different now. We don't really see the world as being, these atoms and billiard ball style point particles. We have a view based upon an ontology of fields and excitations of those fields, and interference and entanglement and decoherence and stuff like this. It just sort of seems weird to me. He's arguing against somebody who's not really part of the argument anymore.
Yes. Yeah.
Yeah, exactly. And the last minute or so there is just a whole lot of unsubstantiated claims that go well beyond anything that he's really established in his videos. The idea that idealism fits the data better, or that materialism can't be substantiated. He mentioned that there are no hidden variables. I mean, that's not been established either. Hidden variables are, I think, a minority view, but they haven't been ruled out. In the way that he says, only local hidden variables. And yeah, I think he's still basically got materialism as a classical, he thinks of materialism in a classical way, where it's like particles moving with specific locations and positions defined. Yeah, that's just not the view of the world that we really have anymore as physicists, or as, people like me as materialists. Yeah, I think of reality as being constituted by fields. As not having, it seems like there's this idea that common sense intuition is like at the base of the way that the physical world should operate. And if we can't understand how everything should work on the basis of that, then materialism must be thrown out. But
that's right. Yeah, that's what it seems like to me. That's
not what a materialist should hold. It's the way the material world works as described by our best scientific theories that we hold to. And this applies not just at the realm of like quantum mechanics, but other areas as well. Like when we've talked about neuroscience and the mind and other aspects as well, where there's lots of like complex emergent phenomena that don't necessarily cohere with our intuitions all the time, or seem a bit odd. But if they fit with the science as we know it, then they're part of a picture of the material world that someone like me is going to defend. And yeah, in that sense, it seems like IP is responding to really a 19th century notion of what materialism was.
So we've sort of looked so far at how the background beliefs to do with quantum mechanics are being established by IP. And now we're going to move a bit more into his kind of theology as it's being established from some of these beliefs. So we've got the digital physics argument for God's existence, which we're going to take a look at next then.
I just want to say, if people think that it's been pretty kind of crazy and difficult so far, it's going to get more so. We've only scratched the surface so far.
And on that note, I shall go.
Okay.
No, I would love to stay longer, but it's sort of heading on in my time zone. So it's been nice to chat.
Thanks for coming by.
No problem, Cam. Thank you.
And thanks for doing this, because I do think there needs to be more online content that's addressing some of the claims that IP makes. So I appreciate it. It's awesome.
Yeah, no
See you guys. I appreciate that.
I appreciate it.
Cheers. Bye.
James, isn't Cam's in New Zealand, I think? Is he like an hour behind you? He's going to bed.
No, New Zealand's a couple of hours ahead of us.
Oh, ahead. Right, okay.
So I think it might be 10:30 his time.
Right, okay.
8:30 my time.
Right. Well, let's in the spirit of your whole week not being messed up by a late night. Let's.
Yep. Well, still ways to go yet, but yeah, let's get started.
Yeah.
I don't hear a sound. I don't know if this is just. Yeah, I'm not getting sound.
This is the very question many philosophers.
Oh, there we go.
Yeah.
And scientists have been asking lately. Although the question would have been ridiculed decades ago, a different picture is now emerging. The results of experimental and theoretical data have been producing some strange results that do not tell us our world is objectively real, but emerging from something else altogether. And in the rise of the digital age, we are starting to see a correlation between our world and the world of a virtual reality. The very notion that our world is virtual or dreamlike is explored by Brian Whitworth. He took the two possibilities, one being the realist hypothesis that our world is physical, exists in and of itself, and needs nothing outside of it to explain it, and the other being the virtual reality hypothesis, that our world exists as a virtual reality, depending on information processing happening outside of space-time. He looked at all the facts we know from experimental data and asked which hypothesis better fits the data. After looking through it all, the conclusion was obvious. The data better fits the idea we are a virtual reality. Our world makes more sense if we look at it as a virtual world and not an objective one existing independently. He started at the beginning, the Big Bang. This established fact that space-time was created from a single event billion.
Again, like, there's a lot of stuff that's been thrown out already. Like, our world is best interpreted as a virtual world and not one that's existing objectively. I mean, I would say like the computation that is like I'd say the software on this computer like exists objectively, you know, like I wouldn't. So that's a strange thing to be. I wouldn't just, even if the reality was a computation of some sort or a simulation, I wouldn't say it doesn't exist objectively still. But still, it's like a pretty radical claim, and we just like kind of boom, boom, boom. Here's like 5 propositions that are kind of really controversial and like blow apart probably the vast majority of the background beliefs you have about reality that you use to operate and make, you know, like form beliefs on a day-to-day basis.
This paper, which I pulled up, because he appeals to it in other videos as well, it's not just this one, is look, let's have a look. I was going to say, well, we'll leave it, but no, I'm not feeling that generous. This paper is really something else.
Okay.
Just got to make sure because he does mention it specifically and show it a couple of times, so I think it's fair to discuss this.
Just close the other tab, James, with the thing that you don't want to share.
Oh dear. Yeah, too many tabs. Okay, so this guy, Brian Whitworth, he, as far as I can tell, he is sort of like a computer or data scientist or something like that. I don't think he has any formal physics training, as I looked up his CV, you know, which is fine. You can still say some good stuff, but unfortunately he doesn't. This paper is full of nonsense. For some reason, he's sort of taken it upon himself to offer a new interpretation of quantum mechanics, and this paper sort of relates to that. And there's just... I don't even know where to start. So let me go to the end and then we'll backtrack a little bit. So he's got this table here of which I think IP showed briefly, with the different properties relating to a sort of showing how there's a relationship or a correlation, I guess, between physical aspects of the universe that we've observed and aspects of a virtual reality that you'd expect to see if, you know, the universe was a virtual reality, or things that would explain why we see that physical outcome. So I mean, almost all this is just nonsense and misstatements. So maybe we can start with the Big Bang, because IP's mentioning that one. So he's saying here, the universe was created out of nothing by a Big Bang in a single event that also created time and space. That isn't what the Big Bang theory says. He says more about this a bit further back, if I can find it. It's just like a series of misstatements and misrepresentations that it's just... I don't know. It's very frustrating, but also in some way perversely enjoyable to read this paper, because it's just like so much nonsense here. Oh, I can't find the other bit I was looking for. Oh yeah, here it is. So I don't think this guy is a Christian as far as I know, but he's asking similar questions like, you know, what happened before the Big Bang and what caused it and things like that.
Romans 1 again, James. It's Romans 1. more evidence.
Wow. Yeah, maybe. If nothing in our universe is created from nothing, then how can an entire universe come from nothing? I mean, that's just Craig right there. That our entire universe arose from nothing is not just incredible, it is inconceivable. One can state problems simply: what caused it to start, what caused time to start, how can a Big Bang arise when there's no time or space? The Big Bang contradicts any theory that assumes the universe is objectively real and complete in itself. How can an objective reality existing in itself be created out of nothing? So it's basically just saying the Big Bang theory is wrong if you think the real world is real. Oh, look, I didn't even say this. Big Bang is an accepted part of modern physics, but virtual reality theory accommodates... that virtual reality theory accommodates, but objective reality theory does not. So let me say a few things about this. So I think we've talked about this in some of the videos we did, the video we did on the Kalam cosmological argument, because there's some similar misstatements here. The Big Bang theory is not a theory about the origin of the universe. It is a theory about the very early evolution of the universe from a very hot, dense state to, well, ultimately, you know, having galaxies and star formation and things like that, and the expansion rates and other Big Bang nucleosynthesis, so the origin of elements. That's what the Big Bang theory tells us about. It doesn't tell us it doesn't tell us the ultimate cause or where the sort of everything began at, because that would require a quantum theory of gravity, which we don't have, although IP seems to think that we do. We'll get to that. But so these questions are, I mean, they're not entirely irrelevant questions, like what caused it. That's a fair question, but it's not answered by the Big Bang. And the Big Bang theory doesn't need to answer that question because it's not a theory of ultimate origins. And so this notion that time and space suddenly appeared or popped into being is just not what the Big Bang theory says. It doesn't say anything about where time and space originally originated from, because it starts when they already exist, like a fraction of a second after the beginning. I mean,
does he talk, James, about so does he just have, though, if it's a virtual reality of reality, like what caused that reality? Like, does he have an infinite regress of virtual realities?
I don't think Brian talks about that, at least not that I can recall seeing. Yeah, but there is an issue there, which IP does mention. But the thing is that, I mean, if we just scroll back to this, he's going to say, well, it makes sense under a virtual reality hypothesis because virtual worlds must begin with an information influx from nothing. Like you turn on the simulation and then it just starts.
I don't think that's quite right, because it's not nothing, like the electrons that sort of pass through my computer to run a piece of software have to exist somewhere to, you're not creating information out of nothing. I'm not sure if I'd...
Yeah, but the thing is that virtual reality theories don't predict a Big Bang, because you could start the simulation at any point you liked. You could start just completely in the middle with people and cars, and there's no reason to predict that you'd start a simulation at that state at all. Whereas you would expect a physical universe to evolve over time from something. Well, if it's non-finite in the past, if it doesn't go infinitely in the past.
Every time I want to play The Sims, I have to wait 13.8 billion years.
Yeah, exactly. Like, it's just ridiculous. So let me look at some other points. We'll preface about what some of IP is about to talk about, but it's just, this paper is just really something special. Let's look at what else he says. So quantum minima, light is quantized as photons, matter, energy, time, and space may have a minimal quantum amount. So that's true. Light is quantized and fields are quantized as far as you know. So what's he say about this? All events, objects that arise from digital processing must have a minimum amount, or a quanta, because it's digital, like it's zeros and ones, so it's discrete minimum amounts. But I'm asking here, why does it have to be digital processing? That's just how our computers work. But you don't have to have a digital computer.
You can have stuff isn't digital anyway. That's the whole point of making quantum computers, right? Is that they have indeterminacy in the...
No, that's true, but that's a somewhat separate point. It is the case that quantum is discrete, which digital computers are as well, or the states in them are discrete. Like it's a 0 or a 1, but you can't have be halfway in between. Right. Quantum computers work differently to that, but that's not really what this is about.
Yeah, sure. Okay, yeah.
The point is that they're saying that the universe is some sort of virtual reality, but they're assuming that it has to be through digital processing. But that's just one type of, like, computers don't have to be digital. A lot of people seem to not understand this point, that before we had digital computers, we had analog computers. I mean, a slide rule is a simple example of an analog computer. And you can build much more complicated machines of that as well that are analog and function. It's just, that's not the way we've built our computers, because there's advantages to being digital. But when you're making an argument about the universe, you can't just assume that, because it's digital, like it's discrete, then that's evidence that it's a simulation. It's no such thing, because you're just assuming that a simulation would have to be digital in nature.
Well, Babbage's difference engine or whatever is the first computer, or even the Antikythera mechanism or whatever.
Oh, Antikythera mechanism. Yeah, that's an interesting thing as well. I don't know how that worked, but the point is that you look up analog computation if people think this is a bit weird, because that this was how computation was for a long time. And there's no reason why you couldn't perform these computations with an analog device. It's just not how we do it. Let's keep going. It gets sillier. The speed of light is a fixed maximum for our universe, and nothing in space-time can move faster. What's the explanation for this? There's a maximum processing rate, so events in a simulation would have a fixed rate that's a maximum rate that's limited by the speed of the process.
Yeah, but that, again, that's not analogous, because it's not like my, assuming for whatever reason this Von-Neumann architecture computer and not something else. I mean, a processor's speed is changing all the time based on like the temperature, the clock rate. Like there's loads of things that are like fluctuating to change. So you'd expect then the speed of light to be changing as the processor speed changes, not to be.
Well, no, actually, because if you're in the simulation, you can't detect that, right? The time between one frame and the next frame is 0 frames. So you don't have any reference to compare yourself to. Maybe you could argue that there's different processes and some may be sped up more than the others, but I don't know what that would mean, because it would be like, I don't know, different aspects of the universe.
Yeah.
That doesn't really make sense. So if you were just in the simulation, like if you're a character in The Sims, right, and your computer's dropping frames and you're like going to 10 frames per second, we can observe that, but the sim, if they could somehow experience it, wouldn't notice that, because it would just be one frame in the next frame for them. So it doesn't make sense as an explanation. But also it doesn't make sense because the speed of light is the rate at which objects and information can move through the universe, which we'll say maybe is through the simulation. But if I'm running a simulation, I can just delete an object from like this location and instantiate it in a different location. There's no reason it has to move through the intervening space in the simulation. Like, you know, I can just delete an object in one house in The Sims and then put it in a different location, because the simulation could just do that, right? I'm not limited by having to move through the simulated space, because I could just plop something wherever I feel like it. So this idea that processing speed would somehow explain the finite speed of light makes no sense at all, because why would you not just be able to teleport something to the other side of the universe by instantiating it in the simulation? It makes no sense at all. And this discussion that I've highlighted here is just completely confused. He says that why must there be a maximum speed at all? If light is like a classical wave, its speed should depend on the elasticity and inertia of the medium it travels through. If light travels through empty space, its speed should depend on the elasticity and inertia of empty space. However, how can empty space have these properties? This guy just doesn't understand basic electromagnetism, because we have answers to these questions. I think he answers his own question here. If light is like a classical wave, its speed should depend on the elasticity and inertia of the medium it travels through. But it's not like a classical wave. I mean, I suppose it's like it in some ways, but it's not a classical wave. It's quantum, essentially. And we know that you don't have to have a medium through light to travel through. The medium, if you want to think of it that way, are electromagnetic fields, which oscillate and give rise to a self-perpetuating, propagating wave packet that we call a photon that travels through space, right? You don't need a physical medium for that to travel through. And the properties of the quantum fields that give rise to photons, I think it's the permittivity and permeability of the vacuum, they're called. Right. Those you can actually derive the speed of light from Maxwell's equations, and show that you can calculate in terms of those underlying parameters. The speed of light is not actually a fundamental constant, as we talked about in the fine-tuning video. So the point is that this is not even that advanced physics. It's like, I did this in second year, I think, where
I remember the permeativity and permeability.
Yeah. The speed of light emerges from properties of how those fields interact with each other. We now understand them at a quantum level, but you don't need empty space to have any properties. It's the quantum fields that have those properties, and they can be instantiated everywhere, sort of, as far as we know. So this just seems to have a complete misunderstanding of what physics is even classical physics really is saying about the nature of light. And we don't need, there's no like question about, why does our universe have this speed? Well, you can derive where the speed comes from. It comes from basic properties of the universe. Now, you could ask where those come from, but you could say that about anything. There's nothing peculiar about the speed of light. In fact, if you think relativistically, why is the speed of light the maximum speed? It's actually interesting, because Einstein was thinking about this, and his idea was that, well, he postulated that the laws of physics are the same in every reference frame. So like, regardless of how fast you're moving, essentially. Okay. And one of the laws of physics are, some of the laws of physics are the laws of electromagnetism. And from those laws, you can derive the speed of light. So if you think that all of the laws of physics, including electromagnetism, have to operate the same way in every reference frame, then it follows the speed of light must be the same in every reference frame. Right. So it's just taking a different thing as fundamental. It's taking the laws of physics as fundamental and being consistent everywhere, rather than our notions of how like transformations of velocity should work. So I did a recent podcast on special relativity, if anyone's interested in my podcast, The Science of Everything. So that's sort of why this is in my mind. But the point is that if you think about this enough, there's a logic to why the speed of light is sort of a maximum speed. It's not as mysterious as like the universe just arbitrarily decided that you couldn't go faster than this. So it's like he's trying to explain a problem that doesn't even exist based on a clear misunderstanding. And I make a point about this because IP specifically mentions this. He brings it up in the video. And it just seems to indicate to me a very clear lack of understanding as to what's even going on in the physics, as if we're trying to explain something that doesn't even need explaining. And oh geez, I think there's all sorts of other stuff in this paper as well. Like we can explain wave function collapse by the fact that a computer processor is equidistant to all the pixels on the screen, which it's not even strictly speaking true, because there is propagation delay, but it's not going to be very large for a screen. But also, non-local effects are, as I said, what you'd expect if it's a simulation, because you don't need information to propagate across the simulation, or at least it wouldn't necessarily have to be that way if you didn't program it that way. So, it could be local, it could be non-local. I'm not sure that it really explains anything. And
this is like what we said. What I said before. Yeah, the processing load effects there. Well, that you just said in that point. Well, from within the simulation, you wouldn't actually perceive any difference, right? Because even if in actual reality the computation was running slower, from within the computation it would only be each clock that you'd notice any changes. So from within the simulation, you wouldn't expect to see matter and speed effects, space curves near a massive body. Like, why would you expect that from a processing load effect? It just performed the same, but in actual reality, it'd be slower if you. And
this idea that the amount of matter in a simulation slows down the processor is particularly bizarre, because, like, wouldn't the amount of mass be just a property that you could define with a variable? Like, why would it slow down the processor? It seems to me that the number of interactions would slow down the processor, not the amount of mass. He talks about that.
Yeah.
Why does he talk about that?
Well, maybe it would
be up here.
Maybe it would increase.
Yeah, here it is.
The number of data points going through an algorithm or something, and so you'd get into.
Mass wouldn't necessarily do that, because there are different fundamental particles that have different masses, and so they curve space differently. But one doesn't have more properties than the other; they just has more mass. It's not like so you could store the properties of a particle as as variables in your simulation, right? And mass would be one of those. It's like a fundamental property of a particle, as far as we know. So why would that take up more processor speed to process one number than a different number? Like, it doesn't make any sense.
Yeah.
It would take more speed to process different interactions, but that's not the same thing as mass.
Well, suppose he's assuming the way that this piece of software is designed in that, because I could see one way of designing it where you'd have to iterate over every atom or something and calculate the mass at each one. But if you could also just have an integer that describes the mass or something. Why am I getting so involved in this anyway? But
even if you did it that way, it still wouldn't explain why mass itself slowed down the processor. Because some particles have more mass than others. But why is it the mass property that's slowing down the processor and not just the number of calculations, which is just a completely different thing? Yeah. So the point here is, and IP will go through some of these as well, but just none of this makes any sense at all. It's completely absurd. Unlike some of the other papers, which are legitimate physics papers and discussing interesting points. I'll stop that. That paper is complete nonsense and makes an amusing read, but he should just not appeal to that paper at all.
Yeah, it's interesting, but it isn't. Yeah. Well, no, I mean, I think it's even fun to entertain those sorts of ideas, but
it's a fun idea,
used, in the way it's being used, to be here's how reality is and here's how we can know why. That is not a good example of how to go about that process of figuring out the fundamental way reality is. That's the equivalent of reading Narnia and being here's the way reality is. I suppose it's a bit better than Narnia because it has a table that says that at least corresponds the theological world to the real one. But yeah,
I guess this is like a fan fiction of reality. Maybe would be a way that I would describe it. It's a fun fan fiction. So let's hear IP. He actually does say these, though. It's not me making this up. So let's hear him.
Billions of years ago. Although hypotheticals have been proposed to get around this beginning point, the fact remains, our universe, space-time, began to exist. From the view that our universe is all there is, as an objective independent reality, this makes no sense. How does space-time emerge from nothing? But if we look at the universe as a virtual reality, the Big Bang fits perfectly. Virtual worlds must begin with information influx from nothing. Brian Whitworth says, virtual reality theory fits well with the Big Bang. No virtual reality can have existed forever, since it needs a processor to start up. Every time one starts a computer game or boots up a computer, such a big bang occurs. From the perspective of the virtual world itself, the creation is always from nothing, as before the virtual world startup, there was indeed no time or space as defined by that world.
I want to comment on the presentation here though as well, because it's like so it's interesting having gone through the paper just then. We're seeing not just here with the text, but when IP's describing the way that the universe must be, with the cool graphics of like zooming through the universe and stuff like that. He's actually quoting like verbatim, like those 6 or 7 points or whatever, that the paper says, here's how you'd expect if it was virtual, whatever, and then, that's what we find. Which is interesting because that's all post-diction anyway. It's not actually prediction. Like, you'd have to make some novel testable prediction, and then we'd be, that's cool, we found it. Instead, what he's actually doing is he's saying, here's all the data points, post-dicting an explanation, and it's a more ontologically liberal explanation because it has all this extra stuff than just like necessitarian.
Yeah, but the explanation doesn't even make any sense. I mean, it's not true that you big bang it every time. Like, that doesn't happen when I play my games, for example, or when I open Microsoft Word. There's not a big bang that it just starts of where it's programmed to. It could be it could start anywhere. Why would you expect that it has to start in a hot dense state and then expand outwards? I don't understand that at all.
Even thinking about like old computers where the memory used to be, there was like these coils and wires that passed over, and this is how RAM used to work. And so the magnetism would actually store in memory like the state of the machine when you powered it down, based off the magnetism, and like that. There's no way of like making the analogy. Well, maybe there is a way, really, really weakly, but if that isn't analogous in any way to like the Big Bang, and then you think about the way like a modern computer starts up, it just isn't analogous. But in terms of the presentation, so it's like there's this guy's like a picture from like an academic profile and his name. And I think for someone who's not thinking critically, you're just going to assume that he is a relevant authority on this. And because there's like a paper here, I think that you're just going to assume that it must be good because it's a paper. I mean, maybe not everyone is as gullible as me, but that's certainly the type of thing that my brain wants to do.
It gives weight to it.
This way.
Yeah.
And
I think it would be more correct to say some guy on the internet says, because this guy has I looked at his CV. He doesn't have an undergrad even in physics. Now, again, that doesn't mean that he's going to be wrong, but it shows in the paper because there's just these like simple points that it just doesn't seem to get.
He's not a relevant authority to be talking about this specific domain.
And even relative authorities, of course, can be wrong. But when this is what he's appealing to, it's just...
it's wrong on all accounts. Like so the point, the point could be true independently of his authority not being relevant, but the points are wrong, and we've addressed why. But then it's also being presented as if he is a relevant authority, and that lends credence to the claims he's making. But he also isn't a relevant authority, so the points are wrong, and he isn't a relevant authority. And this is like maybe not. I think it shows us the way that IP is coming to this, though, where you're saying before, like it's plausible he just kind of like Google scholared like key terms and found things. It's plausible, and then it's like, well, here, like I found 1111, I found all the hits, and then I'm just going to present them in like a slideshow, and that's I think that's what this kind of looks like, because right. Well, anything else you want to say on that one? And then...
No, let's keep going. It gets more fun.
Another thing to look at is quantum minima. The fact that things like light are quantized as photons better fits the hypothesis that we are a virtual reality. In digital processing, all events and objects must have a minimal quantity that cannot be reduced anymore, and yet our world has the same effect.
Man, IP's never heard of null pointer exceptions.
Yeah, and why does it have to be digital processing? Like, I mean, let's suppose that that IP is correct. Couldn't God have a simulation in his mind that is not digital in nature? Like, that doesn't have a minimum quantity? Like, wouldn't that be just as possible? I don't see why that is ruled out. So, but if that's the case, then you can't say it explains why the world is quantum, because God could have just simulated it in a non-quantum way. Like, it doesn't explain anything.
I just am not sure that this even really makes sense in digital process. Like, what does he mean? Maybe he means in like discrete mathematics. Something. I don't. Yeah, I'm not really.
I think that's what he's saying.
Yeah.
Again, no, I mean, it's not even exactly true that so when you represent a number in in a digital computer, you can't represent a real number in a digital computer. You always have to approximate it, because an arbitrary real number has an infinite decimal expansion, but you can't represent that in a finite digital system. So you have to approximate it. But the thing is that if you can always allocate more memory and represent the number with greater precision. So it's sort of true that there's a minimal quantity in the sense that it's zeros and ones and that it's discrete, but I don't think it's not true that there's an arbitrary level of precision. Like, once I get to subatomic particles, I can't cut the particles up anymore. So there's a minimum unit there. But that's not really true in a computer. I can always simulate finer and finer detail if I want to. I just need to allocate more memory so that I can represent the numbers like larger or smaller, if you think of it that way. So it depends how you interpret what he's saying here, but I'm not even sure it holds for digital computers.
Well, I don't really know what he is saying. Like, it's like, well, so objects must have a minimal quantity. It's like, okay, so, we've got a 32-bit integer, say, so it's going to be minus 255, whatever. Well, depending on whether it's like signed or unsigned or whatever. Like, but okay, there must be a minimum because we're expressing it. But it's like you said, you can just make it 64-bit integers now. Okay, make it 128-bit, and then we've got even less. It just depends on. There doesn't. I mean, I suppose maybe he's right then in a sense, because so it's like in an actualized. It's like potentially. It's like the potential infinity thing. Potentially, you could keep expanding the machine and make it bigger. But when you actualize it, it must. But then again, that's like, well, within our universe, like, how do I know about like the actual the computer that's running this simulation in the actual reality is even anything like?
That's the point I made.
Yeah. Right.
But that's also different to our universe, because as far as we know, I can't keep cutting up fundamental particles. I reach a limit there. I mean, maybe strings are a thing, but at some point we think there's a limit to how small things can be broken up into. But that's not the case for a digital simulation. You could write a subroutine in the simulation which always just, if you were like zoomed in or something like that, you can imagine like scrolling in on your Sims or something, that it just always allocated more memory to representing it in finer and finer detail. I mean, I suppose, you'd want to avoid memory overflow, but like, in principle, you could do that. There wouldn't be a principal limit to how far you could zoom into the simulation. If you just allocated more memory to a smaller like region of the simulation, if you see what I'm saying.
Yeah.
Just like support, how just an analogy occurs to me. You know how an SVG image works? That's just defined in terms of curves. It's defined geometrically in terms of the curves and connections between them, rather than in terms of pixels. So you can zoom arbitrarily far into an SVG image and not lose, and it won't pixelate. So that's an example of that, right? There's no, although it's described in a digital computer, there's no minimal quantity. You can zoom infinitely far into such an image. So that's just an example of that occurred to me. Yeah,
that's true. So to qualify, like, it's not David who's asking in the chat. Does he mean like? Well, it's not exactly clear what he's meaning. He could be meaning a few things. So in terms of like, I suppose like how I understand computers, there's going to be a point where the rubber hits the road, so to speak, and you have to like define things. So there's potentially a lot of ways you could define things. But like, let's say you're going to have like a computation running. Well, like an integer is going to be represented by 32 bits, and there's only so many possible numbers that can be expressed by 32 bits. Now you could potentially, like it's possible then for you to make a computer that has 64-bit integers, which is then going to mean that there's like larger numbers that you can express using 64 bits than you can with 32 possible combinations. But in actuality, maybe he means there's going to be a minimum quantity, but then that might be one way of interpreting what he's saying, but I don't think I'm even sure that that's what he means. I don't know.
I think it's very unclear, and it's not really relevant in any case, because it's not clear why should it be digital processing anyway. So I think we've given it more time than it probably needs.
More time than it needs, right?
Every computer-generated image, no matter how realistic, breaks down into pixels when you get close enough. You might think this doesn't...
Well, again, like you just said, It's like, well, that's like, so if I were to like physically zoom in on my screen, it goes.
Yeah, he's talking about the way the image is displayed, but not necessarily the way the image is represented in the computer. Which the latter is more relevant, right? Because that's the simulation.
Yes,
your
exactly.
screen is actually just an interface between you and that simulation. So, I mean, I think that this is being used in an analogous way as to just understand what like discreteness means. Pixels are an example of that. But I think IP is pushing it further and saying like reality is like that, and a simulation would be like that. So therefore, they're like related. But a simulation doesn't have to be like that at all.
Happen in the real world, but you'd be wrong. In the past century, physicists have discovered that matter really is made of tiny little pixels, fundamental, indivisible particles billions of times smaller than an atom.
Look at the way the universe behaves. It's quantized. It's made of pixels. And it's made of individual atoms. Space is quantized. Time is quantized. Energy is quantized. Everything is made of individual pixels, which means the universe has a finite number of components, which means it has a finite number of states, which means it's computable.
And that the true nature of the universe is indeed digital, that we have smallest space, smallest time, and that there's nothing that you cannot compute. And at the moment, there is no evidence against that.
What about the fact that there is a maximum speed?
Let me just comment on that because he's moving on to a different point now. So whether the universe, so this is actually, there's a field called digital physics where it's the idea that like the laws of physics are all computable. I don't exactly know what they do with that idea, but it's a thing, and it's a bit different to what
Well, I think
how
Stephen
IP uses the term.
Wolfram's been doing something weird.
Yeah,
with it,
yeah.
which is
That's a good example of that. Yeah, exactly.
very different, but that's very different to this.
Yes, it's not really related except by very vague analogy. But the point is, to my knowledge, it's not established that that everything's computable. As far as we know, the laws of physics are all computable, but we don't know if space and time are quantized. I mean, people suspect that they are because we're looking for a quantum theory of gravity, right? But I don't think it's fair to say that that's established because we don't have a quantum theory of gravity yet. Also, if the universe turns out to be infinite, then it's not going to be computable because you have to. Yeah. Well, it may not be computable. I suppose it's possible that it still could be, but it wouldn't necessarily be computable. It's only necessarily computable if there's a finite number of combinations and you can process all of them. Essentially, if the universe turned out to be infinite, then there wouldn't be a finite, and so it wouldn't necessarily be computable. Yeah. So someone points out in the chat saying there's no evidence against it, which is, I think, probably true, isn't the same saying there's evidence for it. So I think at the moment it's an open question whether like the universe is computable. I mean, the thing is, though, that in some sense it's pretty hard to prove, right? Because suppose we found the universe was infinite. Well, you can never explore an infinite universe. So it could just be an illusion of an infinite universe, whereas only a finite amount is actually computed. So I don't even know how you could falsify this, or at least seems to be quite difficult.
Or it could be a scalable vector graphic, right? You just keep going out there, and there's more and more
exactly,
and more universe. Yeah.
Exactly. So it could seem infinite, but not actually be. So I just think it's this stuff is not evidence for anything IP wants to defend. Really, it's just people have speculated that maybe the universe is computable. Even if it is computable, that doesn't mean it is actually being computed, like on a simulation. That's a totally different point as well. And yeah, someone else points out having Morgan Freeman narrate this seems to maybe give a bit more weight that it should to the ideas being expressed.
Well, it's just, I don't know, maybe there's a lot of stuff going on. Like there's the general phenomena, right, where people do keep talking about the idea of the universe as a computation, and like, why is that happening? My guess, because computers have sort of changed the way that the world works, and so people want to use analogies that make sense of them to try and understand and represent the world. Similarly to, I suppose, when you look at like biblical authors and how they understand the world and the types of things that they use to represent it, which are going to be very different to, like they're very alien to us when we go and read the biblical text. So that's one thing. Like, why are people even doing this in the first place? And I don't, it's one of those things again, where it's like, once you've kind of like got this belief in there, I don't see what could ever count against it, because like what you were saying before about Oh, what was it you said? Oh, yeah, the universe being computable doesn't necessarily mean that it is being computed or that it is a computation.
Yeah, exactly.
It's like I was thinking in my head. Well, I give the analogy of like, you know, like the information about like a rock or something or a rock falling is like computable, but that doesn't mean it's being computed. But then they, you know, obviously the person will go, well, it is being computed because reality is being computed, and it has, and like, it's like it doesn't. It's not like there's no like thing I can point to and go, well, here's a case of something that's computable and not being computed, because they just think everything is being computed. So it's impossible to like falsify in that sense.
This point is actually quite subtle about the nature of computation and its instantiation, and comes up in computational theory of mind, which is something that's interesting to me. So I think it's John Searle who's pointed out that to say that the mind performs computations or is like computational is potentially a bit vacuous, because computation is really just an abstract relationship between inputs and outputs that can be specified by certain rules, but there's no real limit when they have to be finite. But that apart from that, there are very few limits on the nature of those rules, so they can be like arbitrary and ad hoc. So he points the example of, you know, a bunch of molecules on the wall is computing some elaborate function of, you know, the inputs and outputs of that physical state. But we don't normally talk about it that way because we don't know the rules and it's not helpful. It does not. So I tend to agree with that and think about computation as a formalism we apply or don't apply to systems, and not really a fact of the matter about the system themselves, because it's a very flexible framework that just is about relating inputs and outputs through a series of finite rules. But those rules can be arbitrarily complicated as long as they're finite. So it can apply to almost anything, not quite anything, but it's pretty abstract in terms of what it can relate to.
Mm. Well, it's almost like if you
go ahead.
say it can be, it's almost like saying it can be described in language, because I suppose like a computation is just basically a series of well, like you said, there's that caveat that it has to be finite, I suppose. But it's just a series of functions, basically.
Yeah.
And so as long as you're able to describe some phenomena, basically it's potentially, you know, like potentially computable in some sense of the word. And so it's like, it's similar to just saying like, well, it's describable, like, but what does that really tell you about it? Like, it doesn't.
In itself, not a lot. And that's sort of the point I think that John Searle was making, and I tend to agree with. You need more substance about the nature of the computation or how it is relating to the system to, I think, make that very meaningful. So if someone says the universe is computable, to me, that doesn't say a whole lot. I mean, I think it doesn't necessarily imply that it's finite, because you can compute some infinite things, right? But it places some restrictions on it, but it's not that much.
Yeah. Well, we shall continue.
Must have a maximum rate limited by a finite processor, and our world has a maximum speed. Einstein deduced that nothing travels faster than light from the way the world works, but this does not explain why the world had to be that way. Why cannot an object's speed simply keep increasing? If light is like a classical wave, its speed should depend upon the elasticity and inertia of the medium it travels through. If light travels through the medium of empty space, its speed should depend upon the elasticity and inertia of space. However, how can empty space have properties? Virtual.
I thought this was an interesting comment, actually. My guess would be that putting computers at the center of your theology gives a sort of scientific veneer to intentionality being fundamental. Yeah, it might be that then, because the what's the word that like English people use, like the lexical field or something. I don't know. It means like the set of language and what the language kind of connotes and stuff. In people's minds, like the connotations are going to be like smart people, technological people who have a firm grasp on reality. So it might have that like psychological effect of like giving it some sort of like credence that it kind of shouldn't have, because, you know, like I see a lot of people, actually I see a lot of like scam artists doing this, where, you know, with like Ponzi schemes and things, but like they, you know, like when they talk about it being to do with like you know, cryptocurrency and computers and whatnot, it begins to like legitimize it in some people's minds, unfortunately, because it's like, oh, well, this person obviously knows what they're talking about because they sound like some genius physicist who's like figured it all out.
It's not a pyramid scheme. It's a cryptocurrency investment opportunity.
Yeah, it's an IPO. It's an ICO, initial coin offering.
Yeah, exactly. Yeah, I've already talked about this point. It's just a complete misunderstanding of well, classical and modern physics, really. Yeah, but we can move on from that.
But objective reality cannot. There is also how space curving of massive objects and time dilating at high speeds correlates to virtual processing load effects. High matter concentrations.
It's just interesting how this like correlates to every point that was like in the, either in that table or in like the 6-point.
Yeah, because this is where he's getting this from. It's from this paper. That's why I talked about it at some length, because it's not just like he referenced it and then moved on. He goes on and on about this.
Yeah, it's just
and
every
all
point.
of these points are ridiculous, either false or just irrelevant. Like, why would we expect the mass of the thing being simulated to have anything to do with the processing speed? Also, why would we even be able to detect that? Because there wouldn't be any intervening time when we're like waiting for the processor that simulates reality. So none of it makes any sense.
But I just would have thought, you know, like this kind of like post-diction, post hoc offering of an explanation. Okay, maybe there's something to it if the explanation is like a more conservative one. Like, you know, it's like, oh, I've come up with some theory that like, you know, that explains it all, and it's like a simpler theory. I'd be like, oh, okay, I'm gonna generate some predictions based off of that, and figure out, you know, if that's right, or if I need to stick to maybe the old model or whatever. Whereas what's actually being done is the theory is more complicated than anything. Like there's so much more stuff involved in it. It's not like it's like, oh, we came up with a better theory. It's like we came up with a worse theory that accounts for all the data.
Yeah, I mean, a good explanation should be able to account for a wide range of observations with a small number of initial postulates. Whereas it seems that every datum that this is attempting to account for requires a new postulate, many of which are very implausible or entirely ad hoc. So it's a terrible explanation. And partly it's because it's
same. Oh, sorry,
it's just not clear how you could even, like, what would be inconsistent with a virtual reality. It's not obvious that any observation would be, because anything could be simulated in a computer. I don't know how we could tell the difference. So that's, I mean, it's hard to have that explain anything when, remember, a good explanation, as I keep saying, needs to say why we would expect this outcome but not this other outcome. But if all outcomes are equally probable under the explanation, then it doesn't actually explain anything. That's why in general, God is not a good explanation, because he's omnipotent. So he is consistent with any possible outcome, because he could do anything.
It also reminds, like, this is the ad hocness thing as well again, where it's like, oh, okay, well, the speed of light is limiting, you know, limited processes, whatever. But again, all that's being done is offering a description of the phenomena, but in a different way. It's not like there's one unifying thing that's like telling us why we expect all this stuff. I mean, it's similar. It's really interesting. Well, I guess he's saying it is God, but just assuming on the computation thing, it's like I was going to say it's similar. It's interesting how this is similar to God, because you can just say, well, it's a computer simulating it, and like the token that's used to denote that is like, you know, a couple of words, whereas like God is, you know, like one word or whatever, and so like you think, oh, that's well, it's not the word that's used to express the idea. It's not the simplicity of the language that you have to use to express it. It's the actual explanation and the ontology of that explanation.
Exactly,
like
yes. And that's commonly misunderstood. And I think a lot of theists are confused by this point, because God seems simple to them in their minds, or the word is simple. And so it seems the explanation is simple, but it isn't. So take an example like the Big Bang, for example. We can predict the proportion of hydrogen, helium, and lithium, and so forth that we would expect based on the Big Bang theory, because of a series of assumptions that flow out from the underlying logic of that theory. And if we observe something different, that would be inconsistent with the existing theory that we have. Now, compare that to theism. Let's say that God just banged the bang, right? What would we expect the proportion of different elements to be? Now, they could be what they are. It's not ruled out by any evidence, but it would be equally consistent to observe any combination of any elements, because God could create whatever he likes. So that's why it's a bad explanation. It's not because it's falsified by any observations we have. It's because it doesn't account for any observations as being more probable than others. That's why naturalistic explanations like this are, I think, superior when they can account for the data, because they actually rule things out and say, well, no, this is what we'd expect and this is what we would not expect. Whereas God, like, he could do anything. So how can you make any predictions?
Yeah, and it's like, let's say we find out, you know, like that some new thing in physics where I don't know, like there's fundamental p particles and they do something or whatever, and then it'd just be like, oh well, this is kind of like, you know, in a computer how you know, like RAM does this, and so p particles are obviously more evidence of a simulation, like because you know, like
yeah.
yeah, just adding more and more things to the description. Like you can't. It's not like oh, we've reached this. Okay, right. You've got your explanation of. You've reached your final description of the explanation. So, like, if we find something that lies outside of it, that's gonna rule out your explanation. No, just like add a new piece of hardware. Like someone plugged a USB stick in. That's why we, you know, like see black holes.
Yeah, the explanation is infinitely extendable. Yeah. You can just keep adding more into it.
They constitute a high processing demand, so massive objects would slow down the information processing of space-time. In the same way, high amounts of data processing in a computer slow the processing speed down. The fact that all quantum objects are identical to each other correlates to digital equivalence, in that in a virtual world, every digital object created by the same code is identical. The same holds true for quantum particles. And these are just a few of the 11 facts Brian Whitworth lists. He concludes by saying, individually, none of the above short points is convincing, but taken together, they constitute what a court might call circumstantial evidence, favoring virtual reality against objective reality. When coincidences mount up, they present a plausibility argument, if not a proof. More powerful evidence is provided by cases which a virtual reality theory explains easily, but which objective reality...
Like, it's so interesting how this is like the exact same reasoning that the NDE people use. Like,
yep,
when coincidences
the same problem.
Yeah, and
so lots of bad evidence doesn't equal good evidence. If this is a cumulative case done poorly, I'm a fan of cumulative cases, but each element needs to have its own evidentiary value. If each element has no evidentiary value, then the whole thing doesn't have evidentiary value. It's sort of like I think of this as like construction. A single pillar doesn't have to support the whole structure, but each pillar has to bear some of the weight. If it turns out that each individual pillar is like, well, actually, this isn't bearing any weight, and you might say, well, yeah, okay, so no pillar is actually doing it, but like the whole structure as a whole, all the pillars collectively are supporting the weight. That's not how it works. Each has to have individual evidentiary value, and so. When you look through this list, I would argue that not a single item here has any evidentiary value whatever in favor of virtual reality. And therefore, the whole case is worthless. It's not improved by just having more bad evidence.
Yeah, and I think so. One thing that I used to say that I now think is wrong was that this sort of thing is, you know, like conjunctive probability. So if you add together the two claims, then you're going to multiply like the probability of each one happening independently. Okay, it's not that, but it's general probability. So you're gonna have given, if you want to have like both claims together, then it's going to be, well, you've got the first one, and then you've got the probability of the second claim given the first one, and you multiply those together. But if either of those isn't one, then it's going to lower that overall number. And then what we're saying is not only are these not one, but they're not like 0.999 or something. They're like really, 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 really bad. Like, you know.
Well, honestly,
really
most of the items in the list here, at least, I think are probably quite independent of each other. Like, there's no relationship between like this maximum speed in the simulation and whether more mass would mean a slower process. Like, this is just different assumptions. I think most of them are pretty much independent of each other, and none of them are very plausible in themselves. So the whole thing is just. It's actually, it's less probable, not more.
But either way, you look at it like probabilistically, like the more and more that's being put in here isn't making this better in like any way. Like, right.
Approaches have great difficulty with, and this is only the beginning. In the hunt for a theory of quantum gravity, the theoretical data better fits the idea we are a virtual reality. Both underlying string theory and loop quantum gravity is the holographic principle. The idea that three-dimensional universe emerges from information processing on a 2D surface.
Maybe the three-dimensional objects, us, everything in the world around us, maybe all of the information in these objects is carried, is smeared around a distant two-dimensional surface that surrounds us, and we're just in some sense a whole...
Like, at this point, I don't know what, like, I've gone to a different planet, like, the information is smeared around a 2D surface.
Yeah, okay, so I had to do a lot of reading about this because this is pretty high-level stuff. I will defer explanation. I think you need to mute because I'm getting a bit of feedback from when I talk. Yeah, thanks. I will defer an explanation of what he's talking about here to, I think, the emergent universe video where he goes into this in more detail. Yeah, so he is talking about real physics here, but he's misrepresenting it very significantly. So I'll just, we'll put that on hold for the moment and come back to it in a future video where he goes into more detail about this.
Holographic projection of that distant data.
The holographic principle tells us something quite astonishing. It says that our ideas of volume, of the real world in a sense, might be a kind of illusion.
We forget about what space is and what time, and then somehow the information, by thinking about how much information is, what information is doing, then the space-time will, what we call, be emergent. It will come out of just a bunch of zeros and ones.
It should be clear that this whole holographic story is the most radical thing that has happened to our understanding of space, time, matter, since the invention of quantum mechanics and relativity.
Now, someone could always dismiss the theoretical data, but that would be impractical, because it would take away our best chance for a theory rectifying relativity in quantum mechanics. Even so, the experimental data cannot be ignored, and the results of quantum mechanics infers the same implications.
Did you notice that when he said the experimental data cannot be ignored, he displayed the table from that paper that was like a thought experiment?
Yeah, I noticed that as well. Sometimes he just, I mean, maybe this is a bit nitpick, but sometimes he says things in a strange way. Like, I've now forgotten. Can you just rewind like 5 seconds?
Yeah.
What are you saying just doesn't make sense grammatically?
Because it would take away our best chance for a theory rectifying relativity in quantum mechanics. Even so, the experimental data cannot be ignored, and the results of quantum mechanics infers the same implications we see in the holographic principle.
Yeah, infers the same implications. That just doesn't make sense.
Infers the same. Yeah, it implicates.
You don't infer
something. To implicate something
that is imply, not infer.
Yeah,
they're different words. Infer is an inference that a person makes. Imply is like the result of an argument or something like that. It's a nitpick, but sometimes it just annoys me because it makes it less clear what he's saying. Like infers the implication. I'm like, wait, what does that mean? Because it's important how these ideas connect to each other. That's why I think it's. I'm not saying I'm always perfect, but it does matter how you phrase these things, because that helps us to understand what's actually being said here.
Yeah, a person can infer an implication. That would make sense.
Arguments don't infer things. People infer things.
Yeah.
Arguments can imply things, but not infer things. Anyway.
Quantum mechanics means it's possible everything we see could really be produced by lines of code inside a powerful computer.
So we cannot ignore the recent experimental data, like the fact that for objective reality to be true and the world to exist independent of observation, something known as locality would have to follow, which means for objects to interact, they need to be in close proximity. But experiments in the early 80s showed this is not the case. Instant interaction can be seen between two particles that are separated from great distances. This is what we now know as entanglement, and it makes more sense if the world is virtual. In a virtual world, space doesn't limit correlations. All points in a virtual world are equal distance with respect to the source of the...
What even was that sentence? In a virtual world, space doesn't limit correlations. I don't even know what that means.
Well, I mean, yeah, I think he misuses the word correlation quite a lot. He talks about evidence correlating with other things, but that doesn't even make sense. Correlation is a relationship between numerical variables, okay? Objects can't correlate with other objects. That doesn't mean anything. What was I saying about this? Yeah, so the point about he said for a real word... Sorry, can you mute again? It's quite distracting.
Sorry about that. Yeah.
I don't know why it comes and goes like that, but what was I saying? Yeah, he said for like reality to exist, then we'd have to have local interaction only, but locality has been falsified because of these experiments. We discussed that previously. That's just not true. Locality and realism are different points in quantum mechanics. Even on the table that I showed, that whether it's realist and whether it's local are separate issues. So it's true that local hidden variable theories of quantum mechanics have pretty much everyone agrees, not 100%, but most people agree have been falsified. But that doesn't mean that realism's been falsified. It just means that that you can't have local hidden variables. I mean, now, and then he's going to say, well, okay, but then the non-locality is evidence for virtual reality. But it's just not clear that it is, because there are other interpretive approaches there. Rather than saying that it has to be a simulation, you could just say, well, well, basically any of the other interpretations. That's how quantum mechanics works, that you have these relationships between experimental outcomes here and then particles that exist somewhere else.
I think that the reason that the echo occurs is because the thread that's doing the screen sharing, the thread that's giving you the audio, go out of sync. And I wonder what that would look like in the virtual reality if we had a multi-threaded processors going.
Yeah,
out.
maybe it's like the density of the arguments that we're making, like it causes the processor to slow down, and so it, I don't know.
It's the the processor has an antipathy for. I'm trying to make like a joke where you realize how silly humans are at like coming up with scientific explanations when we look at like language and the way we use words and try and like infer the way the world works from like like the medieval scholastics. And
yeah, it's pretty strange. But how can someone say this? It doesn't make any sense to me. So the statement that's right on screen, like it's like my central processing unit is over here, and part of my screen is here, and part of it is over here. Like they're not equidistant. I don't.
Well, here's why I don't know what it's, because like in the browser, right? There's a few things going on that are rendering what I'm seeing. But all of those at some point are going to be like independent instructions, which are going to sit, which are going to sit in a data structure called a stack on the processor and be executed one by one. Instruction, maybe move data into a register, execute an instruction on it, whatever.
Yeah.
And I have no idea like what that has to do with the distance of the things on the screen from the CPU. I just don't even know what this is saying.
Well, the only relevance I could think of is that there is a delay time between when the signal is sent out and when, like, the pixel registers that and changes the display.
Equidistant with respect to the CPU. Like this corner of my screen is further away, though.
That's what I was saying.
Yeah,
so
like,
they're not. I mean, you're not going to observe that, but if the distances were long enough, you would observe a difference there. That's why That's why these finance companies pay millions of dollars to have the direct fiber optic cables to the stock exchange, so that they can just be a few milliseconds faster to make the trades. Because this actually does matter if you need those really high speeds.
When was that paper written? Was it like, is this like an older computer architecture or something like that?
I don't believe so. I'm pretty sure this is. I closed it now. This is only like. I'm curious now. I went to the holograph principle. What's the paper called again? No, it's not that one.
Don't know where it is. Does he mention it? He's Brian Whitworth is the name of the man.
Now I can't find it.
Where are we?
Oh no, it was in this folder. I'm confusing myself.
He's not quite.
Physical worlds of virtual reality. Yeah, here we go. So this paper, this paper was written in 2007.
Okay. I mean, still, I don't think. They had detachable
computers haven't
monitors.
changed that much since.
Yeah, they had detachable monitors with cables, and
I think the Von-Neumann architecture was developed like in the 40s. So I mean, okay, monitors have changed since then, but
I mean, I suppose maybe he means so. Like, if you think about the signal that's coming down the wire, so the signal that's going down the wire is going to hit the hardware in the computer and be distributed about the monitor by its electronics equidistantly. Maybe he means. I really am just not sure what's being said.
Yeah,
On a screen are equal distance with respect to the CPU. Processors can ignore screen distance, and the same thing happens in our world. If our universe is a three-dimensional screen, its processing is equal distance to all points in the universe.
Yeah, I think that's right. It means like from the software perspective, because of the way that the hardware's made, you can just ignore, like you don't have to factor in the distance. You can just assume it's all going down the wire the same way. But
yeah,
again,
but that's only because the speed of light is very fast. Like and your computer is small. If bits of your computer were extended across a large space, then you would have to worry about this. And the fiber optic cable for the finance people is an example of when that is relevant.
Yeah, so, that's why I'm saying I don't know what this is even supposed to like show about the theory. If our universe is a three-dimensional screen, its processing is equidistant to what does that tell me about this explanation? So the non-local collapse of the quantum wave function could be what?
Like the thing is that what I want to know is hang on. I thought the universe, our three-dimensional universe, is the simulation, but here he's saying it's the screen. But the screen is hardware. If we use a computer analogy, the screen is physical hardware that exists in the physical world, right? So if our three-dimensional universe is the screen, then that would be part of the same physical universe that it was simulated in, because the screen is hardware just like the processor is. So they're not even consistent about the way they're defining the different components. Like, is our universe the simulation, like the processing, or is it part of the hardware?
We'd have to be observers that were we'd have to be from the real reality but put into the machine.
Yeah,
maybe would that, you know, so we've got like our real reality eyes on in our souls, and then we can like look at the
you're hurting me, Nathan. I can't deal with this. I don't understand. Let's continue. I can't. Yeah, you've broken me.
The collapse of a quantum wave function could be such an effect. Space seems to be an illusion created by the virtual construct, which is something Einstein came to realize at the end of his lifetime. Hence, it is clear that the space of physics is not, in the last analysis, anything given in nature or independent of human thought. It is a function of our conception.
Einstein was a big Linux advocate as well.
Scheme. Space as conceived by Newton proved to be an illusion. But even more strange than this is what quantum physics tells us about matter. Prior to observation, matter doesn't exist. This was demonstrated in the 1920s by the double slit experiment. The existence of matter is dependent on observation, and recent experiments have not only reconfirmed this, but have debunked theories in order to avoid the conclusion that the existence of matter is observation dependent. Now, many accept that particles do not exist prior to observation, but they exist in a state of a wave, which then forms into particles upon measurement. But this would be false. As they point out in the quantum enigma, quantum probability is not the probability of where an atom is, it is the objective probability of where you or anybody will find it. The atom wasn't someplace until it was observed to be there, which is what Heisenberg said years ago. The atom or element.
The atom wasn't someplace until it was observed to be there on these interpretations.
Yeah, but that's, well, see, the thing is that what IP said is that you can't say that the, let's say the electron existed as a distributed wave prior to collapse. Because, and then he quoted that passage from Quantum Enigma, which just said that the particle doesn't have a well-defined location prior to measurement. But that's perfectly consistent with the idea that it was a wave before measurement. Like, IP's argument is illogical because the quote that he gave as being a reason why you can't say that while the particle was real, it was just extended as a wave prior to collapse. Well, I mean, it wouldn't be a particle, but the electron was real. It just was extended as a wave prior to being collapsed into a particle. That's not false because, and let's go back to this quote, the first quote. He's saying that is false because...
Not this one.
No, the previous one, the one before that, from Encountering Consciousness or whatever.
Yeah. That? Or,
he's saying that's false because quantum probability is not the probability of where an atom is, it's the probability of where you will find it. But that's consistent with what what you would say, in that, yes, the electron is distributed as a wave before you collapse it, and the square of the wave function gives you, by the Born rule, the probability of the wave function collapsing to find the particle in that particular location. This quote does not refute the thing that he says that it refutes. It's perfectly consistent with the thing that he says it refutes. It's just explaining what he says that it's false. Like, he says, basically, IP is saying X is false, and this quote shows why it's false, and this quote just says X. Like, it's just asserting the thing that he says is false, basically. It doesn't make any sense how this is supposed to be an argument against that. Yeah, exactly. Alan Bird points this very well. The position of matter, or I'll say the position of a particle, is not the same as its existence. It existed prior to measurement. It's just that it didn't exist as a particle with a localized, well-defined location. And that's all this quote is saying, which is just a standard view of quantum mechanics.
Find it. The atom was someplace until it was observed to be there, which is what Heisenberg said years ago. The atom or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of the things or facts. But what does this all mean?
These basic rules of quantum mechanics apply to all tiny subatomic particles. When we look at them, they are just dots. When we look away, they lose their physical form.
A different way of looking at that is to say, well, how parallel is this behavior with what I see in my PlayStation 3 when I'm playing a video game. In a PlayStation 3, and for an example of that is SimCity. It's an enormous city. I can navigate my way through every bit of it because the PlayStation, the video game, gives me the frame that I need when I'm looking there. If I look somewhere else, it'll create that frame. Well, oddly enough, the universe behaves that way in reality. The universe gives you what you're looking at when you're looking at it. When you're not looking at it, it's not necessarily there.
Our world is pixelated and only assumes definite form.
On that point, I don't exactly know who that guy is, but I think what he's saying is just making an analogy for a popular audience about the way quantum measurement works. Because what we have established is that quantum mechanics is not consistent with the idea that the particle had a position that it moved through that we just didn't know. No, it didn't have a defined state before collapse. And how it collapses is context dependent. We talked about quantum contextuality. I think he's probably referring to those in a very loose way to help people understand. I think that's what he's saying. I mean, it might not be. It's hard to tell. But if that's what he's saying, then that's what he said is fine. He's just trying to give an analogy for that. But it's just not true to say that you're forced to the view that like nothing exists until you look at it. That's not what quantum mechanics says at all, as we've discussed. Also, who the heck plays SimCity on a PlayStation? That's a computer game. Like, I don't even know if it's been ported on the PlayStation. Irrelevant point, but as a SimCity fan, it kind of annoyed me there. Yeah. Plus, what they were showing wasn't SimCity.
You could just make, but this is how weird analogous like reasoning. This is just like how spurious these like analogies are. It's like you can just like draw any like image, any platform.
That's why you've got to watch out for these documentaries, because they're often very misleading. Even if they get physicists, who are really good physicists, and I don't know who that individual was. Maybe someone in the chat can pull that up. But even if they get good physicists, they often have to like try to popularize or simplify what they're saying, and then they sort of pick out the quotes and put them in their context, and then they interpose this imagery with Morgan Freeman talking, and often you get a misperception of what the actual science is.
It's the clips as well, because like do you remember that debate with William Lane Craig, Jordan Peterson, and Rebecca Goldstein, where she says like, oh, it's the like the Euthyphro dilemma is a problem for your view. Are you okay?
I haven't actually watched that debate.
Yeah. And Jordan Peterson goes, William Lane Craig comes out with a quote where he's like, the Euthyphro dilemma has been debunked or something like that. Or was it it might have been, it was either the Euthyphro or it was like the genetic fallacy. It was one of those things. And he quotes against her husband, Steven Pinker, in a book saying something, but Steven Pinker in the actual quote in the book is saying someone might argue X, but that would be wrong because. But William Lane Craig quotes X as if he's like that's something he advocates against her.
Jeez.
Like, I mean that's like one version of this though, where these documentary makers they get like it's the same with the NDE ones as well, where you get like people saying these things, but then like you selectively clip out the quotes, you change the scene every 4 seconds so your brain doesn't actually get used to what's going on and start thinking about it, and you put some imagery in that maybe like anchors your sort of creation of what's being said to something in reality that will make it make sense for you, and it doesn't have to make sense. It just like becomes this thing that you start believing in randomly because your brain's bad at.
Yeah, exactly. And these documentaries can be quite misleading, especially about quantum mechanics, because they like to play up the quantum mysticism part, which got to be careful about.
And ancient aliens as well. That's
computer simulations behave.
The conclusion is inescapable. The universe behaves as a virtual reality. In light of the evidence, this is why this question is now taken seriously by experts. Which brings us to the next question.
The more interesting aspect to that question is, who's the programmer and where's the computer?
If the universe is a simulation, who is the simulator? Should we take the view of Nick Bostrom, that we are being simulated by future humans as an ancestor simulation? Well, the problem with this theory is it really doesn't answer the question. If we are being simulated by future humans, then their world would have to have the same features as ours and be based on qubits. This would.
We're gonna get to let's see. What I'm interested in. I'll say what I'm interested in. I'm interested in what IP is going to tell us about meta reality that God lives in. That's what I'm interested in, because he's going to say, well, there's a problem for people who are saying this, because it just pushes the goalposts another step back. But then what's IP going to say about his materiality, where he doesn't have, that problem?
Imply they are also a simulation. Using Leibniz's law and discernibility of identicals, it would have to follow that they are also a simulation, if they have the exact same world as ours, just further in the future. If the properties of our world entail that we are a virtual reality, then a world identical to ours would have the same implications. But if their world needs outside processing, they would also need a simulator. If they are also being simulated by a future civilization, then the cycle continues, and it is nothing more than an infinite regress. Borstrom admits this and says, we would have to suspect that the post-humans running our simulation are themselves simulated beings, and their creators in turn may also be simulated beings. Reality may thus contain many levels. So this amounts to nothing more than an infinite regress. But what if one of the higher levels is not a quantum world, but an actual objective world based on classical physics? Well, this solution creates more problems.
I mean, he's going to critique this view, but I'm not even sure what that would mean, because there's only the one world, and then we have things we come up with to describe it.
Well, Bostrom has famously presented the simulation argument, although not for the same reasons that IP does. Bostrom's certainly no theist, but I think an interesting point that IP isn't. I mean, I don't believe the universe is a simulation. Right? There are actually people who argue for this, but on completely non-theistic grounds.
Yeah.
I don't buy their arguments, but putting that to the side, suppose the universe was a simulation. What IP is saying, well, this just leads to an infinite regress, but I don't see how it does, because you see, the argument that he makes for this universe being a simulation is based on the physical laws of the universe, or our understanding of them at least. But the underlying ultimate reality could have completely different physical laws. And so the arguments he's going to make for that being a simulation may not apply at all, right? Now, he kind of is relating to that here, because he's saying, well, suppose there was an objective world based on classical physics. But I wouldn't say that. Why would it be based on classical physics? It could be based on literally any physics you could imagine. It could have completely different physical rules to ours. In fact, maybe you'd expect that if someone was simulating it. Maybe they just want to know. Maybe they're trying to solve the fine-tuning argument, and they're simulating different universes with all different possible types of physics and parameters to see which of them develop life, because they want to know whether God exists. A silly reason, but the point is that there's no reason to think that the underlying physics of the true reality, however many simulation worlds that goes down, is anything like the physics that we know. So I don't actually see how you can make this argument, because the physics could be anything.
Yeah.
Problems that it solves. For a quantum world like ours to be simulated in a classical world, all of the qubits would have to be unpacked into classical bits, and this would result in a classical computer hard drive bigger than that which is being simulated. So a computer bigger than the universe itself, which would be absurd to postulate
because it has to be simulated on, your Dell PC and not.
This argument makes no sense. The fact that so suppose that you did need a computer that was bigger than our universe to simulate our universe. What difference would that make? The computer doesn't exist in our universe. It exists in the universe that it exists in, which could be arbitrarily large. The argument makes no sense. It's like, somehow the computer that simulates the universe needs to exist in its own simulation. What? No, that's not how it works.
Yeah, there's a lot of stuff going on there. Why assume that? Why would it have to be bigger? So he's saying qubits contain more information than can be represented. So but information doesn't necessarily correspond to size of the representation, Sackett.
Or of the computer, but we could go on about that, but Sorry, no sound.
Vault of Heaven.
Sorry about that. Is that Freeman Dyson? Who's this guy?
Yeah, that's right. I was wondering why he looked so creepy, but yeah, Freeman Dyson did look creepy, so... I think he died recently, wasn't it? A few years ago.
Yeah, I think so. Ferguson.
I was going to say, I'll say thanks, Ferguson, because if I said the other thing, it wouldn't sound so sincere.
It feels like what the Closer to Truth channel should have been. Oh, thanks for that.
Not familiar with that channel. What do they do?
They've done a lot of interviews in person, and it's something I'd love to do in future as well with a lot of like theologians, philosophers, and physicists. So I think they've even got one with Freeman Dyson as well. You know, like sitting down in cool places like churches or physics labs or
Right.
whatever, and they just ask these like questions like, "Oh, is maths invented or discovered?" Or like, what does it mean for God to exist or whatever? And these people, like they get these 10-minute videos that are quite popular that people watch.
10 minutes. Pff.
Yeah.
The universe is being simulated in a mind.
Could what we think is the universe be some sort of vault of heaven rather than a real thing?
Given the problems that result from being simulated on a computer, one can find a much simpler explanation that the universe is being simulated in a mind. This would solve many problems of being simulated on a computer, because a mind
That's an interesting looking mind.
is being simulated in a mind.
Why does it look like that?
Yeah, why do minds look like brains? In every representation, they always look like brains. It's a bit suspicious. It's almost like we have no idea what they would look like.
Well, they're not spatial, James. They're just
Yeah. Okay, but this is a problem here. Okay, so if a mind is immaterial, how does it process information? Because information needs to be instantiated materially. This is an even bigger problem for God, because later on he's going to say that God doesn't have... IP is going to say God is outside of time. God doesn't process... I think it's actually one of the debates that he says this. God doesn't process information because that implies a sequential series of internal states, which would basically bring God into time. So God can't process information. That doesn't... Maybe you can get away... there's a way around that where you can simulate something without processing it, but at the very least, you can't say that it's like a computer, because it's going to have to be something very different.
Well, in terms of what we said, necessary conditions of computation seems to be a series of finite steps.
Yes.
So, like if we're going to say that God is the computer performing a computation, but doesn't have a series of finite steps, then it's not computation. We've falsified our own hypothesis, of course. I don't know how you can get around that. You're going to have to say it's like, I don't know, theo computation, like it's sort of computation, but it's not. Right.
Invent a new thing.
Invent a new thing and apply it as a predicate.
This would solve many problems of being simulated on a computer, because a mind has elements of integrated information states and also processes information.
I need to stop and think about this again now. A mind has elements of integrated information states and also processes information. Okay, I think I can grant this much. I mean, it's pretty vague. It's not.
I'm going to say the first clause there is pretty much meaningless. A mind has elements of integrated information states.
Yeah.
I have no idea what that means. Elements of it?
Mean, yeah, it could mean anything really. I think because just anything can be information, right? So
pretty much,
if minds exist, then there's going to be some information about them. And process information. I don't think I can think of a mind apart from it processing information. I don't understand what that would be like. So I think
it's interesting that in sort of cognitive psychology or sort of computational neuroscience, well, no, I shouldn't say computational neuroscience, because that usually applies an information processing framework. But in cognitive science more generally, this is actually still somewhat controversial. So computationalism is kind of the main game, but there are still, like I mentioned, John Searle, who argues that there's more to thinking than computation, essentially. But I don't think he would disagree that minds process information. But I mean, is processing information the same as performing computations? And there's other questions you can ask there.
Yeah. I understand. Yeah.
The thing is, Searle is not any sort of dualist, as far as I'm aware. He just thinks that computation, there's more to it than computation, and isn't fully on board with the sort of computational theory of mind stuff. So I'm just saying there's sort of more to it than IP's presenting here.
Yeah, you're right. Let's continue.
The physics in a dream environment would emerge from information processing and therefore look identical to the conditions of our world as we described earlier. So a dream environment just emerges from Platonic information in a mind, which is essentially the same type of physics we see in a generic information construct, such as the illusion of space and matter and the elements which make it finite and computable. Even more important, a mind, different from the brain in a computer, is an immaterial substance that doesn't require matter to exist. In fact, interestingly enough, matter seems to need mind, since this is what quantum mechanics tells us. Mind is necessary.
Since I'm begging the question, I can't see. I just can't see how again it's that problem where how are you getting these finite computational steps in immaterial substance? Like I literally only understand computation fundamentally in terms of like electrons doing things in a von Neumann architecture machine, or like someone turning a cog that makes like, you know, like arms do something in like the difference engine or whatever, or Pascal's weird computer. Like I have no idea what it looks like to do a computation.
So standard model of computation is deterministic. It passes through discrete states, and it follows a series of, well, deterministic rules, which are finite and always stops, right? So these are some of the elements of computation. So how would that work in an immaterial mind? I mean, there's got to be one state that deterministically leads to the next state, because that's what it is to compute.
Yeah.
It has to be discrete, and there has to be some sort of, well, mechanistic process that generates this one state based on this existing state that, you know, so you have a state that you're in, and the next state that you move to depends on your existing state. And that has to be deterministic. How does any of that fit with IP's view of what the mind is, this immaterial free agent? It just seems like a completely different description. Yeah, exactly. Like that seems inconsistent with the notion of a computation. I don't know how you reconcile those.
Yeah, I don't even know what's going on with this.
Necessary to collapse a wave function for matter to exist.
So recent experiments led by the group at the University of Vienna, Austria, provide the most compelling evidence yet that there is no objective reality beyond what we observe. So it's really the observation that creates the reality. What they found is that Leggett's inequality is violated as well as Bell's, even if you allow for instantaneous influence.
Do you know who this is speaking or what they're speaking about? Did you find out anything?
I don't know who is speaking. I did look up the Leggett inequality, so we can talk about that briefly if you would like. I hadn't heard of it before. Let me pull something up. I don't want to get too bogged down into this because it is fairly technical, but since he does mention it a couple of times, it would be worth touching on. Okay, so this is a pretty good paper. What does the Leggett I just called the Leggett inequality actually test, because it's often misstated as to what this exactly shows, and indeed I think that there's even some confusion in the literature based on this paper here. So the Leggett inequality is, well, it's like Bell's inequality, right? So it's attempting to show restrictions on particular types of physical theories, and so the I think the Leggett inequality has been demonstrated to hold, so it's the opposite of Bell's inequality, which has been violated. But what I wanted to show here, I don't even really want to get into what, I mean, like, that is the Leggett inequality right here. Or it says in one of its standard forms. It's basically just describing the different possible states that certain types of quantum systems can be in under certain assumptions, essentially. But the key point that I think I wanted to make here is down here, right? So Leggett's derivation of the inequality uses, as we've seen, both the assumption of macroscopic realism and the assumption of non-invasive measurability. Whilst Leggett notes that the non-invasive measurability does not follow logically as a consequence of macroscopic realism, they try to argue that it is nevertheless extremely natural and plausible. So this is the key point that I want to emphasize here, because what they're trying to discuss for this inequality is whether you can have states, so macroscopically real states, so that's basically like there's a determinate state that the system exists in, and non-invasive measurability, which I don't understand precisely how that's defined, but basically that you can measure the system without changing it, essentially.
Right, okay.
And as far as I understand, they're showing that you can't have both of these things. The Leggett inequality shows that. So you can't have macroscopic realism and non-invasive measurability. But as the point is made here, that non-invasive measurability does not follow from macroscopic realism. So they are separate assumptions. And what this paper talks about, and what I tend to think about as well, is that they're just, this is not a sort of extremely natural and plausible assumption. It might be an intuitive one, but I don't see why we should expect this to hold. So, I mean, it's a fairly standard view that when you try to interact with a quantum system, it can change their system.
Yeah,
I suspect there's a bit more to it than in the particular application here. But the key point that I wanted to make here, given what the extent to which I understand it, is that it's not that result, the Leggett inequality, is not just about realism. It's also about non-invasive measurability. So there's further assumptions that are being made there. And what the result shows is you can't have both of those. You can't have macroscopic realism plus non-invasive measurability. And now, remind me, if we can jump back a bit, what does IP claim about the Legan inequality? Because I've sort of forgotten as to exactly what he said about it. But I think he claimed a lot more than that.
Yeah, let me try from here.
Mechanics tells us mind is necessary to collapse a wave function for matter to exist.
So recent experiments led by the group at the University of Vienna, Austria, provide the most compelling evidence yet that there is no objective reality beyond what we observe. So it's really the observation that creates the reality. What they found is that Leggett's inequality is violated as...
Yeah, I think it's observation creates the reality, like this point here, rather than passive observing it, we in fact create reality. I think that's what IP is trying to push here, the idea that there's no reality to the quantum state, we sort of create it. But that's not really what the result shows. It shows that you can't have macroscopic realism, which relates to the reality part, plus non-invasive measurability. And that's a statement about when we measure a system, we change it, essentially. And to me, that is not very surprising. I mean, I don't know if it's exactly the same as the observer effect, or it's a bit more specific than that. I need to read more. But again, the fact that we have to give that up is not overly surprising to me. And it certainly doesn't imply that we create reality, or like it didn't exist and we just like invent it somehow. That's not what it's showing.
Yeah, these are like interesting little kind of like riddles where it's easy to get like lost in your own description and form like a false model of what's going on by like using analogy. It's kind of like that initial thing that we were talking about with the photon, where the photon is the very means by which you would observe, you would see. So to be like, oh, you're seeing the photon, like doesn't make sense without interacting with it. Or it's kind of like, like if you ask someone, this is like this little riddle of, what's it? If you look into, if you look in a mirror, why is like left and right reversed and like up and down isn't reversed and stuff like that? And you get kind of like trapped in your own point of view and for some reason, like find it difficult to answer. You're like, oh yeah, like why is the light being reversed that way, but not the, and then whereas if you like, all of a sudden, all you need is like someone to just give you that additional bit of insight, like, step outside and like look at what's going on. And then you see like, oh yeah, it's just reflecting the same bit each time. But when you're in that like first person point of view, it's really difficult to see. And I think it's the same with some of the inferences that are being made, the inferences that are being implied by some of these things. Like, I mean, I'm obviously assuming that what you're saying is in the paper is what's in it, and there isn't like something else.
At least show the highlighted section. But you can look at that paper, and it is talking in a lot of detail about what the Legan inequality actually shows. I do hope that by the time we have the discussion, I had the discussion with Michael, that I'll have a bit more time to digest some of these results with more precision than I currently have. But I think, again, it seems pretty clear looking at that to me that it does not say what IP says that it does, even if I don't have a full understanding of exactly what it does say. And I think that's consistent with the fact that these questions that IP is implying are closed by some of these inequalities are still discussed by physicists, and they're still contentious, and they're just not resolved by these results, because it's really about exactly what assumptions you make and how you interpret them and things like that, which is sort of issues that IP just doesn't address.
Well, this is, I guess this is what I'm saying is the issue, is you have like these riddles, which, because they might trap you in like your own epistemic access to the world and your own like ways of describing them, like it might seem like, it seems like certain things are like intuitive ways of describing what's going on. This is like a computation, this is like a conscious observer, an observer, whatever. But then you form like these little false beliefs, and then as you keep layering more and more in, you like build up this whole system, which is just like based on like false lemmas all the way up almost. That's what I like. I definitely do not know enough like physics or quantum physics or philosophy to be like a relevant authority on any of this, but it seems like as we go through it claim by claim, that's like what's happening, is like you have the initial level of like quantum interpretation that gets put in, and then there's some stuff wrong with that, and then it's like, oh, and then here's a bit of philosophy of interpretation and philosophy of science, that's a bit wrong, here's some more false beliefs in there. And then it's like 10 years down the line of doing this and like, coming to learn about computation, learn about this, and you've added in like all these false beliefs. And then we reach this point where like it's almost impossible to even engage with like what a paper is actually saying, because all your background beliefs are like over here and reality is like over here. Like,
Yeah, that's a really good point. And unfortunately, a lot of people on IP's channel just sort of eat this stuff up and don't seem to be, I mean, I don't know, unless he deletes all of the negative or critical or questioning comments and just keeps the positive ones. But even so, there's still a lot of just highly positive comments that just are very uncritical. Like, oh, this is the best channel ever. This is amazing. And I'm learning so much stuff. I just, you know, all that sort of thing.
Yeah. I mean, I guess I was thinking I've got some comments like that, but I guess I can't say that because I've got a lot of also
I don't think we get that many comments like that, but here's the sort of comment that I don't see. I'm not saying there are zero comments like this, but I don't see them. A comment like, you know, I hadn't heard of this or that before. I'm going to, you've given me something to think about and I'm going to read more into this, something like that. That is the comment I would like to see, but I don't see a lot of that. They seem to be just taking what he says at face value and not going and doing more thinking about it, which is the real issue here.
Yeah,
I think. David asks, should we even expect most people to be able to see through things like this? By the way, Nathan, there's no sound on the video. I'm not sure that we would expect most people to be able to see through things like this, particularly when you combine it with IP's presentation skills and all of the quotes and other things that he shows that make it seem quite sort of legitimate and authoritative. But I guess that's the point of doing these videos, where we try to break that down a bit and show that, you know, it's a lot less robust than IP is claiming that it is.
Yeah. And then Alan says, I mean, James here has like a degree in physics and understands a bit of what's going on, but even so, he's saying, you know, like take what I'm saying with a pinch of salt, and I'm still learning about it. Now, this definitely applies for me. Like I haven't done like physics since high school. I mean, other than like a bit of stuff in my spare time. And again, like I'm definitely not an authority on this. I'm just like offering my thoughts as someone who has endeavored to develop critical thinking skills. And so even like we're not really the relevant authorities on this. We're just the only people who seem to be around to to sort of address the claims of apologists like IP who are drawing on all these sources. And like you need to like then delve into like a bit of physics, a bit of philosophy, a bit of quantum this and that, to a bit of theology to be able to.
Yeah, and the thing is, it's not clear that there are relevant authorities in a lot of this stuff. Like, who's a relevant authority on interpretation of quantum mechanics? You might say, well, a physicist, but actually a lot of physicists don't know very much about this because they don't do anything with it. A lot of physicists haven't heard of these different interpretations. They've just been taught Copenhagen and don't think too much about it. But you might say, okay, so someone who specializes in that, well, they would know a lot more about the details of some of these points. I'm not sure that they would necessarily know that much about some of the philosophical aspects that IP is drawing out of it. But also, even there, I mean, you also have to have someone, thanks, Mitch. You also have to have someone who is able to separate their own idiosyncratic views from like what the general state of things are. Like, you know, you can find physicists who know about this stuff, who have very particular views and will push those. And, you know, you wouldn't necessarily know how to argue against them because they know more about it than you do, but that doesn't mean that they're right. It's, I mean, you know, I'm not saying I'm right about everything, but I do think I make a lot of effort to separate, well, here's what I tend to think, with like pushing that. Like, for example, I've said that I kind of have a preference for hidden variable or objective collapse theories, but I'm not arguing for those now because, well, I'm not a super expert, but even if I did learn a lot more about it, I just wouldn't be confident enough in those views because it's really contested. So like, I think that, that's one issue about relying on individual experts too much, because they can still be really biased in their own particular views. And so and in fact, they can be the worst at it, right? Because no one knows enough to disabuse them of their like confidence that they can argue with. So there's a balance there between, that's why I said at the start, like, well, I can't remember exactly what I said, but like not having a degree in something doesn't mean that you should be dismissed. It can be relevant to assess whether someone knows what they're talking about. But at the end of the day, I think that arguments should be assessed on the basis of what is the content of them, not on the basis of who said them. And I don't think people need to have qualifications to say something about it. But it can be telling when they don't have qualifications and what they say is total nonsense as well, based on just basic physics. Like, we're seeing a pattern here where this person just doesn't know what they're talking about.
Well, I suppose the problem with especially this kind of quantum thing is it's not that the person doesn't have a degree, but it's that there's a certain amount of like legwork that needs to be done to like have an understanding of what's going on with the quantum stuff, and that is going to involve, you know, reading around the subject of physics. In terms of interpretation, reading a bit about the philosophy of science, and also doing some maths, right, to be able to, because most of this is using maths as a descriptive language to try and like describe the observations and make predictions based off them and stuff like that. So if someone can do that legwork without getting a degree, but it seems like rather than doing that, like I'm pretty confident that if IP were asked to do like one of these equations or something and figure out like a solution to it, that he wouldn't really be able to, for example. And that's not to say that then therefore what he's saying is wrong, but it seems like he's not approaching like quantum physics as a subject to be understood, but it's a philosophy Pokemon to be collected, key terms to be Google scholared. And then if I can put way more in my column than anyone else I come across can put in their column of like bullet points, then I've won, kind of thing. That's what seems to be going on, rather than like let's investigate.
And I think that
this.
really comes across in the debates as well, which we'll get to in a bit, the way he presents this. And that's one of the reasons I'm looking forward to having a discussion with him, because I think we'll be able to have the time, and I guess I have the patience to look into this stuff where we can dissect some of it in a bit more detail.
Yeah.
So I think we're about finished. Let's finish this one out.
Yep.
Objective reality.
So a mind, unlike a computer, doesn't require the existence of particles to be built upon. So given the options, the most likely case is the universe is actually being simulated in an immaterial necessary mind.
An all-powerful, all-knowing, super-intelligent being. An entity whose motives are unfathomable.
It's very important for us physicists to not dismiss ideas just because they're weird. Because if we did, we would have already dismissed atoms, black holes, and all sorts of other marvelous things.
But from this deduction, we can then formulate a simple argument. Premise 1. Simulations can only exist in a computer or in a mind. Premise 2. The universe is a simulation. This, of course, comes from the evidence.
So I just want to say, I know in terms of charitability, right, you should grant premise 1 to let him get the argument off the ground. But it's like, I thought we were just saying that minds are computers. Like, it's not a computer or a mind. It's simulations can only exist in computers, and minds are computers.
Yeah, I mean, a computer is something that computes, right? So, I mean, depending on how we define a simulation, it would seem to me that, yeah, I don't know. But, premise 1, I think, is questionable, but depending on how you define a simulation, really. And this was briefly mentioned in one of the debates, actually. But premise 2 is really where the work's going on here, because there's just no good reason to think that, well, Bostrom presents various arguments for thinking that the universe is a simulation, but those are very different to the type of arguments IP presents. The type of arguments that IP presents are mostly derived from that paper we talked about, which is just terrible. There's no good arguments made in that paper that I saw. So I just don't see any reason to accept premise 2 that's been presented by IP.
I think the reason why it might be important to draw out that premise 1 in a different way. So if we had like simulations can only exist in a computer, we could probably, I mean, I could probably grant that. I don't really know, but yeah, okay, fair enough. And then we go, the mind is a computer. So maybe I can grant that. And then we can go, okay, so the universe is a simulation. So the universe exists in a computer, but then we have to infer that then it's going to draw out that inference as to why the kind of computer would be a mind if the premises were kind of established in that different way. Because I think, I don't know what the rest of the premises are. So maybe I'll just shut up and play it. Thank you, Fake Name, for your donation. It's appreciated.
Do you prefer fake or name, or should I just say the word Mr. Name?
There were two people with the same
Mrs.
name.
Miss? I don't know.
There were two people with fake name as their name in the live chat, I think, the other day.
It's presented earlier. Premise 3. A simulation on a computer still must be simulated in a mind. This would follow from the infinite regress.
So this would follow for a simulation on a computer still. Okay, sure. Whatever.
Problem if we were being simulated on a computer. To prevent the infinite regress of endless computer simulations, we eventually have to stop postulating higher levels of computers and stop with a simulation existing in a necessary mind. And we would also have to remember...
In a necessary mind?
I don't know where that comes from.
The
Hasn't said anything about necessity before now, so I don't know.
If we have to inevitably arrive at the conclusion of existing in a mind, then why even postulate intermediate levels of computer simulations, unless it is necessary to do so? And no reason.
Oh, wow. I'm not having this. I'm not having invoking Occam's bloody razor here to say there's just one layer deep. After all that, after all 5 hours, are we really going to do this? There's no need to postulate the intermediary levels. Oh my God, there's no need, is there? There's no need.
I don't follow how he established that the universe can't be a simulation in a computer that exists in just a different physical universe. He made some sort of weird indiscernibility of identicals argument, which I just didn't understand at all as to why that would be the case.
Well, he said if it were a computer must still be in a mind, right? That would be the premise doing the work there, or am I? I remember he made the indiscernibility of identicals thing.
Yeah, I didn't understand that argument. But why couldn't there be a computer that's just in a different universe, like that's in the real universe, and we're a simulation in a computer in that universe? I don't see why that's ruled out.
Because he'd say it still has to be in a mind, or you have an infinite regress. Because then that'd have to be in a computer.
Where does the regress? So why does the computer that's doing the simulation have to itself be simulated? That's what I don't get.
Yeah,
it could have there could be completely different physical laws in that universe, so that the argument for that universe wouldn't apply, because it would be different to the argument that this universe is a simulation.
Yes, I get what you're saying now. Yeah. That would also undercut the premise, I think. Yeah. Yeah, I don't think he's got a response to that, and or he's vocalized in the
yeah.
In the
I mean, I do like the visual though. That you've got this the universe in this computers in the mind, and then the computers just disappeared. It's just the universe in the mind. It's like logically and inescapably.
Specifically in the central sulcus or whatever. What's that part called?
I can't exactly see. That's the dorsal fissure between the two hemispheres. Well, I guess it's in both, right? Because the sulcus would be sort of sideways in this image. But anyways,
intermediate levels of computer simulations, unless it is necessary to do so, and no reason suggests this. And one can also argue that it may not even be possible to simulate conscious beings in a computer, given this hasn't been demonstrated to be possible. And one can argue that consciousness is more complex than just...
well, there you go, James. It's just not been demonstrated to be possible to demonstrate conscious minds in a computer. So he's foreseen your objections.
Yeah, well, fair enough. I mean, it's not been demonstrated. I can't argue with that. It's true, it has not been. So
one can argue that consciousness is more complex than just information processing.
I bet are you going to argue that as well?
That is actually a very interesting point. So I think so this is what John Searle was saying. I think he agrees with this. That's what his Chinese room argument is attempting to show. I don't really want to get into that here. I think that it depends on what you mean, because information processing is such a vague term. I think that so just because an account is attempting, let me rephrase that. Just because we're giving an account of consciousness or intentionality or something like that involves information processing, I don't think that would necessarily reproduce like all conscious behaviors. Like I think you could replicate aspects of what the brain does at some level that wouldn't be conscious. But if you went far enough down and sort of simulated that, I think that you would reproduce the consciousness. So I don't know exactly like how detailed the simulation would have to be in order to reproduce all of the relevant aspects of consciousness. That's an open question. But
yeah, I see what you mean. Yeah,
I don't think there's anything that's not computable about consciousness. Let me put it that way, as far as I know. But it's a very subtle question, so that's why we could easily spend 8 hours just talking about that. I think maybe we'll at some point. I don't know.
Yeah, maybe for another day. I was going to say maybe there's something about it like. Maybe everything is like computable about consciousness except like the qualia or something like that, right? And then it's like, but that's to do with the type of hardware it's running on for some reason.
That's actually what John Searle thinks.
Right.
So he thinks that neurons have special causative powers that give rise to like understanding and consciousness, I think. Which I don't really agree with, but I mean, it also depends on what you mean. Again, I don't think that just any way to try to simulate the brain or the process of the mind would necessarily result in consciousness. It depends on the level of the simulation.
Yeah.
But I don't agree that you could have everything the same but not be consciousness, because that would be what's called a philosophical zombie that's physically indistinguishable but not conscious. And I don't think that's possible.
I suppose what I mean is you could like computationally on like the type of computer that I have, you could model an entire brain and every single neuron, but you'd be modeling it. And so because the underlying hardware is different, there are actually different properties in the model than there are when you're like running that in reality when it's made.
Yes, this is actually a point I've written about before. So it seems to me that the method by which something is physically, let me rephrase that, the method by which a simulation is physically instantiated or processed could be relevant to whether consciousness emerges or not. Because in theory, you could run that same program on like a series of water pipes spread out across a large area, or like people in China holding up signs or something like that. Yeah, and it's plausible that the way it's instantiated could make a difference here, but that's quite speculative because we don't really know. And I tend to think that might be the case, but I know I'm not sure. But I don't think there's anything non-physical going on.
But a different conversation for a different day. Well, yeah.
So Occam's razor shaves these off. But even if one insists on leaving them there, the universe would still exist in a mind anyway. So inevitably, we have to say premise 4. Therefore, the universe is a simulation in a mind. Premise 5. This mind is what we call God.
And again, like the old Tommy Aquinas, like it's not though, is it?
Well, yeah, not exactly.
I mean,
I'm not sure how God can simulate something, because that seems to imply a succession of sort of separable states.
But it's like even if this is all dubious, but it's like to get from 4 to 5 by this is what all men call God, whatever the et hoc omnes intelligent deum or something, that all of Thomas Aquinas's 5 ways end with. It's like, well, it's not necessarily, it isn't what all men call God. Well, that's not what this mind is what we call God. Well, what if I don't? What if I just call it the simulator? What if I call it Brahman? What if you just don't get that for free? Like it could be anything else. It's like, oh, well, for all intents and purposes, I'm going to call it God. Well, it's just an alien. It's just an alien that's.
I mean, if you think about what properties is God supposed to have: omniscient, omnipotent, omnibenevolent, non-spatial, non-temporal, whatever else. Well, not everyone agrees is non-temporal, but a lot do. How many of these has the established God to have? It's not even clear he's omnipotent, right? Because there might be things that you can't. The simulator can't do. I mean, just because you're a simulator doesn't mean you can do anything in the simulation. You might not know how to program it, or you might have limited hardware or whatever, right? So I don't know that this really establishes any of God's traditional properties, other than perhaps he's the creator of the universe, I guess. But
right,
and the conclusion simply follows.
Dreams, they feel real while we're in them, right? It's only when we wake up that we realize something is actually strange.
Right. I don't really. I mean, I suppose it was meant to sort of feel profound having the quote in there, but
and then Gandalf.
but I don't really know what it added, because what is dreams? I guess he's saying this is kind of like a dream, so it feels real. I don't know. Again, more sort of.
Yeah, interestingly, this is what some of the Eastern people, well, I shouldn't say Eastern people, but like adherents of Eastern philosophies say. Yeah, this is a dream that you need to wake up from. Anyway, so it's a bit Eastern there. Let's look at cosmic consciousness argument, where it gets. This is more philosophical, but it gets. It gets more. Whatever you want to say it is, it's more
it
that.
Gets more.
It gets more. I don't know what predicate to use, but it's more that.
I'm not ready for it. I'm. It's almost a good argument. Points for originality. Yeah, I guess
I said that at the start. Points for originality. I agree.
Yeah, we'd agree with that.
The key premise there that the universe is a simulation. I think I'm just not really convinced at all that I should believe that. Also, that the issue that is this really God? I'm not really convinced of that either.
I don't even know if I was convinced of almost any of the premises.
Well, I'm being generous.
Simulation.
I could grant the others.
I could grant one if he modified it. I mean, a simulation runs on a computer, or whatever, or a mind. Right.
We need a good intro like that. Where's our fancy intro?
Well, you say that, but a viewer has emailed me, and I've given them a couple of pictures and things.
Oh.
So maybe we'll have one.
Nice. Oh no, are we going to get one like the radio show of Frank Turek,
Trinity.
where he?
All right.
No, Frank Turek. You know, where he's going all these like snippets and it's like yelling at people.
If somebody tells you asks you what's true, it says there is no truth. What do you tell them? Is that true?
We need one of those.
Francis Bacon. Have you seen the Francis Bacon meme?
I don't think so. No.
I'm sorry for the time, but this is so important that I'm going to have to quickly find it.
Francis Bacon.
Let's get this. Come on.
When I was young, my father said to me, "Oh, do you want to read it?"
No, it's okay. You go.
When I was young, my father said to me, "Knowledge is power." Oh, I've lost it. Oh, knowledge is power. Francis Bacon. For more than a decade, I wondered over the meaning of the second part and what was the surreal linkage between the two. If I said the quote to someone, knowledge is power, Francis Bacon, they nodded knowingly, or someone might say, knowledge is power, and I finished the quote, Francis Bacon, and they wouldn't look at me like I said something very odd, but thoughtfully agree. I did ask a teacher what did knowledge is power, Francis Bacon mean, and I got a full 10-minute explanation of the knowledge is power bit, but nothing on Francis Bacon. I then prompted further explanation by asking Francis Bacon in a questioning tone. I just got, yes. At 12, I didn't have confidence to press it further. I just accepted it as something I never understand. It wasn't until years later I saw it written down and the penny dropped.
Yeah.
Oh dear.
So there we go.
I've reached a new phase of consciousness with that meme. That's impressive.
So yeah.
In several videos, we have looked deeply at the evidence the universe is emergent and consciousness is fundamental, and we've hinted to the theistic implications. So building on this data, I want to present a formal argument of how, logically speaking, this evidence leads to theism. Mikio Kaku has referred to this line of reasoning as cosmic consciousness. One minority point of view.
Is he a deist, by the way, Mikio Kaku? Is he a deist?
Not that I'm aware of, but I mean, I haven't really looked into it.
I just remember his like Physics of the Impossible book or something like that I read as a teenager, and then
yeah, I think he's one of those people who writes the same book over and over again.
Yeah,
just
and like appears
titles.
on MythBusters like from time to time or something. Like,
yeah.
Is there must be a cosmic consciousness reading the universe. Objects spring into being when measurements are made, and measurements are made by conscious beings. Hence, there must be a cosmic consciousness that pervades the universe, determining which states we are in. Some, like Nobel laureate Eugene Wigner, have argued that this proves the existence of God, or some cosmic consciousness. Building on that same logic behind Wigner's reasoning, I would like to present the cosmic conscious argument. Premise 1. Contingent minds either have a personal explanation or a natural explanation.
this is sounding like Swinburne's argument for God's existence from so far. Let's see.
I've borrowed this premise from J.P. Moreland's argument from consciousness. The logic of this premise flows from theories and philosophy of mind. Some argue the mind is a product of natural...
I bet J.P. Moreland is copying it from Swinburne. In what's his Swinburne personal or natural? Like Swinburne has this massive God is the simplest explanation. Knew it. Explanation in terms of substances having properties. Explanation of existence. two kinds of explanation. I've argued that.
Yeah, Craig appeals to this as well. I don't think I've read this specific paper, but I've seen it before. We'll need to address that in the future because I think that personal explanations when it comes to God just don't work. They're pretty controversial philosophically, and I mean, I would say fringe. I guess I'm biased there, but that's not to say people don't defend them, but they're not the mainstream.
Yeah, so we can look at that at a different time. But I think
actually
this is the
sorry, go ahead.
source. Well, just saying that I think this is the source of, like we're getting like third degree kind of copying of ideas here from Swinburne being the source of that personal natural explanation, and personal's better for whatever reason. Yeah, sorry. Do you want to?
I was just going to say that something that would be cool at some point to do in some bad apologetics would be to work, well, not in a single one, but to do a chapter of each for the going through that Blackwell companion
The
to
natural.
natural theology. We've already basically done one because basically that was the nice. I don't have a physical copy, but I've got a digital copy. How much did that set you back, by the way?
Oh, I can't remember. I think it was like 30 quid, 35 quid, something like that.
That's about 70 Australian dollars.
When
That's not trivial.
When I was
but
still a
it's not massive.
theist. When I was still
you
a
bought it
theist,
then?
no. Yeah.
How much of it did you read while you were still a theist?
Well, I think I only read the Kalam when I was a theist. Yeah.
Don't tell me you read the whole chapter, even the bits about the different, theories of quantum gravity and all that stuff.
I can't remember exactly
all of those bits.
I just remember. I remember because on weekends I was spending like 3 or 4 hours out evangelizing on the streets. So I remember in the mornings I'd read some apologetics and then I'd go and use it on people in the day. So who knows what went into my mind in those times.
Interesting. Yeah, but anyway, that's a pretty good resource. So it'd be good to work through that. Anyway, but for the moment, quantum consciousness.
Natural processes. Basically an emergent process or something similar from the chemistry of the brain. The alternative, which also encompasses a multitude of views, asserts the idea that consciousness is fundamental as it is and cannot be reduced to smaller parts, like chemical processes in the brain.
When I asked Bernardo Kastrup, he described his idealism as a naturalist. I mean, I guess you'd probably reject that. I don't have it seems kind of alien to me to describe it as naturalism, but it is like the naturalist himself might potentially say. I suppose he wouldn't be a subjective idealist; he'd be an objective idealist. So maybe there's something different, important there.
I'm no expert on idealism, but I mean, usually that's seen as a competing view to naturalism, but there's always someone who tries to make some combination of things work. So
if consciousness is fundamental, meaning it cannot be reduced to smaller parts, yet we came into existence at a point in time, that would infer a personal explanation for the origin of our consciousness. To be conscious means to be a self-aware mind or agent. If the mind was not built by smaller parts and is fundamental, then it must come from a personal source, which produces other persons. In other words, if reductionism is false, and the mind cannot be reduced to smaller natural or informational parts, then it must come from a source as is. Consciousness.
Why can't the mind be made up of? Why can't the mind be formed by a combination of non-mental, non-physical sources? Why is he just ruling that out?
Yeah, it's interesting because I was just thinking. I mean, I know we addressed it when we've addressed his views of the soul and so forth, but it just seems to me that if you're committed to this view, you would never in a million years predict cases like Phineas Gage, with the railroad spike through the brain, or how would you ever get that from the if you're committed to the view that consciousness comes from a source and is not reducible to the physical constituents, why would you think that removing certain parts of the prefrontal cortex or whatever would reduce someone's ability to plan into the future and make risk decisions about risk and so forth?
This is where you get over determination problems, because you want to say, well, the hardware that the soul uses to make its decisions is broken, but then you also want to seem to they also want to say that where the mind can do this separately from the brain as well. So it's sufficient. It's a sufficient cause for the effect, but also the brain is somehow necessary as well, or at least is sometimes necessary. I don't see how you can really make that make sense.
Yeah. another thing to think about long and hard.
Yeah, I
at
mean,
some
maybe
point.
Alan's asking why can't consciousness be physical? Obviously, as a materialist, I think that it is, right? But I'm just like, as Nathan says, we've already talked about that at length. I don't want to go through all that again here.
Yeah.
I'm just sort of thinking about, well, what other possibilities could there be? I'm not convinced that it has to be material or it just has to be irreducible. I don't see why it couldn't be made up of sort of interacting non-physical but still non-mental substances or forces or something.
Yeah.
I just don't see how you can just rule that out.
One thing I do want to just quickly point out, though, is that the usual arguments are from the impossibility of phenomenal consciousness being tethered to the strictly material. Now, one thing I want to point out about these, like Mary's room and so forth, is that they are deductive arguments. So similarly to the problems of these deductive arguments that we see with the theists, right? It's gonna be this problem of that the premises contain the conclusion. So a naturalist, so someone who thinks that consciousness or qualia or whatever just is reducible to some material thing, is just never gonna like accept one of the premises if you get to the conclusion that therefore that all the physical facts don't contain the fact about qualia or whatever the conclusion of like Mary's room is, or same with like these zombie thought experiments and things. It's like so you can have all the physical parts without having consciousness. Well, of course, like the naturalist is just going to reject one of the premises. It's just deductive. It's just a recombination of the conclusion in some way. And the question is, how do we get from facts that we all agree to drawing out conclusions that seem to be the most plausible based off of the things that we can be certain about. And I think there's something else that's interesting when we think about those sorts of intuitive first person things, because it'll often be like these indiscernibility of identicals type arguments as well, where it's like, oh well, me tasting coffee or whatever it doesn't like weigh anything, whereas like neurons weigh something or something like that. So it's got different properties. But it's like, like my thoughts about future planning don't contain any description about like me having a prefrontal cortex, right? But removing my prefrontal cortex is gonna make me unable to like do future planning. It's not it. The way that the description is, what it's like to be that description doesn't have to contain a description from a third person perspective of the thing. And that's not what the materialist is committed to. So arguing in that way is always going to sort of contain some issues, both in terms of like basically question begging of worldviews against each other, which we're just not going to be able to make progress. And in terms of sort of from an internal critique perspective, I think not acknowledging what the naturalist is actually saying about the way that consciousness works and is.
Yeah, you make excellent points there, and I think that's why these sort of deductive arguments don't work, because they're essentially always just going to contain premises that the naturalist or materialist is going to reject. I think inferences to best explanation are better because they don't work deductively like that. Although, of course, there is some subjectivity in assessing that. So
it's just affirming the consequent, James.
No, I mean, I think that's essentially how we reason most of the time. So I'm generally a fan of that approach. But then you do have to be able to provide an explanation that accounts for something. And I think that's where the non-materialist views really fall down, because they're not able to actually explain anything. They want to use the deductive arguments to rule out materialism, but don't actually have anything very sensible to replace it with, for the most part. It's like we talked about this in the NDE episodes. They want to show physicalism is wrong, but don't have anything to replace it with. And the thing is that because the deductive arguments basically don't work, because there's always premises you can reject, they're going to need to give an inference the best explanation or something similar to that. And that requires an alternate theory.
Yeah.
So I don't think that there's a real plausible way around that.
Of consciousness, which would be personal by definition, since we are personal agents. Some might try to assert the various forms of panpsychism could be a third option here.
He said personal by definition, but on there's some people believe in like an impersonal conscious, like the NDEers, for example. A lot of them believe in like an impersonal conscious soup or something that we sort of go back into. Yeah,
that's true. There's a lot of assumptions about the nature of consciousness and mind that are going on here. I mean, because can you have non-personal minds? It seems you can, right? Like, cockroaches have a mind of sorts, right? And so there's all sorts of assumptions here.
But I would argue panpsychism is incomplete. If consciousness is in all material things, we still need an explanation of consciousness and why we are conscious, whether that means our conscious minds are produced by smaller parts, or that the conscious universe emerges from a source. It is not enough to simply say that everything material is conscious. We still need to explain why, even if panpsychism is true. And the options we are left
pause right there. Pause right there.
Smaller part.
So just take that exact sentence and say and substitute the words. I've already forgotten the sentence now. But take out when he's talking about like panpsychism or material or whatever, and just substitute that with immaterial, like what is it? Irreducible immaterial mind. Like, we still need an explanation of consciousness and why we are conscious. Just because you say that it's an immaterial, irreducible mind doesn't mean we still don't have an explanation. You've just said that it's this thing. I think
that's what I'm saying is happening.
He's
just describing. He's just describing the phenomena and saying, "Look, there,
exactly.
I gave it a label."
How do we have consciousness? Why are we conscious? Oh, because it's produced by an irreducible immaterial mind. Well, it just doesn't answer the question.
It's produced by a conscious thing. Because there's a thing with consciousness, of course. Like
that's why I say that there's just no explanation there.
Yeah.
And the options we are left with is it is reduced to smaller parts or grounded in a personal source. Most forms of panpsychism, although not like typical materialistic or naturalistic reductionist views, seem to try to argue consciousness is built by smaller elements of consciousness, inherent in all matter. But this has been a problem that goes as far back as William James, and it is known as the combination problem. If at the micro level, every atom has its own consciousness, and these micro levels of consciousness combine to form our consciousness, that would still be a reductionist view, and suffer from the same problems of how conscious experience can be divided into smaller parts. Plus, despite popular myth, most forms of panpsychism actually fall under realism. As Charles Hartshorne said, in contrast to idealism, as the term is often used, panpsychism is not a doctrine of the unreality of the spatio-temporal world, perceived through the senses, or its reduction to mere ideas in the human or divine mind. The constituents of this world are, for panpsychists, just as real as human minds, or as any mind. Indeed, they are minds, though in large part, of an extremely low subhuman order. Thus, panpsychism is panpsychical realism. Realistic both in the sense of admitting the reality of nature and in the sense of avoiding an exaggerated view of the qualities of its ordinary constituents. Souls may be very humble sorts of entities, for example, the soul of a frog, and panpsychists usually suppose that multitudes of units of nature are on a much lower level of psychic life even than that. Panpsychism also contrasts with the monistic tendencies of much of idealism. It does not depreciate individual distinctness, and in its most recent forms, it admits some degree of freedom or self-determination, even in the lowest orders of psyches. Insofar, it is pluralistic. This pluralism of panpsychism is evidently connected with its realism. So panpsychism would simply be another type of reductionism and would be most similar to a naturalistic origin of consciousness. Premise 2. Quantum mechanics and other fields of science imply the natural universe is emergent from consciousness. Now, since I have several videos arguing for this, I will not defend this premise here, but simply refer people to my other videos where I argue scientific evidence points to this conclusion. Therefore, we reach conclusion 1. The natural universe cannot be the explanation of contingent minds. This follows from the logic of premise 1 and the evidence that is used to support premise 2. If the universe is emergent, as we have argued, then everything physical or natural is emergent as well, and therefore consciousness could not have been an emergent feature of the natural universe, and the explanation of consciousness cannot be something natural, meaning emergent from matter and space-time. Premise 3. The explanation of the existence of conscious minds is personal. Premise 4. The personal source is what we call God. This premise is not too controversial, since no one is using this premise to say it is a specific God, but simply a personal source, which is the explanation of consciousness and who we call God. and thus the final conclusion, therefore, God exists, and is the reason contingent conscious agents exist.
So let's just pause on that argument. So we talked a bit about premise one. Not entirely convinced on that, but I can grant that for the sake of argument. Obviously, I don't accept premise two. We've spent a lot of time talking about why his arguments for that aren't not very good. I think conclusion one does follow from the first two premises, as far as I can tell. Well, actually, not quite, because he says cannot, which is a modal claim, whereas premise two is just that it does not. So maybe I'd modify conclusion one to the natural universe does not explain contingent minds, or is not the explanation of contingent minds. Because I'm not sure that the premise actually says that it can't be. I mean, maybe that's nitpicking, but I think that there is a subtle difference there. So premise three, the explanation of the existence of conscious minds is personal. Oh, yeah, so he's deriving that from... where does he get that one from? 1 and 2, he says. But doesn't conclusion one come from 1 and 2?
He doesn't deny any of the disjuncts. I don't know. Yeah. Where does he deny
personal.
the disjuncts? To get
well, it's conclusion one, right?
The natural universe cannot be the
contingent minds is either personal or natural. It's not natural.
Oh, necessary minds.
Therefore,
I see what he's saying. Yeah, but he means by contingent minds. Contingent minds either have a personal explanation or a natural explanation. So he would have to deny that they have a natural a natural universe cannot be the explanation of contingent.
Yeah, that's
okay,
conclusion
so denied
one.
it there. I see. Yeah, okay, I'm with you.
Which again, I don't think it follows from premise 1 and 2. I think it should be modified slightly to say does not or but that's a minor modification.
Yeah, how did he get conclusion 1? Quantum mechanics and other fields of science imply the natural universe is emergent from consciousness. The natural universe cannot be the explanation of contingent minds. Why? Where does that follow from anything that's been said before it?
Well, yeah, I think there's probably suppressed premise here now that I think about it, because he's saying that so the natural universe is emergent from consciousness. If the natural universe is emergent from consciousness, then contingent minds don't have a natural explanation. I think would be the suppressed premise there. Because otherwise, if so, it would be saying like there's natural universe, consciousness, and then like a natural universe under that somehow. I mean, that's plausible enough, but it's true that he hasn't really shown that. So, yeah, I think that it could do with some tidying up there.
And then 3 to 4 just doesn't follow.
Premise 3 doesn't follow from 1 and 2. It follows from conclusion 1 and premise 1, because that's the first premise is a disjunction, and then conclusion 1 is negating a disjunct. So then you're going to get the other disjunct as a conclusion there, but. I guess 1 and 2 could be either conclusion 1 or premise 1, so that's a bit unclear there. So I think that works.
I'm saying that we've got the same problem of the this is what we all mean by God.
Premise 4 I think is not true at all, and he said that's not controversial, but I think it's very controversial because God has a certain set of properties the way that's typically defined in like classical theist sense or whatever, and it doesn't really seem to have much to do with just being the explanation of contingent minds, which is all it's doing here. Like that's a very narrow conception.
I think on a really, really charitable interpretation, you can say that this is valid, but it's difficult to pull the valid form out of it. Like you've got to do a lot of interpretive work, which you shouldn't really have to do with a deductive argument.
Yeah,
the point is
it needs a bit of work. I mean, I get the idea of it, but I mean, so if I'm charitable with a bit of reframing, I'm still going to have issues with premise 4, but I think it could be, you could restate premise 4, like maybe so this personal source, I don't think you can say it's what we call God, but maybe it is an aspect of God or a function of God or something. I don't know what you might say. Identity seems a bit strong there because of the properties that haven't been established, but
maybe
the main premise I have an issue with is premise 2, clearly, I think.
Yeah, maybe like, like something like, if a mind gives rise to all contingent minds and simulates the universe, then it's worthy of worship or something like that. Or,
Yeah.
Yeah.
Because I don't know exactly how you can establish. I mean, you might try to establish it as a greatest being type argument, or through accumulation of properties, which is sort of how Craig attempts to do it with his multiple arguments that establish different properties. Although you've got to establish how they all come together on the same being. But here he doesn't try to do that. He just sort of gives one property, which is not even a standard one, really.
And I guess you would expect. Well, just that you couldn't really guarantee that you weren't worshipping like Rick from Rick and Morty still, I don't think.
I did a debate the other day with on the what is it, Theology Unleashed channel about the problem of evil. And interestingly, the Hare Krishna guy that I was talking to actually denied that God is the source of contingent minds. Although he said he sustained them but didn't create them in some way. So that's interesting. But I mean, IP might reject that, but the point is that at least there's someone who has a conception of a theistic God who would reject that God is the ultimate source of personal mind. So, I mean, there's clearly an issue with premise 4 there. Anyway, it's a bit of a sloppy argument the way it's formulated, I think. But premise 2 is really pretty controversial there, and I just don't see that the arguments he's given for it are good.
I mean, that's most of the difficulties come from the form, but then you look at the actual soundness of it, and it's like, I mean, it's not even clear to me that this is true, personal explanation or a natural explanation. I mean, what if you think a personal explanation is a natural explanation, you know, just in a different suit? You're going to get...
I guess premise 1 is still true, but but as I mentioned, it seems like that may be a false dichotomy because you could possibly have other possibilities as well.
I've still got this book to read, which is where this is where Swinburne gets his ideas from. About this is what he uses as the basis for personal and natural explanations and distinguishing between them and stuff. And I've not.
I'm just holding this up because I haven't done so this stream. So check it out. It's not really relevant to anything.
So I'm saying I don't really, but let's just grant 1 for being charitable. 2 is we spent all that time saying it's not true. The first conclusion, it's not clear that it actually does follow from the premises given, but okay. The explanation of the existence of conscious minds is personal from combining 1 and 2. Maybe. I mean, why is it a premise if it's just a combination of it? I don't even know. Yeah,
that's a good point. It's not a premise. That's a conclusion, and it follows from what was it? Premise 1 and conclusion 1. It doesn't follow from premise 2. Premise 2 is used with premise 1 to produce conclusion 1, which then conclusion 1 in combination with premise 1 is used to derive premise 3, which isn't a premise. It's the more I look at the form, the more problems I find. Let's just move on. I'm getting upset now.
Yes.
If consciousness is fundamental, then it leads us to the conclusion God exists as the reason for our conscious existence. Now, what if someone tries to avoid the argument by appealing to solipsism, which is the belief that only your mind exists and everything else is a product of that? Well, like panpsychism, I would argue this idea is incomplete. Physicist David Deutsch, in his book, argues that solipsism is unsustainable on its own. Logically, it must collapse to something else. Deutsch argues that it is realism, in that because the solipsism...
Deutsch is a physicist who denies... who thinks probability is all epistemic and denies that it exists in reality and stuff like that. That's all my understanding of him. Is that right to you?
I don't remember a lot about David Deutsch. I just remember vaguely that he believes some weird stuff, which is not not very charitable, I suppose. But I mean, yeah. I mean, I'm not a solipsist, so I'm not really going to push this argument. But I have a question for IP. Is God a solipsist? Because if everything is a simulation in his mind,
does
that mean that he should be a solipsist? I don't know.
Yeah. Like in what sense do the other minds really exist if they're completely dependent upon God sustaining them? you know, like they're a subset of God. It's like a disembodied avatar that's forgotten about itself inside of God. But in what sense could you really say, you know, that is its own distinct thing in the same way that, you know, you and I are distinct? Like, there's no way really of saying that like your mind or my mind is like dependent on the other one for its existence. But so we can say there's this meta realm to each of us that we're both nested in. But how could you do the same thing for God and the beings who are simulated? Does IP do this in any of the videos, to your
I don't think he
knowledge?
mentions it. I just something that occurred to me, that it seems like the way he defines solipsism is that God should be a solipsist, which, I mean, maybe he'd disagree, but it just seems a bit odd.
Yeah. So potentially, from a theological point of view, potentially heretical to Christianity is, I suppose, what I'm getting at.
Well, I'm pretty sure that theistic idealism is not a mainstream Christian view, so I don't know if it would count as heresy, but yeah. Which actually, that's one thing that strikes me as odd about the large number of fans that IP has, because, I mean, there's definitely some really non-standard beliefs that he has. I don't know why he doesn't get more pushback from Christians.
Well, isn't the distinction between creator and created stuff pretty fundamental? I mean, like, I know there's like weird philosopher people who have like held it's the same or whatever, weird Neoplatonists and so forth. But like in general, that has been really important to Christian theology. The idea that God is distinct from the creation. Yeah,
and that's kind of important for the incarnation as well.
Yeah,
God
right.
Into creation.
Kenosis.
And I think that I think that IP's idea kind of weakens that. Although, I mean, I guess you can. He enters into a simulation, but somehow that's just, I don't know. He enters into his own mind. I mean, it just gets a bit weird.
Yeah, yeah.
Well, the incarnation is already weird, but like it gets even weirder.
Yeah.
Didn't create his own mind or is able to control what he experiences. Therefore, the solipsist, just as the external world is the uncontrolled parts of the mind the self or conscious agent is exploring. He writes, the solipsist, who believes that nothing exists other than the contents of one mind, must also believe that that mind is a phenomenon of greater multiplicity than is normally supposed. It contains other people-like thoughts, planet-like thoughts, and laws of physics-like thoughts. Those thoughts are real. They develop in a complex way or pretend to, and they have enough autonomy to surprise, disappoint, enlighten, or thwart the other class of thoughts which call themselves I. Thus, the solipsist explanation of the world is in terms of interacting thoughts rather than interacting objects. But those thoughts are real and interact according to the same rules that the realist says govern the interactions of objects. Thus, solipsism, far from being a worldview stripped to its essentials, is actually just realism disguised and weighed down by additional, unnecessary assumptions, worthless baggage, introduced only to be explained away. Now, I agree solipsism collapses as
Sorry, are we
something
talking about solipsism or theism
I
here?
disagree.
Ooh,
Yeah. No, yeah, I was also thinking that. I was like, how can IP like read this stuff and see it as like a good argument against another worldview that he understands, and then like do the exact same thing with his like worldview? It's really, really weird to me.
Well,
It collapses to realism. I would argue it collapses to theism. If solipsism is true, then the external world is an illusion or emergent from one's own mind. But that doesn't mean it would qualify as realism.
Just looking at this diagram, so like this would be like God, right? And this would be like God's self. And
yeah,
then
that's exactly.
this would be like, you know, the universe being simulated or whatever. And then there'd be like you. So it's just like solipsism, but with different with God. It's just the same problems, yeah.
All it agrees with realism is that thoughts are real and governed by rules the self cannot control. But it denies there is something other than mind and thought processes, which means it is not realism. In fact, if solipsism was true, the aspects of experience the solipsist cannot control are still mental and non-physical. So there is a more powerful aspect of the solipsist mind that is in control and governing the experience, which would be godlike in controlling reality for the solipsist. Thus, since solipsism still means there is a mind in control of experience and creation that is not you, that would more align with...
Wait. Did I like blank out for a second? Why is God
Well,
inside
I must
the
have blanked
self?
out as well. I don't understand how this worked here.
Why is the godlike mind inside the self mind? Oh, maybe
It's like, what's determining how the physical world works or something?
is he say like this is like Satanism, where like God is like an ideal in your mind, like
self-worship.
Levian
Yeah.
Satanism, or yeah.
with theistic idealism instead of realism. Just that the godlike mind in control is just part of the solipsist mind the self cannot control and is subject to. So even if solipsism was true, and I don't think it is reasonable to assume other people are not conscious, it would not escape the theistic implications. Another objection presented against the cosmic conscious argument is given in the quantum enigma. God may be omnipotent, but we note in the spirit of this limerick, he is not omniscient. If God's observation collapses the wave function.
Here we go.
In
I
the
told you
spirit
talked
of
about
this limerick.
I feel like there's context that's missing here because it doesn't make any sense given what they've said.
What?
So,
Where's the limerick?
you probably should have just cut that out of the quote because I'm guessing that it refers to something that we're not seeing here.
Yeah,
but anyway,
I mean, I think that's probably right, but it's just so strange. Like,
yeah, I
like,
read that as
what
well.
alternative universe have I just landed in?
If God's observation collapses the wave functions of large things to reality, shouldn't that be in reality? Quantum experiments indicate that he is not observing the small. Yeah, because
It
we
rhymes.
we collapse things.
Of large things to reality, quantum experiments indicate he is not observing the small. The point they are making is that in quantum experiments, the collapse of the wave function is...
Oh wait, have I missed an important point here though? Because I was saying that God, like, why isn't God collapsing all the wave functions? And I
Yeah, that's what he's addressing.
It's just too small for God to see. Is that basically it?
Well, I think that's what they're sort of jokingly saying, but IP's sort of trying to give an answer to that, I think.
Yeah.
The point they are making is that in quantum experiments, the collapse of the wave function is caused by our observations, when we obtain knowledge of the system. If there is a necessary omniscient observer who knows all, then he should have collapsed everything. So he
Right.
must not be always observing, so that we can observe experiments and cause collapse of the wave function. However, the problem with this objection is it assumes God is a contingent being, like us, who has to obtain knowledge in space-time. First, God does not physically obtain...
Okay, so just before, so something about God's being a necessary being rather than a contingent being somehow means that his causal powers don't interact with his observations don't cause quantum disentanglement.
Yeah, even though earlier IP said that an observation is about knowing. And you remember he said it's about knowledge and knowledge
Yeah.
requires a knower? So
Yeah.
God knows it, right? It doesn't matter how he knows it. IP didn't say, well, it's about how you know it, because in fact, that's closer to my answer, right? It's physical interaction with the system, physical disturbance of the system that collapses the wave function. But IP rejected that, and he says, no, it's about knowing the state of the system or something like that. But God knows it. So shouldn't he collapse it? Where does the fact that God is necessary come into it? He doesn't explain this at all.
Mm. And then what was that? The second point he just said.
Who has to obtain knowledge in space-time.
Has to obtain knowledge in space-time.
Yeah.
So, yeah. So
again, what does that matter?
Yeah. Why somehow the obtaining of the matter of the knowledge being within space-time causes quantum disentanglement? Like, what's the truth maker for that? Like, in virtue of what is that true? Like, do we need like some Platonic forms of like IP's metaphysics that like have causal powers? And I just don't understand. And then I've no idea.
He says that God doesn't collapse the wave functions because God is necessary and God doesn't attain knowledge in space-time. Obviously, those would be true of God, but he doesn't explain why they're relevant to him not collapsing the wave functions. It's just like a red herring. It's like, hey, look at these things that are different about God. But he still knows it, right? Isn't that what's important for collapsing the wave function?
Yeah, because
it's like, no, it's
we
actually
need
knowing
mechanism.
it in space-time by a contingent mind. And it's like, well, where did that come from? Why is that important?
So if IP actually offered us an explanation of what's going on when we as contingent minds in space-time observe quantum disentanglement and, like what that mechanism is and what's involved, then maybe he could say, and those features aren't present in God's knowing because here's what's involved in God's knowing. And then maybe it'd become plausible, but it's just a complete non-answer. Again, he's just describing like facts that he wants to be true, which is that conscious observers cause quantum disentanglement, but God consciousness doesn't. And he's just basically just restating that, which are just the very things in question again. Yeah.
First, God does not physically obtain knowledge like we do. He doesn't experience things in a physical world and therefore does not cause collapse. God would be outside of space-time altogether and contain all the information of space-time in a single timeless instance.
And why does that cause or not cause disentanglement?
So he would not be in a state without knowledge.
And furthermore, how could you tell the difference between this God existing or not existing? Like, it doesn't interact in...
then we wouldn't have quantum mechanics, because all the states would be collapsed, right? So I guess we better hope that God doesn't just look all of a sudden, because then the quantum mechanics just stops working.
Good point.
That would be a bit concerning.
Knowledge of collapse, then experience collapse as going through a progression of time like we do. God would simply have knowledge of all instances of time at once, and therefore know each instance equally. There would never be a time before, from his perspective, where he did not have knowledge.
I guess what I was saying is, it just seems like, from my point of view, like he's just like inventing something that doesn't. He's like describing nothing and giving like nothing properties and stuff. And I couldn't think of like a good way to describe how it seems like he's doing that. Like, because he's like, oh well, God knows it, but he doesn't know it in this way because that would be a problem. And it's like, it just seems to me it's kind of like when people talk about souls and they're just like providing all these random descriptions, but like
it's just super ad hoc. It's like, it doesn't have anything to do with anything that he's justified or being relevant. It's just being pulled out now to answer this specific objection. Another point is that this is supposed to be a simulation in God's mind. So, like, it's there in God's mind because that's where the simulation is. Like, that's what form it has, if you want to use that language, right? But somehow he doesn't know it, even though he's supposed to be omniscient, and therefore knows everything that's in his mind, presumably. But somehow he does, like, he has to know it and not know it at the same time.
Well, James, you don't have to know. You don't have to know how much your neurons weigh to be able to taste a strawberry.
Well, God does, though, because he's supposed to be omniscient. I mean, this is the problem. He should know all these things.
That's true, actually. Yeah. Well, maybe IP is going to become an open theist. I don't...
of the system. So God's timeless nature explains why he does not cause collapse in quantum experiments. There is no state of being before something. Second, God is also not a physical being, observing all of space-time, like how we observe physical reality. God would be an immaterial conscious mind, and having a conscious experience of physical reality, independent of ours, would not be necessary. God's focus would be on us.
But aren't we immaterial conscious minds? He says God is an immaterial conscious mind, unlike us. But isn't that what we are according to IP? So what's the difference?
And why does God incarnate if he doesn't need this? If he's self-sufficient without it, why is he doing that? Why does he...
When God incarnated, did he acquire the ability to collapse wave functions because he's now...
Mary. God Mary.
So, but like maybe that's why he didn't know about evolution, right? Because he had to restrict, because otherwise he'd collapse everything in the universe as soon as he incarnated, right? And then everything would stop working. So he's like, "Oh, I better not observe these wave."
He found out what it's like to collapse a wave function.
In other words, physical reality would be a creation for us, not something he has to see or be a part of. He can manifest in his own form for specific purposes, But when he is not, his omniscience would not be dependent on an independent observation of physical reality. He would simply know what we choose and experience in each moment of time, in a single timeless instance from his perspective. So there would be no issue with why we observe collapse in quantum experiments. God is simply outside of space-time and is not going through time as an omniscient being.
There's no issue because I've just given you a description where there is no issue. So I guess
He doesn't explain why God needs to go through time. The issue should be God knows it. Knowing is what causes collapse according to IP. Therefore, God should have collapsed everything. Precisely because he's outside of time, so already knows this. He doesn't address this. He just says, oh, but God's outside time. So somehow that addresses the point. But it doesn't. He still knows it.
the only part of his explanation of conscious observation causing collapse is that it's conscious observation. That's all he's given us. And then he's only just come up with these ad hoc postulates as objections have arisen rather than modifying, rather than thinking something might be wrong with the
He can
original.
always just say, well, that's just the way it works. God's mind just works differently. That's all there is to it. It has different causal powers. And that's really the problem with these explanations. They're just ad hoc. You can always just assert that these mysterious forces or entities work that way. And there's no way to disprove that. But it's just a fault of the explanation because it's ad hoc. And it has to invent new aspects or constraints to explain every problem that it comes across.
Yeah, because if that's a valid way of...
He could come up with something to explain this, but the problem is not so much that he can't come up with it, although he hasn't here, but it's just that you always can, and it's just going to be more and more ad hoc and a worse explanation as a result.
And if we're allowed to make inferences that way, if we agree that that's a good way of doing it, then it's like, well, why are we going with this explanation as opposed to the machine elves? You know, the conscious, non-conscious machine elves that simulate the universe.
Yeah, I mean, why can't I respond to the hard problem of consciousness just saying, oh, that's just how neurons work. They just do that. They just produce consciousness. Like, how is that a worse explanation than, oh, that's just how God works. He just doesn't collapse away from it.
Right.
You see what I mean? What source for it could bring up your thing. It's exactly that. The source one.
His omniscience.
You know, the thing at the bottom of the screen.
Essence.
Sorry, you want
the text. No, not on the video. The one you bring up for the stream.
Oh,
the green thing.
Sorry,
Come on, chat, you know what I'm talking about.
I've gone insane. This one?
What? No, not that one. That's the one. Yeah.
I thought you meant this one, right? This one. Just cover the plaster the screen in ads. At unreasonable faith.
Oh, that reminds me, we're coming up to an ad break.
Yeah, hold that thought, James. Hold that thought, because down.
It's so good. Oh dear, we're getting a bit distracted. It's 6 hours in, and so we've got to finish this one. We're nearly there.
Yeah. Just in response to Digital Hammurabi, you've not missed the Naram-Sin video. I'm going to do it if it's still in the Google Docs. Minimal facts for why Naram-Sin was a god, based off of some of Digital Hammurabi's research.
I don't even know who Naram-Sin is, so.
Well, there's 5 indisputable facts that all scholars agree to about Naram-Sin.
So, given the evidence for an emergent universe and the fundamental nature of consciousness, the conclusion simply follows. The evidence is too overwhelming to deny an idealistic, dualistic picture of reality. And the conclusion.
Come on, IP. Like, we're trying to give you the benefit of the doubt with some of this stuff, but when you say things like the evidence is too overwhelming, it's just like, it's just.
He says the William link, right? He's like, and the conclusion simply follows from my invalid argument.
Logically and inescapably.
Yeah.
It just really loses credibility when you say things like that.
Yeah.
I don't think you'll ever hear me say things like that, unless it's like the world is round or something. But these things
I
are
don't
not
even
that
think I'd
clear-cut.
say that, like, because I'm just not that committed to the world being round. Like that, I'd go like, you can't escape from my Romans 1 round Earth. Like,
why do people cling with such ferocity to belief in a mind-independent reality? It is surely because if there is no such reality, then ultimately, as far as we can know, mind alone exists. And if mind is not the product of real matter, but rather is the creator of the illusion of material reality, which has in fact, despite the materialist, been known to be the case since the discovery of quantum mechanics in 1925, then a theistic view of our existence becomes the only rational alternative to solipsism.
Right. Well, that's us
Boom.
told. What's the next one? The emergent universe.
Yeah, so this is the peak of what we've been doing. This is the coup de grace, the piece de resistance, the alpha and omega. So I saved it till last, of course.
Oh God, the music's. I can't pause it because my computer's getting overwhelmed trying to load it, and
all the gravity is slowing it down.
Yeah. Yeah, the gravity of the computer is slowing down. Right.
All right, so this is where, when we get through a little bit, this is where I'll talk about the, I've forgotten the word for it, the holographic principle and how he applies that. Because he mentioned it before, but only briefly. It goes into more detail here.
He's not going to bring new physics into it, is he?
Well, yeah, it's quantum gravity, so it's a new physics.
Oh. Right, let's do it. Underneath the molecules, atoms, and particles, there is another layer of reality that is coming to light. It is a layer that is based on information. Underneath.
Yeah, well, this is the idea of the emergent universe.
Yeah.
Yeah, we'll see what it's like. I mean, yeah, let's just keep going.
I'm just saying, like, from my understanding, though, I'm not going to understand the high-level physics stuff, but it's like you can just make information out of anything as long as you interpret it a certain way, and like, you can just
see, this is the thing. Information is either defined in terms of information theory or it's not well defined. And if you're using the information theoretic notion, randomness has the most information, right? So this is when I don't understand when people talk about you can't produce information or whatever. Like, it's very easy. you just like roll a dice and you're producing information by the series of outcomes. Order actually reduces information relative to randomness because there's structure to it, so you can compress it. So there's actually less information there. Right. This is the notion of information theory according to what information is according to information theory, which we use for encoding and computers and things like that. So when other people talk about information in the context of evolution or origin of life or here the universe, I don't really know what they're talking about. It's because it's just not defined in a way that I understand.
I'm not laughing at Alan's comment.
Many today think the universe is only built by tiny bits of matter, and all that exists is different arrangements of these particles. All your hopes and dreams are nothing more than the products of tiny atoms bouncing around. The fundamental nature of the universe and everything within is material, and all we see and know is nothing more than the emergent features of these.
Again, is this rhetorical thing where, like, so just change material deterministic, whatever he's saying, just change it for quantum and irreducible mental. All your hopes, beliefs, and desires are just irreducible quantum stuff. They're
just a dream in God's mind.
Yeah, like what
why is one better than the other? I don't. Yeah.
Yeah, like the phenomenal experience would be the same. Why do I care what it's reducible to? Like.
Yeah, this nothing moreism is really silly. It annoys me. Craig does this a lot with the moral argument. We talked about that.
He literally just produced a new video called "Is the Universe Deterministic?" That's like that, where he does that for like 5 minutes.
Tiny particles. But despite this, physicists are finding a different picture of reality. The old notions of materialism are fading away.
See, and then this is where it begins to make me think it's like a bit culty, because it's like, oh, are you depressed by like physics? Well, here is hope. Here's the hero myth. Here's like, you can adopt this strange fringe worldview and have hope, meaning, and purpose. And that's like just the Craig thing, but with different.
Yeah, it does have that vibe with how he framed this.
First, doesn't appear to be material after all, but something emergent from a more fundamental underlying reality. Space-time and matter do not appear to be the foundation of reality, but an emergent construct of a deeper reality, and a new consensus in physics is emerging.
the future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with. We forget about what space is and what time. And then somehow the information, by thinking about how much information is, what information is doing, then the space-time will, what we call, be emergent. It will come out of just a bunch of zeros and ones.
So the idea is that the concept of space, of distance, all the spatial concepts we deal with in science are emerging from that deeper level. They're not fundamental in the world. They're derivative.
In the hunt to rectify quantum mechanics with relativity, physicists discovered something known as the holographic principle, a theory which suggests the entire three-dimensional universe can be seen as two-dimensional information. In other words, the whole three-dimensional universe, the particles that make up reality, would emerge from underlying information in quantum field.
Did you see what he said there, though? He said, as nothing more than information. How do you feel about being nothing more than information?
Yeah, I believe I haven't looked up the clips of the physicists they're showing, so I don't know exactly the context. Yeah. I think that when they are talking about information, they're talking about information in a quantum sense. So I'll give a bit of background here. The holographic principle originally came out of studying black holes, because there was this concern that the information in terms of, think of it as, yeah, the information in terms of the specification of the physical properties of stuff that fell into the black hole was lost, because essentially there seemed to be no properties of the black hole that would be sufficient to maintain that. Like a black hole is basically defined by, I think it's got angular momentum and mass, and that was it, right? So like where does the information go? It seemed that there was nowhere for it to sort of be encoded physically. And that was a concern because it seemed to violate what we understand in quantum mechanics, something called the unitarity principle, where basically quantum information should always be preserved over any sort of quantum transformation, that you can always, at least in principle, if not actually in practice, work out what came before, like what had come previously to that system, because the information is still there. It doesn't like disappear. It's sort of, I mean, I don't know if it's exactly true that it follows from, but it's related to like conservation of energy and other properties that, and the laws being, like Schrodinger's equation being deterministic and so forth. So anyway, so this was a concern about black holes. Now, in trying to resolve this issue, people like, what's his name? Kind of black hole guy, Stephen Hawking, black hole guy. People like Stephen Hawking were sort of thinking about these ideas, and increasingly have sort of come to this conclusion that the information is not about the matter that falls into a black hole, is not in fact lost. It is preserved, but it's encoded around the surface of that black hole. And this led to the idea called the holographic principle. So I'll explain the name in a moment, but the idea here, black hole guy, yeah, well, that's what came to mind. The idea here is that, yeah, the information about all of the matter and particles and whatever that falls into a black hole is preserved around the surface of that black hole. It's encoded in a two-dimensional, well, surface of the black hole, I guess, around the event horizon. So that is what gave rise to the idea. Now, this idea has been taken and applied to quantum cosmology. So this is an attempt to reconcile, or I guess integrate, quantum mechanics with general relativity, which describes the bending of space-time, and try to construct a quantum theory of gravity. And currently we don't have a quantum theory of gravity that's generally accepted, so this is the sense in which it's new physics. Physicists are trying to work this out, about how to, what the best quantum theory of gravity is. So people have probably heard of string theory. Loop quantum gravity is a competing theory. So there's a lot of active work on this area. The holographic principle has been taken from its original context in describing black hole information loss and then applied in a different setting, I guess. So it is a hypothesis. It's not established, contrary to what IP says, and we'll go through that in more detail. But I just want to, because IP doesn't really explain what he's talking about. So a hologram is it's basically a thing that stores all of the information needed to reconstruct a three-dimensional visual image. So it's not like a photograph, because a photograph just stores a two-dimensional representation of a scene. A hologram, if you just look at it, under ambient light, it doesn't look like much. It just looks like scrambled. But if you shine the right type of light through it, it can reproduce a three-dimensional scene, because basically it reproduces the pattern of light rays that came off the original scene in the first place. There's a way to it's basically diffraction grating for people who know what that is. It's and that's a way of storing the information that was present in the original light. So if you've seen a hologram, it has three-dimensionality to it. You can like move around and see it from different perspectives because it's preserving much more of that information that was present. Well, theoretically all of it, although in practice there's difficulty with the practicality of making one. Theoretically, it can preserve all of the information that was present that was from the light that came off the original image. So the idea here is that you can encode all information about a three-dimensional scene or object in a two-dimensional device, which is a hologram. So it's a bit confusing because some people use the word hologram to refer to the physical storage medium, and some people use it to refer to the thing that you see when you shine the light through the medium. So already there's an issue of equivocation about what the hologram actually is. So is this making sense so far, Nathan?
Yeah, it's making sense so far. I was just thinking though, and I don't know. This might I don't want to like send us off on a silly tangent. But a lot of the kinds of arguments that IP wants to put forward for the irreducibility of the mental to the physical or anything else, well, surely they're going to apply to information. Like why is consciousness reducible to information? Like, isn't he going to have to adopt some kind of because this is what he says about like the resurrection stuff as well. Like God's kind of like got all the information of like all your memories and things, so he can reconstruct it. And it's like, well, if you're reducible to the information, like why can't your brain can be simulated in a machine and like all the information about it can be stored there? Why isn't that just you? Like there's all these questions for IP's view in terms of consistency of he wants to argue against like reducing the mind, but then he also wants to be able to reduce it to information. And I
think this might be where the dual aspect comes in. So,
okay,
he calls himself a dual aspect idealist, right? I think what he's going to have to say is that the physical world is reducible to information and quantum mechanics or whatever, but our minds, while also being simulated in God's mind, are not themselves reducible to information.
Well, they are by God, though, surely, because that's how he.
Well, I don't think they can be, because then why couldn't they just be physical, right? If the physical is reducible to information, then
this is my point.
There has to be like they have to be different in some way. It would seem to me to make sense of what IP says.
Information.
Sorry?
Theo information.
Theo information, yeah. Look, I guess I can ask him about this when we have a discussion, but yeah, there does seem to be a tension there between saying that, like the mind's not reducible to matter, but also thinking that it's reducible to information in the mind of God, which seems to be inconsistent. But maybe there's a way around this. I don't know. But that's a good point. But let's come back to the holographic principle.
Sorry, my apologies.
That's what a hologram is. The basic idea is that it's a thing that can encode three-dimensional information in two dimensions. Or more generally, it can encode n-dimensional information in n-1 dimensions, because you can apply this principle to a broader class of things. And that's the sense in which it's being used. So some people talk about the universe being a hologram. I think that's very misleading. It's based on the holographic principle, which is named after holography as a phenomenon, but it's not literally the same thing. It's more a similar principle, but it's not literal. So we shouldn't take that too far. But how does it apply to the universe, you might ask? So so it came from black holes and like holography with light, but what does it have to do with the universe? Well, I'll share this. Wait, what? It's not letting me share. Not this again. I don't want to have to. Well, no, I guess I will, because there's a couple of papers I need to share here.
You don't have to leave and rejoin, do you?
Yeah, it's not like I click share and it just doesn't do anything. I'll be back in a second.
Yeah, no problem.
You can entertain him in the meantime, Nathan.
Yeah, I'll dance in a circle or something for everyone. In the meantime, how many of you have been here for the whole journey so far? And those of you who have joined us partway through, at this point, this is our last video in the series. And then after this, we're going to take a look at IP's kind of opening statement that he uses in debates and how that's evolved over time. James is back.
Sorry about that. Yes, okay, so it's doing something now. So share screen, the illusion of gravity, that's what I want. So this, hey, what?
I've got you.
Okay. This is an article. Yeah, this is the first blank page for some reason. Yeah, no, this is just the silly things I do. But this is a decent article from a few years ago in Scientific American. Yeah, so it's a bit 15 years old now, but still relevant. So this gives a popular, but still fairly decent, I think, explanation of the holographic principle and its application to theories of quantum gravity. Although I think the title is very misleading, but you know, that's how these things go. So I'm not going to work through the whole article. There's a lot here. It's pretty decent. So if you want more information, check it out. I have a bit here that I wanted to show you in explaining how the holographic principle relates to quantum gravity and why people are interested in this. So the holographic theory describes how quarks and gluons, so fundamental particles, interacting on the boundary of an anti-de Sitter space could be equivalent to particles in the high dimensional interior of the space. That's basically the substance of the theory. So let's break that down a little bit. So an anti-de Sitter space is a space, like space-time. Think general relativity. It's like a way the universe could be. It's a geometry of the universe, or a universe with a particular geometry. Except it is different to our universe. So our universe is thought to be like mostly flat, whereas an anti-de Sitter space is actually shaped like a hyperbola. So it's an open universe. I'm just trying to see. Yeah, so it kind of looks like this. Like they sometimes call it a horse saddle shape because it sort of looks a bit like that in 3 dimensions. But anyway, the point is that's just where this applies. I'll explain what I mean by that in a moment. But that's just the type of space this applies to. So the point is, what has been discovered in this particular context of the anti-de Sitter space is that you can actually show a correspondence between a certain type of quantum gravity theory and a more ordinary type of quantum what was the word I'm looking for? Quantum field theory on the boundary. So here's what this is saying here. The idea is as follows. A quantum gravity theory, remember, that's what we're looking for, a quantum theory of gravity. We don't have that. In the interior of the anti-de Sitter spacetime is equivalent to an ordinary quantum particle theory living on the boundary of that space. So this is how the holographic principle comes in. What we're doing is we're moving from the interior, which is 3-dimensional, well, it's actually 4-dimensional because there's time as well, to the boundary, which is one less dimension. So we're saying that there's a correspondence between the theory in the middle to the theory on the boundary. And all of the information about what's happening in the middle can also be described or is also represented by stuff happening on the boundary. So this has been established formally, as in mathematically, you can show a direct correspondence, like basically one equation here, one equation there, one number here, one number there. That's what they mean by equivalent. You can show a direct correspondence between a quantum gravity theory in the interior and then a normal quantum field theory on the exterior. Now, there's a couple of reasons why this is an important result. Firstly, quantum gravity is really hard, and we don't know how to solve all of the quantum gravity problems in the interior of the space. So we're trying to work around that. Secondly, there's 4 dimensions. But if you go to the exterior, the boundary, it's one less dimension, so it gets a bit easier to solve the equations. Plus, and this is really the key point, you only have to deal with like ordinary quantum physics, essentially, or quantum field theory, which is a simpler theory to solve, and that's the key point. So it allows you to solve the equations in an easier way by this correspondence between what's happening in the middle and what's happening on the boundary. So that's the key idea. It's basically doing the maths in a simpler way by showing a correspondence between a theory in the middle and a theory around the edge of that space. Now, this has been shown in very specific contexts. For an anti-de Sitter space and particular types of, I forget the exact name of it, actually. I had this up here. I want to actually mention this because it's kind of relevant. There's a Wikipedia page on this. Oh, no, it's not called what I thought. This is called, yes, it's called ADS-CFT correspondence. So I'll actually see if I can share this with you now, because that's a popular article, but it gets very technical. And I don't know that much about quantum gravity, so I certainly can't do all the details here, but I just want to show you this. So this is the theory that I'm talking about. It's called anti-de Sitter conformal field theory correspondence. And this is what I was saying. There's a correspondence, so like one-to-one mapping between equations in the middle using hard maths and equations on the edge using easier maths, to put it in a very simple way. And because you can show a direct correspondence between everything in the middle and then everything on the boundary, it's applying the holographic principle because you're reducing the dimensionality, like 3 dimensions to 2 dimensions. Now, it's important that this is an illustration of what's happening there as well with the middle compared to the boundary. It's important that this has been established for very particular theories. So anti-de Sitter space, which remember is not what the universe is really like, and this particular type of string theory, which is equivalent to n equals 4 supersymmetric Young-Mills theory on the 4-dimensional boundary. I don't know exactly what that is. I have a very vague idea. But important point is this is not a physics that describes the real universe. This is a different type of physics that has a lot more different types of structure, different types of symmetries, and other things like that. As it says here, the dual theory is not a viable... Sorry, here. Might zoom in a bit.
Yeah, I might need...
The dual theory is not a viable model of any real-world system as it assumes a large amount of supersymmetry, which has not been established to exist. This boundary shares some features with QED, which is good. Sorry, quantum chromodynamics, that's not QED. The fundamental theory is a strong force, so it allows us to solve problems we couldn't otherwise. There's some other realizations as well that people are looking at with different theories, but the point is that these are not the theories of the actual universe. They're theories that people are exploring to try to see how far they can use this result. And I actually messaged one of my friends who's doing a PhD on this exact topic here, and was sort of asking him about this. And I mean, he agreed with what I was saying here, that, yeah, this is interesting and people want to see where they can take this, but it's very far from being currently a theory of like our actual universe. These are a different space-time and a different quantum theory than, you know, we currently think describes our universe. So this is sort of provocative, and a lot of people are interested in this, but IP is not really explaining very well how it's very primitive is not the right word. It's very early stages of this sort of theory, because it's not established this even applies or could apply to the actual universe. It's just people sort of hope that they'll be able to get a result that could be applied to the real universe. You're muted.
Oh, yeah, I am. Shall we?
Sorry, I thought you were going to say something. So one other point, though. So I want to now explain what this means by talking about emergent. Okay, so the idea here is that what they want to do is explain space and time in terms of quantum mechanics. They want to give a quantum theory of where space and time come from. And so under this view, space and time may not be fundamental. It may emerge from or arise from quantum interactions of a quantum field theory. And really, that's going to be true in any quantum theory well, probably most quantum theories of gravity, not just the holographic ones. I think it's particularly provocative here because there's this correspondence between what's happening on the boundary, which could describe what's happening in the middle. But remember that it doesn't mean like it's an actual hologram that's being projected and it's like an illusion. That's just completely misleading. All it means is there's a formal correspondence between the theory in the middle and a theory on the edge. And that's a mathematical correspondence that doesn't tell you anything about which one is more fundamental. So to say that space-time is an illusion or gravity is an illusion is completely wrong.
Well, because holograms are illusions, James.
Well, you see, even like they're not actually illusions; they're just reproducing the light, right? That they've been. But even that's not literally what's happening here, because that sort of implies something outside the hologram. Remember the hologram as the medium that you shine the light through. That's not really what's happening with the universe. It's just the principle of reducing the dimensionality of the description that's being applied here, and on the boundary as well, which is similar to how it worked with the black hole. So again, it's more like an idea, a principle, rather than the specifics. So these results about ADS CFT correspondence and emergent universe and quantum theory of gravity stuff, they're illustrative, but they're not established to actually apply to our universe. They don't show that, even if they were to apply to our universe, they don't show that gravity is an illusion or space-time is an illusion. Really, they're just ways of trying to explain how to link up quantum mechanics with general relativity, which we've been looking for a long time. And that would be really interesting if we could work that out and have a quantum theory of gravity. But it wouldn't mean that anything is like an illusion or a simulation or anything like that. That's just spin that people put on it, basically.
Yeah.
Now let's see what spin IP puts on this.
People finally began to articulate this new principle, this holographic principle. And what it said is that all the things that were falling inside a black hole were somehow captured in a preserved image at the horizon itself.
So if the information is not lost on the surface, the information is not lost inside because they are equivalent.
All the information about those objects, what they were like in their three-dimensional existence, was preserved or encoded on the surface of the black hole. And that's a little bit like a hologram.
It's interesting that it's encoded in binary in the shape of the object that was absorbed, as these graphics demonstrate.
Yeah, the binary thing, I don't really know what that has to do with anything. It's about the I mean, I don't fully understand it, right? But it's about the way the physical system is, such that it preserves information content from the particles or matter that fell into it. It's not encoded in the sense that like information is encoded on your hard drive.
Well, this is where I think the graphics that are used, and it's all linked up to like paint this picture of what's going on, but that isn't necessarily what the science is even saying. And it's like, oh, because this fringe view, we're just going to push like that the universe is like a computed hologram for some reason. And so because computers use binary to like encode their information, well, I guess like, oh, we're just going to put a bunch of bits along the edge of the event horizon. But the problem is, like, if you think critically about it, you're like, well, okay, they've got a bit of creative license to do that or whatever. But the problem is that this is precisely the mechanisms that's being used, or maybe IP is like a victim of this, like to form false beliefs that then like then you go and do research and you sort of ignore the misses, focus on the hits. You don't, and you end up just building this worldview up that's based off of like the fact that whatever it was, like the graphic was displayed a certain way. The same with like the eye at the start in the quantum eraser experiments, where you think there's some kind of like invisible intentional causation going on when there isn't, which is just to do with like you've been taught through like a graphic that was not explained or thought through.
Yeah, just in terms of encoding the information, to give a bit more of an intuition about what that means, as far as I understand it, an analogy here, and this is a classical analogy, but I think illustrates the point. If so if you imagine firing a bullet through through like a tank comprised of ballistics gel, and there's a reason that I specify like that. So the gun is immersed in that somehow, and then the bullet goes through and eventually stops. So what you will have is that there'll be changes to that ballistics gel, right? You know, the bullets push through it, and there's a bit of shrapnel or expanding gases that push it or something like that. So at least in theory, you know, if it's contained well enough, that's sort of what I'm thinking of. Although you can see it pushes outside a bit, but if that ballistic gel was big enough and you move the gun closer to it and so forth, all of the information about that bullet and its trajectory and energy and all that stuff would be contained in the ballistics gel, in the way that it's changed the shape and properties of the ballistics gel. It's all there, right? You might not be able to recover it in any like meaningful way, but it's there in the way that it's physically affected the ballistics gel. It hasn't disappeared somehow from the universe. And that's what is meant, as far as I understand, by conservation of information in quantum mechanics. It means that the information in terms of the properties of previous quantum systems that interacted with, you know, the black hole or whatever else, is preserved in some properties of the way that the black hole changes, or, you know, any other physical system. Again, that's the unitarity idea of quantum mechanics for people who want to look this up. So there's nothing really like mystical there about like information being encoded in zeros and ones or some consciousness of story. It just has nothing to do with that. It's just about like physics affecting other physical things in a way such that, you know, in principle, you could sort of reverse it out of it if you had enough, if you somehow had the computation to do that.
But if you've already been kind of anchored to some of the ideas about the universe being computational or whatever, and then you see like this graphic while you're being told this stuff, you're going to be seeing 11 right now, like, you know, you can 11, and you're going to be, you know, like this is just more evidence, in fact, when it's actually got nothing to do with like the computational theory of the universe, whatever.
Nope, you did.
To the universe as a whole. Maybe the three-dimensional objects, us, everything in the world around us, maybe all of the information in these objects is carried, is smeared around a distant two-dimensional surface that surrounds us, and we're just in some sense a holographic projection of that distant data.
The holographic principle tells us something quite astonishing. It says that our
It's the same with that graphic where there's like zeros and ones around the Earth, as if it's like some sort of matrix simulation or something, which just isn't right. It's like, well, yeah, you could.
Yeah, the way Brian Greene described that is like you could defend it, but it's highly misleading, I think, for especially the way IP is presenting it with the visualizations and everything. Like, in some sense, a holographic projection. Well, yeah, in a very specific sense that I just tried to describe, you know, like because of the mathematical correspondence of this theory here and that theory there. That's what he's talking about, right? But I think people are not going to get that impression. They're going to get the impression that somehow, like, this isn't real and it's like projected from the outside somehow, like a hologram is. But that's not what is actually happening. That's not what any of this says.
Yeah.
The holographic principle tells us something quite astonishing. It says that our ideas of volume, of the real world in a sense, might be a kind of illusion.
The holographic principle only worked in theory at first, with no observable data to back it. But all that changed in 2017, when a peer-reviewed study published observable evidence for the holographic principle. They tested the model against cosmological observations of the early universe, and found that the holographic model is compatible with the data that is found in the cosmic microwave background radiation. From looking at irregularities in the background radiation, their team found that simple equations of quantum field theory could explain almost all the cosmological observations, is marginally a better fit than the standard model, and could potentially explain apparent anomalies. But this would mean evidence in the cosmic microwave background radiation infers three-dimensional reality is an emergent informational construct. Observable evidence infers reality as we experience is not fundamental, but emerges from the quantum realm. This piece of data only correlates to a study from later that same year, which points out entanglement is an inevitable feature of reality. Entanglement happens when two particles interact in a way that their quantum state or wave function.
Hang on. Let's stop here. So we sort of move into something else now for some reason. I don't know what, and we've already talked about that, but this paper here about the observations of the observational test of holographic cosmology. Okay, so he uses this a lot in his debates. I think he used it in most of them, and it's sort of like the Borde-Goose-Vilenkin theorem of Craig. It's like the go-to. So I had to look at this because it just didn't make sense to me on the face of it, right? Because if this had been established, these people should be winning Nobel Prizes. Like, this would be massive. This would be huge if they could establish, because basically that would amount to establishing a quantum theory of gravity or sort of a big step towards it. So why is everyone not talking about this? Where I put this paper in Google Scholar and it's not, I mean, it has some citations, but it's not being discussed much in the physics literature. So something didn't smell right with the claim being made here. So let's talk about this paper, shall we? I'll pull it up here because, again, this is a very important one. Okay, here it is. Observational test of holographic cosmology. Now, I got to be careful what I say about this. I think this paper is not wrong per se. It's just not very good. There's a big difference between a paper that's like just flat out wrong or nonsense, you know, like the one we looked at with the guy who was saying that the universe is a simulation. That's just nonsense and rubbish. This isn't like that. It's a legit paper, but it's just a bad paper in my opinion. So let me explain why it's a bad paper, and it doesn't establish anything like what IP says it does. So you've got to understand what they did here. What they did is I don't think I actually, well, maybe I can use the abstract here to illustrate the point. So we test a class of holographic models of the universe based on cosmological observations and find that they are competitive to the standard lambda CDM model of cosmology. So this is the standard model of cosmology. That stands for lambda stands for the cosmological constant, which is like dark energy causing the universe to expand, and CDM stands for cold dark matter, which is the standard model of what dark matter is. But anyway, so that's the standard model they're comparing it to. And they want to see whether a holographic model, based on some of the theories that I just mentioned before, how it compares to that. So how do they do that? Well, what they do look at is they look at the power spectrum of the cosmic background radiation produced by the Big Bang. And they see which model fits that data better. But yeah, see, they don't really explain this in the abstract very well. But if you look at what they actually did, they fit the models to the data. So the lambda CDM model is parameterized by 6 parameters here, including the amount of baryonic dark matter in the universe, and some parameters about the Big Bang, some other things that I'm not entirely sure about. And in comparison, the holographic cosmology is parameterized by 7 parameters. A bunch of things here that we didn't concern ourselves with. But most of these are not things that are well known necessarily. So they've got two models here. They're then fitting them to the data by using basically just like a maximum likelihood function, or a loss minimization function. So it's not like that they just had the theory which predicted what this should look like. This is the data that they're fitting to, essentially. I'll explain what this is in a second. But it's not like they just had this prediction that came from the model. They're fitting the model to this data and then seeing which one fits better. So any model that has sufficiently many free parameters will be able to fit any arbitrary set of data. So you already have to be a bit skeptical about what this means precisely. But so it depends on the details, but let's look at what this is. So what is this exactly that we're looking at here? This is the angular power spectrum of the cosmic microwave background temperature anisotropies. So what this means is that if you look at the earliest radiation that was produced just after, when the universe became transparent to light sometime after the Big Bang, that's called the cosmic microwave background radiation. If you look at that, it's mostly the same everywhere, but there are small differences. It's slightly more intense in some places, slightly less in others. These are called anisotropies. It just means like differences in different directions. And it's these small anisotropies that ultimately led to the formation of like clumping together of matter and giving rise to galaxies and stars and so on. So these are studied to understand the early universe better. Now, the angular power spectrum is basically a way of describing how these are distributed across the sky. So basically, you can think of it as like breaking up the anisotropies into ones that are like large, and then those that are smaller and smaller than that, and so on. So it's sort of like decomposing a wave into different wavelengths of like longer wavelengths and shorter wavelengths. It's a bit like Fourier analysis for those who know what that is, although it's not exactly that. It's a power spectrum. So it's not quite that. But basically, this is a description here of the different modes of the anisotropy. So it's just a description of the way the cosmic microwave background radiation looks like. And the height here is just the intensity, essentially. So it doesn't matter too much exactly what this means. I just wanted to give some context for it. But this is what we empirically observe. So the dots are empirical observations. And what they're doing is they're fitting both of these models, lambda CDM, that's standard cosmology, and then the model based on the holographic principle, the quantum gravity stuff. They're fitting that both to this data and seeing which fits better to the same data. So again, they're not taking the predictions and using these models to predict this. They're fitting the models to the data and seeing which fits better. Well, which fits better? Let's have a look at that. Well, here's the key plot here. So it's a bit busy, but I will break this down. So the vertical axis here is the key here. This describes how well it describes how well the model fits the data. So higher up on this graph is a better fit. So you're looking for which is higher. Now, confusingly, they've plotted a few different things here. So notice that we've got lambda CDM, we've got it twice, and then we've got HC. So that's the holographic principle predictions, basically. So lambda CDM is like standard cosmology, and then HC is like the new quantum theory stuff based on a holographic principle. Okay, but why do we have it twice? Well, it's a bit confusing because remember I said that lambda CDM has 6 parameters, but the other one has 7. So that's an issue because if you have a model with more free parameters, you can fit the data better to it. So what they're saying here is they need to add a parameter to lambda CDM. Where do they say that here?
So it's that,
here it is.
7th parameter.
The model has 7 parameters, so in order to compare models with the same number of parameters, we also consider lambda CDM with running coupling. So it's an extra parameter they're putting in so that they have the same number of parameters. You really should always do that because otherwise the model with more free parameters is going to have a better ability to fit the data. So really, I think you should look at this one here. Lambda CDM with running. That's the one with the same number of parameters. So you should look at this top line here. And this line here is like the fit, and then this is some sort of confidence interval. I don't know exactly how it's defined around the fit. So that's what we're comparing it to. Now, HC, that's the new model, like the quantum gravity one, the holographic one. So again, why are there 2 of those? Well, basically because the way they're doing this is that they're using Bayesian updating. So they need priors on the different parameters they're putting into the model. The priors are based on cosmological evidence, but there's some debate about how to do that exactly. So this graph here kind of relates to that. But, when you do confidence intervals, there's like the 90%, the 95%. There's like how far out do you go, so to speak. This is a contour plot of standard deviations. So the question here is like, do you pick the parameter based on like 1 standard deviation or 2 standard deviations, or like how it's kind of arbitrary. So they've just done it in 2 different ways. So I don't know that there's an answer as to which is better here. whether you go with the small range or the large range. I would probably say the small range is more justifiable because it's a tighter fit to the data, but you can justify either of them. There's a lot of there's a lot of choices that you have in doing this. So the point is, you can look at this blue dotted line, or this whatever red, is that red colored? I think it's a red dotted line. So I'm colorblind, so sometimes I get muddled. Now, why is there a horizontal axis here? Well, it's because there's another parameter here that they don't know which value to pick, so they're just showing you all of them. So it's kind of confusing, but all we really have to look at the end of the day is which line is higher. That's the model that has the better fit. And you can see, well, I mean, they're basically the same, because we should be looking at this green one here, because that's the one that has the same number of parameters. I mean, they're pretty much the same, right? Depending on whether you look at this one or this one, but there's not much of a difference. Is this difference significant? Well, it says so. It describes it here. The results for Bayesian evidence are presented here. That's this figure here. As a guide, a difference of log n of less than 1 is insignificant. Okay, well, how big is the difference here? So from this line here to this line here is less than 1. In fact, here to here is 1, which is insignificant. So all of these differences that they show here are insignificant. Basically statistical noise as far as we can tell, to put it crudely. So there's no difference between the fit of these models, especially if you're looking at the running one, which is higher up than the other one. But really, it doesn't matter because they're all so close to each other. Now, they say here, we see the difference between the two models is insignificant, with marginal preference for HC depending on choice of priors. That's what I mean here in terms of like where you go along here or which dotted line you pick. But when they say marginal preference, they mean a non-significant difference, which to me is no difference. If you were publishing this paper, this result would be considered not significant, right? They're trying to spin this as if it's a result when it's not actually a result. It's no significant difference between their fits, which to me which is not surprising to me, because you're fitting two models with 7 free parameters to a data set that I'm not exactly sure how many observations it has, but I don't think it's that many. So there's a fair bit of flexibility in these models. So I'm not very persuaded by this methodology in the first place. Plus, there's some other issues, like actually you have to restrict where you're looking at, because it turns out that the holographic cosmology just breaks if you go too far. If you choose a low L, they talk about that here, that you can't do the calculations, and so you've got to just sort of restrict that. They say that somewhere here. Yeah, here at lower values of L, the two-loop turns time changes and grows very fast. So blah, blah, blah. The point is that you shouldn't trust these models below L equals 10. So you've just got to ignore those because the theory doesn't work. But, we should not trust a perturbative expansion below L equals 35, actually. So you even have to throw out more than that. So what's all this come to? This is why I say this is a terrible paper, because all it's doing, it's just a statistical data fitting exercise and asking which model fits the data better. And their conclusion is that they fit the model basically the same. And that's even when you throw out the L's that you can't trust because you can't do the calculations properly. If you included those, then that would be a worse fit because you can't really do it. So this paper is not evidence for holographic cosmology. It's not really evidence for anything because it's just a statistical fishing exercise is the interpretation I would give. So IP is grossly misstating what this paper actually shows.
Damn.
Hopefully that was clear. Like, it's very technical. It took me a while to work out that. But when you actually work out what they've done, it's nothing like what IP is presenting. It sounds like that they've predicted and it fits just with their predictions, but it's not like that at all.
Yeah, I mean, I think the point that you want people to get from it is clear, but I think a lot of the nuances are going to be lost. And I certainly I've got everything that you've got from reading the paper and going through and looking at the methods I've used in the data, and even understanding like where that data comes from, what it is and stuff. That's all going to make, but I think the main point that it just doesn't show the conclusion that IP wants to get from it.
There's no significant difference is the key point there. So there's no result. It's a null result of the paper. And they try to spin it as like a marginal preference, but that's just spin that authors put on these things. It's not, even if there was a result, I wouldn't really trust it because it's just a fitting a model to the data, which is always suspect because there's always free parameters you can choose there, like the choice of priors, for example. But so even if there was a result, I wouldn't really believe it, but there wasn't a result. So there's just nothing there.
But now there's something to say though, because IP's had several debates on this topic where he's used this paper and no one has pointed this out.
Yeah. Well, because most people aren't crazy enough to track down the paper, read it, and spend time working out what the heck they're talking about. But one thing, because I actually did a course when I did, because I didn't do a lot on like what am I trying to say? I didn't do a lot on general relativity, and like they don't really even teach you quantum gravity at that level. That's like PhD level. But I did do a course on physical cosmology, and we did look at anisotropies in the cosmic micro background radiation, because that's really standard stuff. So I do actually, we worked on those plots, and so I do know exactly what that, well, pretty well what that is. So that was familiar to me, and that helped me to work out what they were actually doing. They're just fitting models to that experimental data, or that empirical data. And model fitting itself is not really very persuasive. You want to make predictions, which then you can test, or something that's more than just a statistical exercise, because you can fit any data if you have enough free parameters in your model to do it. So already I wasn't persuaded when I worked out that's what they did. But then when I found out there was not even a difference between the fits of the two models when you use the same number of parameters, I'm like, well, what's the point of this? It's nothing.
Yeah. Right. Well, let's see how is he going to talk more about that paper then and the conclusions he wants to draw from it at this point?
I think he does in this video, and he definitely does in the debates.
Or without the other. However, if you were to separate them by a great distance, a change to one instantly affects the other. This has been demonstrated in several experiments, and now a new study shows that such a phenomena is an inevitable feature of reality. We show that any theory with a classical limit must contain entangled states, thus establishing entanglement as an inevitable feature of any theory superseding classical theory. In other words, any theory which purports to describe reality must include quantum entanglement as an underlying fundamental feature of reality. If you entangle two particles and separate them by a great distance, a change to one will instantly affect the other, regardless of the space between them. So the information between them doesn't seem to be affected by space, implying space is not fundamental for the underlying world of quantum mechanics, but an emergent phenomena of the classical world that only exists after measurement.
Whereas space is just obviously not fundamental. Space is something where when you go from classical mechanics to quantum mechanics, space more or less disappears. In classical mechanics, what do you have? Some particles moving through space with some velocity. In quantum mechanics, you have a wave function of all those particles. That wave function, we tend to talk a language that the wave function is a function of all the particles and their locations in space, but we don't have to talk that language. We can use what is called the momentum space description. We can completely describe the particles by how fast they're moving instead of where they are in the universe. And for that matter, we don't need to use any description at all. We can just use these quantum mechanical states in their own right, with no reference to space whatsoever.
Remember that in quantum mechanics, prior to measurement, particles have no defined properties.
Sorry, I want to comment on what Sean Carroll said there. Because again, like a lot of these things, it's sort of true in a sense, but I mean, I do get the impression that Sean Carroll sometimes overstates his own particular interpretations or views on things, but that's just me. But anyway, the idea that space is not fundamental really depends on what you mean by fundamental, right? So in the sense that we think that there's probably an underlying quantum description that that sort of from which classical space-time emerges, I think that's probably the case. Generally, that's what we think, but we don't have that description at the moment. The holographic principle is like an idea that might lead us to that, but it's not there yet. But the point that I want to make there is I think that space and time are, well, he didn't actually, time is a bit different, but space is very important to quantum mechanics because it's sort of critical to the measurements that we make, which are used to test and verify quantum mechanics. They're conducted in space and usually relate to detecting particles in particular locations at particular times, right? And that's a key part of quantum mechanics as well, the experimental verification and testing of the results. And I mean, I don't think Sean Carroll would disagree with that. It's just that I feel like the emphasis was a little bit off there because, yeah, you can describe things in an abstract way that doesn't mention that at all, as he was saying. But at the end of the day, you do need to be able to test these things. And then you have to be able to translate it all back to things that we can measure in space and time and, you know, things that connect to physical apparatus, right? So I think this may be sort of the theoretician coming out a bit, but that's not exactly disagreeing. It's just more that the emphasis there can be maybe misconstrued depending on exactly how you're interpreting what he's saying there.
Particles simply exist as a wave function, of possible states they could take, and that includes the location of the particles. If particles have no defined locations prior to measurement, that would mean the information between entangled particles exists other than spatially. Spatial location only emerges after measurement. Thus, entanglement shows space is not fundamental, but emergent from quantum processes, correlating with the evidence from the holographic principle. The wave function of entangled particles is far more fundamental than the space between them. Therefore, the underlying information is more fundamental, and space is emergent. Space is just the illusion that particles are separated.
Just something to remind the audience of here, I suppose, is that we are talking about why we should believe that Jesus Christ died for your sins and resurrected, and why you should believe that he is the Son of God and worship him, just in case you forgot at any point.
Not a fundamental feature of reality. Physicist Sean Carroll writes on his blog, Space Emerging from Quantum Mechanics, that the most likely way to explain the nature of gravity is to note space emerges from quantum mechanics, not that space is a fundamental property of the subatomic world. Physicist Haiyan Seok Yang says emergent spacetime is the new fundamental paradigm for quantum gravity. This new paradigm suggests space is not fundamentally real, but emergent from the underlying quantum realm. But it is not.
Pause here. So there's a mistake about the notion of emergence. Okay, so, and I think that this maybe is reflecting again some of Michael's understanding about what it is to be real or material. So the fact that something is emergent doesn't mean that it's not real. It just means that it's not fundamental.
Right.
So someone mentioned before, temperature is not fundamental. It's emergent from the kinetic energies of the particles existing in a given space, right? In fact, most things that we know are not fundamental. Well, I mean, maybe if you're a Platonist or something, but certainly if you're a reductive materialist like me, or I mean, even people who aren't will acknowledge a lot of physical things are not fundamental. Like cells are not fundamental. They're made up of parts, right? There's no essence of a cell that gives it cellness, as far as we know, at least. Again, maybe if you're a Platonist, it does. But so the fact that something is emergent, like weather is an emergent phenomenon, climate is an emergent phenomenon, the economy is an emergent phenomenon, language is an emergent phenomenon. Okay, so nearly all of these things are emergent. It doesn't mean they're not real. It just means they're real in virtue of lower order things that give rise to them. So this idea that because gravity might be and space and so on might be emergent from an underlying quantum description, that therefore it's somehow fake or not real or an illusion, it just doesn't follow at all.
Yeah. And that's said as we travel through the quantum tunnel of binary digits.
Virtual quantum tunnel wormhole with information. Yeah, it's like
binary. What, like, why is it zeros and ones? Why? I mean, I know he's not like made these, but it's like, you know, like these sorts of graphics and things are just you know, you see the equations flying around and stuff, and it's used to like bolster the confidence of the person who's viewing. And when you just think about whatever it's trying to get at, like, it just doesn't make sense. Like, I don't know of any kind of wire that has like this kind of insulation, or are we in a wormhole, or like, what is this? Why is it got zeros and ones on it?
Entanglement. Einstein demonstrated space and time are one. So that would have to mean that time is also emergent from the underlying quantum realm. And an experiment from 2013 reveals this. The Wheeler-DeWitt equation, which calculated the wave function of the universe, noted the time factor dropped out, meaning time is also not a fundamental aspect of the underlying quantum world, but emerging.
So let's comment on that.
We experience
the issue of time in quantum mechanics is actually a big problem here, because I think, is that what time in quantum mechanics? I just want to check that if there's a more specific name for it. Oh yeah, it's called the problem of time if you look it up on Wikipedia, because the role that time plays in quantum mechanics is totally different to how the role it plays in general relativity. In quantum mechanics, time is like a parameter that like the Schrödinger equation is a function of time, right? The general form of it. Whereas in general relativity, time is bound up with space as something that is sort of that arises out of the maybe that's not the right word of saying it. It's part of the manifold that is described by the equation. It's not a parameter in the equation. So it's treated very differently. And we need to somehow reconcile those to get a full quantum theory of gravity. So that is an open question. I didn't look up that previous paper he mentioned very briefly. I really have no idea what it's talking about. I very much doubt it's supporting what IP has said. This equation here, the Wheeler-de Witt equation, he said that he like calculated the wave function of the universe. It's not even established that the universe has a wave function. That depends on your interpretation of quantum mechanics about whether there is such a thing as a wave function of the universe, or whether it's going to be collapsed before that or something, right? People have postulated these sort of things. So this is just a postulate. This is a hypothesis. And it's apparently, I don't know that much about it, but apparently when I looked it up, it says it's kind of an older one. It's not, doesn't really play that much role in modern theories of quantum gravity. So I don't really know why the fact that it doesn't have time as an explicit parameter is important. I'm not sure whether modern attempts at quantum gravity do. I would expect that it wouldn't, probably, because you're trying to explain the space-time manifold. So it's a bit different to Schrodinger's equation. I don't have a great knowledge of this, so this seems like a red herring to me. I don't know what relevance it has to anything. It doesn't mean that time's not real. It would just mean that it's sort of emerges in a different way than we'd thought before.
Factor dropped out, meaning time is also not a fundamental aspect of the underlying quantum world, but emergent in the classical world. That
one thing I have learned from these videos is I've always seen these kind of clocks, but I've never really noticed this mechanism over the top. You know, obviously there's something turning here, and then this thing sort of catches the piece. I just never really noticed that going on for those viewers who are...
They're pretty cool.
Yeah. Also not a fundamental aspect of the underlying quantum world, but emergent in the classical world that we experience day to day. And in 2013, an experiment seemed to confirm this idea that time, along with space, is an emergent phenomena.
So in quantum gravity now, probably what's going on is what we're seeing is that the whole notion of space and time is probably not really fundamental. So space...
That sounds incredible. That space and time...
That's the closer to truth guy, by the way.
Oh, really? He annoyed the heck out of me because this expert, I assume she's an expert, is talking about this, and he just interrupts her to say nothing of any substance. It's like, I want to hear what she's saying. Can you be quiet? Anyway, I didn't know that.
Time is not fundamental. Space and time seem, in an ordinary sense, to be the most fundamental thing, and everything else seems to happen in space and time as sort of the fixed background.
Right. But what could be happening is that there are two different notions of time, a more fundamental one and an emergent one. So it's the emergent one that is part of the space-time, but there is a more fundamental one that makes sense without space.
Now, neither one of those new ways are obvious to us in our common perception, obviously, but Einstein put space and time together, which was a radical change. What you're saying is that the time that he might have unified with space may be an emergent time, and there's something more fundamental in time.
Thus, all of what we experience, space, time, matter, all seem to be emergent constructs of the classical world, not fundamental aspects of reality. Experimental data shows us matter and space-time are emergent, while in contrast, another experiment shows the wave function is fundamental to reality. At the advent of quantum mechanics, many suggested the wave function.
Okay, so we just to pause there. We talked about that, I guess, a few hours ago now. So what that showed is that, should I remember? Yeah, so it showed it was fundamental if you already assume that it's real, basically. So their results apply under a very specific framework of assuming the underlying reality of the quantum states that you measure with the wave function, or that you describe using the wave function. So it's saying that the wave function is real if there's an underlying real state. It doesn't prove that whole framework is correct. So it's a much more narrow result than IP is claiming. Again, it sort of must be, because otherwise these people would be winning Nobel Prizes if they somehow proved that the wave function was like real. And that can be a way of just, even if you don't actually know a lot about this stuff, if it seems like that would be a massive result and you haven't heard people talking about it all over the place and like Nobel Prizes being won about it, like you want to ask the question, why is this not getting more attention? And usually it's because it's actually not the result that it's being claimed to be. It's a much smaller piece of the picture.
But just a mathematical tool which represents our lack of knowledge about the system. Yet a recent experiment gave strong evidence the wave function should directly correspond to reality. So the wave function, a mathematical probability of possible states in Hilbert space, does correspond to the fundamental nature of reality. Space-time is nothing more than a construct emerging from the wave function in Hilbert space.
Space-time is not fundamental. The space-time is, if you like, an effective emergent description from something else.
The implications of this are quite astonishing, because the wave function is not a physical object extended through space, but a mathematical probability of where physical particles will appear in space. Sean Carroll explains, mathematically, wave functions are elements of a mathematical structure called Hilbert space. That means they are vectors. We can add quantum states together, the origin of superpositions in quantum mechanics, and calculate the angle or dot product between them. The word space in Hilbert space doesn't mean the good old three-dimensional space we walk through every day, or even the four-dimensional space-time of relativity. It's just math speak for a collection of things, in this case, possible quantum states of the universe. The underlying truth of the universe is a mathematical reality from which the classical world we experience emerges. What we think is objectively real is nothing more than an emergent construct of underlying mathematical informational processes. To further confirm this, Brian Whitworth looked at specific features of our universe and compared them to a virtual world.
Oh, it's this guy again. I almost forgot about it. It's our friend Brian Whitworth. This crazy paper.
Are better explained with the idea of a virtual reality instead of an objective reality with fundamental space, time, and matter. Features of our universe, like the maximum speed, the Big Bang, quantum transitions, and wave function collapse, all make more sense in a virtual world. In other words, the philosophical conclusion is our universe behaves more like a virtual world instead of an objective reality.
And what does an objective reality behave like?
Yeah, I just wanted to pull on to mention something that he said a few minutes ago. He said that space-time is a construct, which does not follow from it being emergent. They're completely different things. A construct is something that's artificial. Emergent is just something that arises from something more fundamental. Yeah. So temperature is emergent, but it's not a construct, right? So the wave function, interestingly, may be a construct. That depends on your interpretation of quantum physics and other factors, right? So that's an open question. I tend to think that it's real or describes something real, but again, we don't really know. But I think this is common. IP sometimes slips between different things that sound like they're the same or similar, but are actually quite different. So it's important to just, pay close attention to exactly what he's saying, and then exactly what the physicist that he's quoting or showing there are saying. That woman was saying that it's not fundamental. She said this multiple times. She didn't say it was a construct or it was false or didn't exist or something like that, or an illusion.
This aligns with the scientific data we just discussed, which shows space-time and matter are emergent. On top of this, the work in
this looks familiar.
Yep. See, this is the I guess the sociological side of bad apologetics, right? So he's plucked these figures out from the paper and he's showing them here. Does he explain what they mean? No. Does he explain anything about what any of these lines and numbers and things, symbols? No, there's no attempt there. Now, I acknowledge my presentation was sort of brief and maybe it was a bit hard to follow, but at least I tried, right? I made some effort to explain what this is. I didn't just throw figures at you and said, hey, this proves what I'm saying. Like, I think that is exactly how not to use science as something as a Pokemon to deploy, as you say, to prove an argument without trying to help people understand what's happening.
Show space-time and matter are emergent. On top of this, the work in theoretical physics is leading us towards the conclusion the roles of physics and gravity are emergent from the underlying spaceless, timeless quantum realm. All the evidence infers that physical reality is not fundamental, but emergent.
All the evidence. There's literally no evidence that says anything otherwise. It's all the evidence.
The holographic universe stuff is speculative developments in quantum cosmology for which there's no evidence, right? So it's fine work. As I said, I've got a friend who's doing this, but I mean, he wouldn't say like, oh, this is where all the evidence is pointing. It's a massive overstatement.
From underlying information, but there is a much deeper implication here. The wave function explains the emergence of space-time, but the same underlying mathematics has been seen to parallel conscious thought processes.
Oh boy.
Quantum superpositions do have a vague similarity to how we think and mentally operate. For example, We often
Hang on. Quantum superpositions have a similarity to how we think and operate.
Well, he's about to explain what he means by that.
I'm just guessing what he's gonna. I mean, I guess based on previous videos, it's gonna be the fact that like we can make one choice, right, and it's indeterminate, and the wave function collapse is kind of like that. But that's like about like as loose an analogy as you can get. Like you can say, I'm just gonna pick something random. It's kind of like a tractor, because I don't really know how long I'm going to be stuck behind a tractor when I'm stuck behind it on the road. It might pull in at the next stop, or it might not. But it's kind of, it's kind of like that, isn't it? When I make a choice, because I just don't know how long, which one I'm going to choose before. I don't know. My point is, like, you can make a weak analogy with anything just by finding a feature of it that's kind of similar. And
yeah, so that's what quantum cognition is. Well, I mean, it's a little more than that, but it's a new approach to describing certain aspects of human psychology that uses some of the formalisms from quantum mechanics, like Hilbert space and wave function collapse and superposition and so forth. I need to read more about this. The thing is that I don't know how many people apart from IP are saying that this is evidence that the Von-Neumann Wigner interpretation of quantum mechanics is correct, and it's actually mind that collapses a quantum. Like, it's just, they're nothing to do with each other. It's just a formalism that's being applied in a new area. This happens all the time in science. Like wave equations, for example, actually, he shows that at the end of the video. Wave equations are ubiquitous in science. They can describe all sorts of things. From like fluid flow to traffic flow and all sorts of other stuff. So, and quantum mechanics as well. Like the wave equation is just really an equation of waves, right? So, the fact that a formalism can be applied in a new context is not evidence that those contexts are somehow linked or causally connected. It just means that there are abstract features that can be modeled in a similar way. So, and I don't even know how well the modeling works. It's not something that I've read a lot about. I'll need to do a bit more reading there. But again, it's an emerging area. I guess we'll see how it goes. It could be useful. But just to say that, because, some of the formalisms can be applied in both cases, that they're like the same somehow is just really,
well, this is literally
a stretch, to put it mildly.
So my silly tractor analogy was just to point out how silly IP is being, but it's not to say that like there's nothing to what like Penrose or Hameroff or whatever is saying, like that. But the thing is, like, if you listen to like Penrose has a pretty cool interview with Lex Friedman, for example, where he talks about some of the quantum consciousness ideas that might arise out of some of his maths work. But he's not saying this is the way it is. It's just like, this might suggest this. Maybe we'll find out this problem. Maybe we'll find a problem to like free will by going down this avenue. But he's not just saying like, oh, here's how it is, because like making a choice is kind of like how a wave collapses, which is.
Yeah, it's important to understand that's true, and it's important to understand that the quantum mind is not the same thing as quantum consciousness. They're completely different theories or views. So one is about modeling cognition, the other is about describing the origins of mind in terms of like quantum principles in the brain, the microtubules and stuff like that. So,
right.
Yeah, although the thing is that IP kind of does conflate them, or maybe conflate is a bit strong, but he links them together very closely, and they're quite different things. And different, again, to the von Neumann Wigner interpretation of quantum mechanics. And he lines them up in a way that he's sort of saying, oh, they're all related, but they're really quite different. You could believe any one of them and not the others.
Mm-hmm. Because I suppose talking about the quantum mind in that way would be like a reductionist approach, right? Where you're saying, well,
that's right.
How you get these emergent properties is just by breaking it down to these quantum things, which isn't, which is very different from saying like, the consciousness is quantum phenomena and is like this distinct metaphysical something or other, which the dual aspect idealism thing, which I don't understand, to be honest. Right, shall we continue?
And hold conflicting positions simultaneously before making a final decision. Like how the wave function is in a superposition of multiple states before final collapse to one definite outcome. We can bounce around between different ideas in our head, similarly to quantum tunneling. This similarity might be more interesting than we realize. In 2009, physicist Diederik Ertz took this one step further and published a paper noting that our cognitive processes can be readily modeled using the mathematical.
You're muted. Not sure if you want to be.
Jerry Fodor, not James Fodor.
Yeah, as far as I know, not a relation, but it is interesting that we have similar names and are interested in some similar questions. Although interestingly, we disagree pretty fundamentally, because Jerry Fodor, I'm trying to remember, he's big into like classical computational theory of mind. Not I don't think he likes the whole neural network stuff. So anyway, one of these days I want to write a paper called Fodor versus Fodor, where I critique his his arguments. But anyway.
In other words, our inner mental world of thoughts, qualia, and emotions can be modeled in terms of Hilbert space and quantum processes, the same processes that give rise to space-time and matter. Many suggest this is just a coincidence, but there have been hints that it goes beyond this. Within the past few years, a number of papers have been published supporting quantum mind theory. Information processing has been reported to exist inside microtubules, and another study has shown that tubulin protein molecules self-assemble via quantum tunneling. We even have evidence to suggest that quantum vibrations are coming from microtubules. Quantum biology researcher Anirban Bandyopadhyay said the microtubule appears to be a fundamental information processing device in biology. More and more evidence keeps coming out, supporting that there are quantum processes in the brain, cohering with the field of quantum cognition, that the inner world of the mind should be modeled with the properties of quantum mechanics. This all suggests quantum cognition is not just a way to model cognitive processes, but directly applies to the very nature of the mind and the brain. Stuart Hameroff also points out that since the inner mental world of the
So there's massive problems with this argument. So the details of the microtubule stuff, we talked about a bunch of that in the very first Bad Apologetics, so I'm not going to go over that again here. But in terms of the logic here, that there's a gap here, because let's suppose that Michael IP is correct in what he says, that that cognition can be usefully usefully and profitably modeled using quantum mechanics. And let's also assume that the sort of activity in the brain is fundamentally quantum because of microtubules and entanglement or whatever. The problem is that those two are completely different levels of description. One is talking about the effect of like superposition at the level of microtubules, that would have an effect on the activity of neurons. The other is at the high level of concepts and thought and mental processing. So quantum phenomena at one level is not straightforwardly going to lead to quantum descriptions of phenomena at the other level. The idea is that quantum phenomena might be necessary to describe the processing of the brain, but it doesn't follow that you're going to use the same formalism to model the end results of that processing. I'm just trying to think of analogy there. I mean, that's like, what is that like exactly? That's kind of like using a model of like using a medical model describing the way that our different organs interact to help us metabolize, to describe the spread of a disease. Or the spread of a disease through a population, for example. It's the wrong level of analysis, and it's not necessarily going to have anything like the same structure, even though it like emerges. I mean, this is why epidemiology is different to physiology, right? Even though it's sort of is emergent from the physiology and the interactions between people, but the mathematics of it and the formalisms and concepts are going to be very different. Likewise, even if both of these things, quantum mind and quantum cognition, are both true, they don't necessarily have any connection to each other because they're such different levels of description. And I don't think it's accurate for him to say that one like supports the other. I think they're totally independent of each other. And it would just be a coincidence, even if they were both true, that the same formalism was applicable at both levels. Because there's still many levels of hierarchy between them, even if you accept both theories.
I'm thinking like I don't know, like a contemporary debate in the UK is something like, should we have like the House of Lords in Parliament, right? Which is like this historic thing. And it'd be like saying, well, government is like an organism and it has all its functioning parts. And just like you can't remove someone's liver entirely and have them survive, well, if you remove the House of Lords, it'd be like removing the liver. And so, the organism would die, just like it. It's just like this really weak analogy.
Interestingly, that is almost exactly how people argued in favor of serfdom, because they're like, well, the different the different branches of society are like different parts of the body, and the serfs are like the hands and the feet, and they get things done. And if you abolish that, then how's work going to get done?
Yeah,
so people actually did think about this in that way, which is interesting. But I mean, yeah, it's a really bad analogy. And similarly here, the inference is just very sloppy. There's no clear connection between either of these ideas. No sound.
And from Wikipedia, they say, well, the field clearly distinguishes itself from the quantum mind, as it is not reliant on the hypothesis that there is something quantum mechanical about the brain. So they're trying to have their cake and eat it too. They're trying to say, we're using quantum mathematics, but we don't want to go on that risky limb that there's quantum biology in the brain, because everybody knows the brain's too warm, wet, and noisy to have quantum computing going on. Nonetheless, some of us do feel that the brain has quantum biology, and it has to. And for example, if a classical system would try to simulate a quantum system, you'd have exponential slowdown, as Feynman showed. It would be, you wouldn't be able to do it. It would involve so much computation. And what would be the point of using a classical system in the brain to simulate a quantum system if you could have the quantum system?
Quantum cognition seems to fit with recent experimental data of quantum mind theory. It recognizes the basic idea that our thoughts and emotions behave like quantum superpositions, not like physical objects or chemicals bouncing around inside our heads. Thus, the inner world of the mind, our thoughts, emotions, dreams, qualia, etc., would be distinct from...
As if the chemicals don't have constituent parts which also engage in quantum-like phenomena and are also described like, it's not like chemicals, it's like quantum. This is there's no overlap between the two, of course. They're different.
Yeah, that just doesn't make sense.
From the physical world, like how Hilbert space is distinct from space-time. In other words, there is a parallel...
It seems to me like IP is sort of conceptualized quantum physics and information theory is like these magic things that are like discrete from the rest of the physical world somehow.
Distinction.
Yeah, and he seems to think of them... Oh, sorry. He seems to think of them both as non-material in some way. And this is why he's saying things like, these quantum results disprove the existence of a real material universe and things like that. Like we talked about when Cam was on, that he seems to have this 19th century idea of what reality would be under physicalism, and that this is inconsistent with quantum results and information and other things like that. And I mean, maybe if that's where you're operating, that would be true. But I mean, we should be operating with 21st century, not 19th century physics, right? So this is the way the physical world is. It's quantum in nature, and it's relativistic in nature, and we can describe it using aspects of information theory and computation, but with limits and so forth. Not that these things are somehow outside the physical world and these sort of mystical phenomena that just exist somehow independently in some platonic realm outside of the material. That's not what the materialist or the physicalist says. So it really does feel like there's an underlying straw manning or misunderstanding or something going on here about what these things are and how they relate to the physical world.
Physical reality of Hilbert space, from which space-time emerges, to how the spaceless non-physical reality of our minds, our thoughts, emotions, dreams, is distinct from the external physical world. This is a common understanding with regards to the mind-matter distinction in philosophy of mind. No one can demonstrate how a mental phenomena would emerge from a physical substance. A feeling of pain can never be equated to an electrical signal. The mental experience of color.
There's research into what causes pain, right? And why it is that people can redirect their attention and reduce the amount of pain, there's all sorts of interesting physical correlates to people reducing pain.
Pain is a very complex and interesting phenomenon. Oh, I'm getting feedback again.
Oh, sorry, I'll mute that. There we go.
It sounds like there's a mini me who just repeats everything that I say. It's a bit weird. I did an essay on this for a subject in my master's, and pain is super interesting and not well understood. But was I going to say about that? Yeah, I mean, there's certainly a lot we can say about it. We can't ultimately say what gives rise to the subjective experience. We're a ways away from doing that. And I mean, probably if we could, we'd have an answer to the hard problem, I think, or most of an answer. So I'm happy to say that. But the thing is that no other theory can give an explanation as to like where pain comes from or how it emerges either. Like they just seem to assert it as a primitive in their theories. Like, well, it's just the sort of thing that immaterial minds have.
Yeah,
But
like
I
where
can
does
just say,
that
well,
exist in your ontology?
It's just the sort of thing that neurons give rise to in certain circumstances. Like, source for the goose and source for the gander are coming up again. Like, unless you have a better explanation, then it doesn't make sense to criticize the materialists for not having a good one.
Yeah, it's like and if like the qualia of pain just exists, like what kind of thing is that? Like how does it exist? Like why is it located in brains? Why, like there's so many questions that brings up. Why do rocks experience pain? Like it's just this thing that it like can exist? Why is it in neurons? Why
there's so many aspects of pain as well that don't make a lot of sense if it's somehow immaterial, like the referred pain, which is a extremely interesting phenomenon. People feel pain in different parts of the body to the part that's producing it. Or phantom limb syndrome, which is super interesting. People feel pains in limbs that don't even exist. I mean, like, how's that supposed to work under an immaterial view that, like, somehow I don't even want to speculate. And we don't fully understand how it works, right? But there's a notion of, well, there's well, I don't want to get into it too much, but there's a crossing of wires, if you like, about where the signals are being, because there's parts of our body that like project, that receive input from different regions. And then, so we sort of have a mapping, or actually multiple mappings in our brain to different parts of our body. So somatosensory, motor control, and so on, that like they're called the homunculus, or the, like tonotopic mapping and spatiotopic mapping is a general term. Anyway, so when these get confused, when a limb is removed and the input is taken over by a different part of the body, then we can have a confused experience by like the pain comes from a different part of the body, but it's projected to a part of the brain which used to process information from the limb that no longer exists and that's sort of lost out. And so we experience it as coming from a part that no longer exists. So there's these interesting effects that seem to be explicable, at least to a significant extent, by particular physical processes, that without that, it's just like, well, but why did it somehow change? Why did the percept change by losing a limb? Like, if the percept is non-physical, then what did the limb have to do with it, sort of thing?
Yeah.
Equated to electromagnetic waves which hit receptors in our eyes. There is merely a correlation between the two, but one cannot explain how qualia could ever possibly emerge from this. As John Searle says,
like, it's that assertion, like for him to say, like, well, I just can't conceive of it as something, or it doesn't follow from my worldview. So, like, that's a different claim from no one will ever be able to provide the successful reductions.
And that's just a brute assertion. Like, well, why should we believe that? I mean, and what's the alternative that's superior to? Because if we're going to say naturalism has no answer, okay, do you have an answer? Because if the answer is no, then we're on equal grounds. Like, no one has an answer. Okay, so it's just a hard problem.
how does a mental reality, a world of consciousness, intentionality, and other mental phenomena fit into a world consisting entirely of physical particles and fields of force? Colin McGinn says, the problem with materialism is that it tries to construct the mind out of properties that refuse to add up to mentality. Thomas Nagel says, if a mental event really is a physical event in the sense and nothing else, then the physical event by itself, once its properties are understood, should likewise be sufficient for the taste of sugar, the feeling of pain, or whatever it is supposed to be identical with. But it doesn't seem to be. It seems conceivable for any physical event. There should be a physical event without any experience at all. Experience of taste seems to be something extra, contingently related to the brain state, something produced rather than constituted by the brain state. So it cannot be identical to the brain state in the way that water is identical to H2O. In other words, no amount of introspection can ever be reduced to the chemistry of the brain.
There's nothing about introspection that leads.
Okay, before we go into that claim, but what are the conclusions Thomas Nagel actually draws, though, IP? Because Thomas Nagel does he agree with you that that's where his argument leads, or is he some kind of like property dualist, right? You know.
Yeah, isn't Nagel a panpsychist of some sort? I don't even remember, but
I don't know his exact views, but it
feedback
definitely
again.
Oh, sorry, I don't know his exact views, but it definitely isn't the quantum consciousness thing.
Yeah, dual aspect idealism. No, and also the I was going to say, yeah. So what he was saying there was a variation of the conceivability argument, where it's basically like you can conceive of a physical copy, an exact physical copy that doesn't have the experience, it doesn't feel like anything. So, I mean, the philosophical zombie arguments are sort of a variation of this. So this is, well, I don't want to be too strong there, but I don't think this is a good argument. Lots of people don't think this is a good argument because it's basically question begging. It's like, well, just because you can conceive of it, does that mean that it can actually be? I mean, some people don't even think it's conceivable. Other people think it's conceivable, but just not possible. I'm not even sure what it means to conceive of something because that seems to be pretty vague to me. So I don't actually care if it's conceivable. The question is it possible? I say no, basically just because, well, according to my worldview, that's not how these things work. So, and I don't see any reason to think otherwise. That you could have an exact copy of every physical detail, but somehow a different experience of it. I'm just, well, why would you think that's possible? What I want is an account as to how that could happen, not just an intuition that it could. To me, that's not a good argument for anything. So that conceivability argument there is not persuasive to me. And then it's sort of followed up, though, by an argument against some sort of identity theory to say that, well, the experience can't be the same as like the brain process that gave rise to it in the way that water is identical to H2O. And I agree with that because I think that states, that the experiential states are not identical to the brain states that give rise to them. I'm actually happy with that. Just like weather states aren't identical to the combination of the exact configuration of particles in the atmosphere that produce them. You could say that's an instantiation of that weather phenomenon, but I wouldn't say it's identical to it. And that gets us into issues about the nature of identity and so on. See, I'm not even sure I'm happy to say that water is identical to H2O, but that really gets into philosophy of language, which is
what about X, Y, Z?
Well, yeah, exactly. So are we on twin Earth or real Earth? And what do I mean by so I don't want to go there, but the point is that it feels like there's at least two arguments going on here, and one of them is a lot more plausible than the other. But the identity one really just pushes you away from some sort of identity theory, if anything, which I don't hold anyway, and a lot of people don't for this sort of reason. And then, but the former one, a conceivability argument, is, I think, quite question begging. It's just like, well, so what if you can conceive of it? Well, what does that establish? I don't think it establishes anything other than maybe we have good imaginations. Like, so what? The way that, I mean, it's just, I don't think it's a good argument.
Yeah.
Can ever be reduced to the chemistry of the brain.
There's nothing about introspection that leads you to sense that your subjectivity is at all dependent or even related to voltage changes and chemical interactions going on inside your head. Okay, you can feel, you can drop acid, you can meditate for a year, you can do whatever you want to perturb your nervous system. You can feel yourself to be one with the universe, and at no point in that transformation do you get a glimpse that there's 100 trillion neurons in your head or synapses in your head that are doing anything.
But what if we have?
So I think IP wants to say, like, well, this, like, even materialists admit that it's something different in that sense, right? And it's like, no, but that's the point, is like introspection is just this bad tool for like trying to figure out the way that our brain works. Like I'm never going to figure out just from focusing on what like the tactile like feeling is in my left hand, that the processing for that is going on in my right hemisphere, like just purely by introspection. Like the facts about that aren't there in the content of the experience.
I mean, that statement by Harris there is really in tension with what Thomas Nagel was saying, because Nagel is saying, like, well, it seems conceivable that you could have these experiences. You could have a material copy without these experiences. Whereas what Harris is saying is that introspection is not going to help you with this sort of question, because you just can't tell these sort of things. So, I mean, in a sense, I think that those are in tension, and I don't really think it supports IP's argument to put them one after the other.
I agree. But I think this shows like a lack of understanding of what's actually being discussed to like put them together in that way and be like, look, here's more proof of what it's just like this kind of quote but I don't even think it's intentional. Just like I don't think, you know, Jesus' disciples were lying when they thought that he'd resurrected. I think that this is just like the funky ways that human biases can work when we like come to evaluate evidence.
I mean, yeah, it's superficially, Sam Harris is saying something that sounds like it supports IP's view if you don't think about it too much. So it sort of goes in. Whereas if you think about it, it actually doesn't support his view at all.
Have it backwards. What if the problem is we think that mind arises from the brain, when in reality, what if the experience of the physical world arises from the mental world, correlating to how space-time emerges from Hilbert space? The correlates can no longer be ignored. The scientific evidence points to the fact that space-time and matter are...
When he says the correlates can no longer be ignored, do you remember in the quantum consciousness video when he was like, no amount of correlations between the brain and experience will like convince me.
Yeah, I was just thinking that.
Yeah. The correlates can't be ignored, IP.
But I just think he's misusing the word correlation. Correlation is a statistical relationship between two numerical variables, okay? Well, there are forms where you can apply to ordinal variables as well, but anyway. So you can't have a correlate between two things. It just doesn't make sense. Like, it's just the wrong word. Maybe he means the similarities or the analogy or something between them. It's not a correlation.
Emergent from the wave function in Hilbert space. In the inner world of consciousness and mind can be modeled as Hilbert space in the study of quantum cognition. Add on the evidence for quantum mind theory, and the most parsimonious explanation is space-time emerges from a shared inner mental world governed by a universal mind. The physical universe we experience is emergent from a necessary mind. This simply correlates to the idealist views of philosophy of mind. It is not matter that is fundamental and mind emergent, but mind is fundamental, and the experience of the physical world is what emerges from mind. Think of what we experience. It is a world of qualia. All we see can be described as mental without reference to any separate physical substance. It is completely impossible to describe the inner mental world in terms of physical interactions, but we can easily explain the physical world we experience in terms of qualia, shapes, forms, feelings.
Here's the girl eating an apple again.
All of these are mental in nature, and the physical world itself can be reduced entirely to mathematics in how we describe it. Keith Ward says it like this: any physicist will say that brains are mostly empty space, in which molecules, atoms, electrons, quarks, and other strange particles buzz about in complicated ways. It seems as though...
Well, it seems to me like this sentence is going to be trivially true at that scale for any physical object. You know, it's
correct. Yes,
brains aren't real. I mean, like if we're looking at the scale of like tissue or whatever, you know, like I'm not, like the scale I sort of operate at, and I go and prod my finger through a brain. I'm not going to go, oh, it's mostly empty space. But if I'm looking at, you know, the scale of like atoms and electrons and stuff, yeah, I'm going to go, oh, but I could do the same in like my table or in like diamond or lead. Like lead, think how dense lead is. Like,
yeah. Also, I want to raise issue with something IP said, which is that we can't describe the internal world of perceptions in terms of the physical world or like properties of the physical world.
Right.
But we can do the reverse. We can describe all of the properties of the physical world using, you know, properties or terms from describing the mental world. Like, and that's when he had the girl with the apple and like forms and textures and whatever. That seems just wrong to me. So some things we can, but a lot of things are not properties that we can detect in any direct way. Like what about mass or charge or things like that? These are abstract. Well, I mean, they're descriptions of reality, but that are also abstract in the way that we describe and apply them. And they're not things that we can have, like what does charge look or smell or taste like? It's not that sort of thing. Yeah, but it's not a sensory one, right? So I don't actually see how this makes sense. Like a lot of things we talk about in physics don't have any particular relationship to any of our perceptions, other than a very indirect way in terms of how we infer their existence based on. I mean, ultimately, yeah, it has to connect to our experience to be able to know about it, right? But I don't think it's correct to say that we can describe all aspects of physical reality just using the terms that we would use to describe perceptions, because then we just lose a lot of the language that we need to talk about the physical world. Like, I mean, Hilbert space is not part of our perception. Like, where does all this come from? Like, you need new language for it.
Just divinitatis, James.
Yeah, I don't know.
Yeah.
So physical objects, when not being observed, have no colors and no sounds, smells, or taste either. Sounds, like colors, are not physical events. Smells, tastes, or sensations. Things do not smell like, taste like, or feel like anything when nobody is smelling, tasting, or feeling them. The physical world, it seems, is totally vacuous. No colors, sounds, smells, tastes, or sensations. What on earth is left? This correlates
So
to
this is what I was saying before. What on earth is left? Well, literally every other property of things in the physical world. So let's maybe talk about charge and mass and spin and angular momentum, position, I said momentum. And I mean, those are just of microscopic objects. Like, you can mention any property you like of a macroscopic object that's not any of those things, like that we directly perceive. Like, what about genomic sequence for an organism, for example? That's a property. Or like mineral composition, temperature. You can go on and on of things that we don't directly sense. Like, these are the things that make up the physical world. So what on earth is left? Well, like, literally everything else. So I don't understand what this quote is supposed to be. It's just like, if you're not open to science textbook, like all of that stuff, that's what's left. I just get baffled by this quote.
If everything is just made up of stuff, then what is left?
Yeah, like, apart from all the stuff, what else is there? Like, what else have you got?
Apart from all the stuff that it's made of.
Published, where they point out that there are interesting similarities between neural networks and the cosmic web of galaxies.
Oh, this is the silliest point. Why would you expect, like, he's not saying
I looked this one up. But go ahead.
Yeah, it's just that he's not saying that God's mind is being simulated on the universe as like an architecture. So why would he expect to see this at all? Like, it's so bizarre. He's like, oh, it kind of looks the same. Why would the universe look like, can I just, if I stare at the pixels of the screen, am I going to figure out what kind of processor I've got in the computer? Like,
yeah, can you see the CPU in the screen? Like, well, he hasn't actually said it yet, so our viewers might not know what we're talking about.
Yeah. Astrophysicist Franco Vazza and neurosurgeon Alberto Folletti wrote an article on the similarities between both. Is the apparent similarity just a human tendency to perceive meaningful patterns in random data? Remarkably enough, the answer seems to be no. Statistical analysis shows these systems do indeed present quantitative similarities. They note the similarities line up with information processing, power spectrum analysis, total neuron to total observable galaxies, and in many other ways. If idealism is true, then this is readily explainable and fits with the rest of the data we have presented. Both form the same physical structure because both are emergent from an underlying mental reality. Under idealism, the brain is simply seen as the physical manifestation or second-person experience of a first-person conscious experience. And it fits with the idealist view that the whole universe would be structured in the same way, since it is also the emergent physical manifestation of mind.
But isn't everything supposed to be the emergent physical manifestation of mind? So wouldn't everything look like this? Like, literally everything in the universe? Why is it just the universe as a whole and brains? Like, why is it just those? Anyway, let's talk about this paper, because this has got to be well, actually, that one with all the arguments about it being, it's a tie, maybe, I don't know. I mean, this paper is more scientific, but it's just so silly. So let me show you. The quantitative comparison. I don't know why this paper was ever, this is just a waste of people's time. Okay, so quantitative comparison between the neural network and the cosmic web. So again, what they actually did is, like, the methods were okay. It's just that, it's just like no one stopped and asked them. It's basically that adage, that they kept asking whether or not they could, but they didn't stop to ask whether or not they should. Like, why did they even do this? This is what I ask you. What scientific question is this study asking? That it basically seems to be like, well, some people say that the cosmic web of galaxies and the web of neurons in the brain kind of look the same. So let's have a look. Like, but what's the question? Like, it's so poorly defined what they're actually asking for, what they're trying to find here. So look, here it is. These are what's the word I'm looking for? Microscopic images of brain slices stained in. I don't actually know exactly what staining is being used, and I'll come back to that. And these are images of the cosmic web of galaxies. So these shows the density of matter. So these correspond to different galaxies, essentially. This is a very far out zoom. Now, what they've done here is that they have taken what they call the normalized density contrast. So the difference in color or pixel intensity, because these aren't colored, but the darkness of the image and how that varies across the image in a decomposition. So it's actually a bit similar to the cosmic microwave background radiation spectrum that we looked at before, because these are in terms of wave numbers. So and a power spectrum. So it's actually kind of similar to that, but with different data. So it's not looking at it's not looking at anisotropies in the cosmic microwave background radiation. Rather, it's looking at density contrast in these images of either the cosmic web or of the micrograms of the cells in the cerebellum and the cortex. So here's the results here. So they've got cosmic web for dark matter and for baryons, and then cortex and cerebellum. And notice that because they've got different magnifications here, ×4, ×10, and ×40, they've got these shown on the graph as well. So there's 2 different regions of the brain at 3 different magnification levels compared with 2 different types of matter in the universe. Now, you'll notice that the ×4, which is here, and the ×10, which are the dashed lines here, don't sort of fit very well with the cosmic ones. So they just ignored those. So they just looked at the ×40 slices, the ones that kind of fit, right? So they just, and you can kind of see looking at it here, if you look at this image, it looks more similar to this one than these ones. And that's basically what they're looking at, because they're looking at the density contrasts. Okay. The thing about this is that that's entirely dependent on how you stain this image, because these are stains. These are pigments that have been picked up by the neurons and show where the density of tissue is, like mostly the cell bodies, I think. I'm not sure what these lines are here. How you stain the tissue affects how this image looks. If you stain it differently, it will look completely different. Most of the tissue is transparent, so it's not. I mean, yes, it does relate to the density of the tissue, but it's also largely determined by the nature of the stain rather than and the zoom level essentially that you're looking at it, not just the density of the tissue. I think that's probably less of an issue for cosmic web images because obviously they're produced very differently, but that's definitely a huge issue for these microscope images there. So already I'm basically like, this is just entirely a product of how you've produced the image and the zoom level you're looking at. But then they show, well, these spectrums are kind of similar, and they compare it to other things like sky clouds and water turbulence, and they show that, well, they're kind of different. But like, what is the significance of this? It's just like you've picked the one that it works for, the ×40 slices, the only one that they're showing here. They also mentioned that here, it should be stressed that the power spectra are free to be slid horizontally in the plot in the sense that the reference scale is decided a posteriori. So although they're showing these on top of each other, that doesn't mean anything because they're measuring different things. So they've just slid it so that they're on top of each other so that they look more similar. There's no meaningful sense in which they're on top of each other. It's their shape that they're really comparing. So that's not exactly wrong. It's just like, it's a bit little misleading if you don't realize that. Was there anything else I wanted to say about this? Oh, yeah, they do a connectivity analysis as well, which is completely bunk because it's just based on density, which has really nothing to do with... It's based on proximity, which, I mean, yeah, closely...
arbitrary scale levels.
And also the closer the neurons are together, the more likely they are to be connected, but it's not the same. And also we're looking at a 2-dimensional slice of a 3-dimensional object. So the fact that they're close together in this image doesn't actually mean they're close together necessarily because they could be at different depths. I mean, I guess they happen to be similar to both be in the slice, but you lose that information there. So I think this is not really worth anything because they've not actually done a connectivity analysis. And I'm not entirely even sure how to interpret these plots here. But so the main result that IP showed was this one here, basically showing that basically these lines are on top of each other if you look at the ×40 ones with this particular stain, and aren't too fussy on the fact that you've slid them into position because there's no the starting point is kind of arbitrary because you're comparing wave numbers in 2 different systems. So what does this tell us? I think it tells us absolutely nothing. This paper is worthless. Like it's not clear what the point of it is. Like, so what? Like, what would you expect to see? Why do you expect to see this result? How they showed a few different systems there, but I don't know how many they could have compared to. Like, they showed like 3 different things, other natural systems and their power spectrum analysis. But like, how many other hundreds of systems could you look at, and how many of them would show this similarity? It's just like, why? It's just like it's like, why? It's so pointless.
I found something that might this might be revealing as to why.
Weird.
I think I'm sure I was like 12 or something when I saw that opening on The Simpsons, and that definitely, like, philosophically as well, made me like think about scales and things, and influence. Like I could have definitely bought into this like universe looks like a brain stuff at one point.
That what we saw there, basically, by the way, is based on I think it was a documentary called Powers of 10 that aired decades ago, where they did that, but not where they put them in the right order, where they didn't like, because they shifted them out of order here, so that when you got to like galaxies, it went back to atoms. So it sort of, that's how it went like that. But anyway, it's interesting if people want to look that up. There's more modern versions of that as well on YouTube. It's really cool to look at and gives you a sense of scale.
Scientific evidence. The conclusion is undeniable. As Max Planck said, all matter originates and exists only by virtue of a force. We must assume behind this force is the existence of a conscious and intelligent mind. This conclusion has already been reached by cognitive scientist Donald Hoffman. His model argues that given all the data we just discussed, the best explanation is space-time is emergent from consciousness.
The top was the conscious agent dynamics, long-term behavior. And then if you write down the wave equation for the free particle in quantum mechanics, it's exactly the same equation. This is the non-relativistic case. You can actually read off a one-to-one mapping between non-relativistic quantum mechanics and this agent dynamics. And I won't go through it. This is the actual read-off of the equivalence between space and time and aspects of consciousness. Now, that's non-relativistic, and I'll close by the relativistic. I mean, the ultimate thing is we want to have a relativistic quantum theory falling out of a theory of consciousness. And the direction I'm going on that, and I'm starting to collaborate with Chris Fields and some others on this, is to actually take a system of 2 conscious agents, and it turns out it can be represented by something called a geometric algebra that I've written down there. And that geometric algebra is precisely the geometric algebra that describes the relativistic quantum free particle, massless particle. So the idea is that we can get space-time coming out of this, Dirac spinors, and ultimately, you know, using Penrose twisters, maybe even quantum gravity. So the idea is that this program, for it to be successful, has to start with consciousness and give us all of quantum physics. And then we've solved the mind-body problem going the other way.
The paradigm is shifting, and a new consensus is emerging. The old notions of the physical world being fundamental must be abandoned.
I want to say as well, like, I find it interesting how he thinks that with this theory, he's on the forefront of like a paradigm shift in science as well. And it's like, it's not to say that current science is never going to change and fundamentally be in a fundamental way, which like does away with a lot of the ways that we think about the world, because that's entirely possible, to quote Joe Rogan. But I mean, like this isn't going to be it. Like IP's specific, maybe it's going to be to do with quantum stuff, but IP's arguments here aren't going to be it, because they're just like not sound. They don't accurately represent what the science is showing. The formalisms he's put together weren't even really in valid form. They're like self-contradictory in different ways. Like this is in the same way, like if I think of the way that someone might present to me evidence that the Earth isn't at the center of the universe, it just doesn't contradict itself in the same way that like some of these uses of like information theory and the computation stuff do, and the use of philosophy and stuff like that. I don't think that this is going to be the paradigm shift. Well, firstly, because I don't think it's true, and I think that that's going to, I don't know, maybe there's a whole debate there around like anti-realism and stuff in scientific theories, but I just don't think that IP is on the forefront of this paradigm shifting wave that he seems to think he is by saying that sentence. You know, the paradigm is starting to shift, and he's the canary in the coal mine.
There's the stuff that IP presents is a combination of fringe theories and legitimate science that is being misrepresented, plus dubious philosophical deductions from, well, both of those actually. So I don't even know that there's a clear paradigm that IP is even presenting, because it's a combination of like quantum cognition, quantum mind theory, Von-Neumann Wigner interpretation of quantum mechanics, the holographic principle and quantum gravity, and at least one. And then this whole thing about like galaxies representing the brain, which is just totally not even related to that. And so it's just a bunch of things that are sort of thrown together to just sort of get to a general point of, you know, the universe is emergent from an underlying mind, even though they're coming at it from very different directions and don't have any particular relationship to each other. Some of it's fringe, some of it's mainstream, but misrepresented. It's a bit of a mess, to be honest. And that's why it was doing my head in to try to understand how this is all supposed to work. Because I still don't really understand how it all fits together, because there seem to be internal conflicts, like whether we as the observers are collapsing the wave function or God is like doing that, and how our free will relates to us being like in God's simulation, and then why that would reflect a brain when God doesn't even have a brain because he's not material, and it just so many things just don't make any sense about how they're supposed to cohere together. On his worldview. Did we finish out the video, or
no? There's like a minute more to go ish. Something like that.
Yeah, let's finish it out.
That in light of the new scientific data, consciousness is fundamental, and the experience of the physical world is what is emergent. The data has been building up in several fields, from philosophy, quantum physics, neuroscience, biology and chemistry, and cosmology and holography. A new paradigm in physics is emerging, one that turns the old materialist notions on its head. We are not the accidental products of the blind workings of matter. The workings of matter are the products of the mind. The evidence leads to the conclusion our universe is an emergent world from an underlying consciousness. The paradigm is shifted, and the way we view ourselves and the universe will never be the same.
Can we look at some of the comments on this video?
Yeah, sure.
When I was 16 or 17 and getting interested in quantum mechanics and some of these other questions, and still religious at the time, I would have eaten this stuff up. This is exactly the sort of thing that I was interested in. Although at that time, YouTube was barely a thing, so we didn't sort of have this stuff. So partly that's why it concerns me about like what people are getting out of these videos, because I mean, they're not going to get a good understanding of the science for a start. There's some really interesting comments here that are illustrative of the state of the sort of the discourse here. IP uses atheists to explain weird stuff and provide substance. Atheist YouTubers use Christian content and bash them for 10 plus minutes with no substance. Well, I think that we've at least avoided that stereotype, since we've gone for 8 hours now, and I think there's a lot of substance here. More evidence of an omniscient creator heavens declare his glory. Okay.
My man.
Here we go. Yeah, IP. This video goes beyond apologetics. You have masterfully incorporated domains of science into a theistic worldview that challenges the intellect in a way that complements how your video on the problem of evil feasts the soul. Your videos don't fail to inform my faith like the best church services. Thank you.
Damn.
Just
like don't fail to the church services fail though, but that's the Christianity. Like what
yeah, I know.
Jesus
I was wondering about that.
Thou shalt, you are Peter, on whom I shall build my quantum videos. Like. No, it's his church. Like, this isn't Christianity. I mean, you can say, well, this is the true religion, but yeah, Christianity is church and singing your hymns and loving your neighbor,
reading the Bible.
Researching quantum.
So this is interesting. I love watching this stuff baked out of my skull at 4:25 a.m. What does that mean? Like,
well, I think 420 is obviously the
yeah, but it's not
weed
4:20.
time.
It's 4:25. So I don't.
Well, maybe he's high by then.
Yeah, good point. The thing is,
mean,
though, I don't know exactly what to take out of that, but it's like, are people thinking critically about this? I guess is the point from comments like that. I had to spend some time watching quantum physics video lessons on Khan Academy in order to keep up with this great challenge. Now, that's good if it does lead people to actually learn about quantum mechanics. I'm just wondering what sort of mindset they're bringing to those videos.
So, yeah, she didn't answer.
Came back, watched again 5 months later, and now keep up. Interesting.
The Hebrew noun for beginning also means head.
So in any event in the universe occurs in God's head. Got to stop smoking herbs. I don't know if these people are actually like stoners or they just... Years and years ago, I said, one day we will discover God and physics is the same thing. Like that's just the sort of thing that my grandfather might have said. It's just like, just sort of random, like weird things that people get in their minds. Like, well, what does that even mean? God and physics is the same thing. What? Atheism is in crisis mode and you're to blame. Thank you. Dude, best video yet. I love the end where you bring the full summary of the evidence, not only in video, but all your others concerning idealism, quantum physics, and the introspective arguments case of the soul, and just let them have it. There's a lot of evidence with a lot of cumulative force. Epic, man, just epic. I think that's... and I think that's sort of the attitudes a lot of these people have about these videos.
This guy.
They just...
This is one of the influencers.
What do you mean, one of the influencers? I don't know.
He's
him.
one of the apologists who is in the inner circle of quantum theism.
I didn't know there was such a thing.
There is an inner circle. We had one of the horsemen of the apocalypse here in the chat, Christian Idealism, Kyle Olander, earlier, and he's also direct messaged me on Facebook. I'm probably unhappy about what we're doing and telling me why I'm wrong or something.
Anyway, I just think it's interesting to see how this stuff's being received by the the audience here, and it's just a lot of people just lapping this stuff up and loving it, and I worry about that in terms of the effect it's having on people's understanding of science and the relationship between science and philosophy, and critically analyzing arguments, because it's just really hard to even make out what IP is even arguing in these videos. You can get the gist of it fairly easily, I think. But in terms of like trying to work out what the argument is supposed to be, it's very hard. I had to watch these videos over and over again, just like, what's he saying? I don't understand.
I know it's a little bit, it's in the same topic, but this is one of Jonathan Ratz's videos on it. And I think if I can briefly give you the idea of it in a minute or so, because this is particularly peculiar. So this is that kind of group of people. You'll notice it's 44 minutes long, so I'm going to skip through some key parts. But I've watched this several... Actually, when I was leaving Christianity, I was sent this video. It's not public, and I was sent this video as something to like keep me in. Like here's viable quantum stuff.
The music is just...
Chapter 1. Sentient Dream Alters. In the movie Inception, the action between the characters occurred in a shared dream. One of the characters was different from the others, though. Maul, the deceased wife of the main character,
it's like
Cobb,
a creepy ghost
entered into
story.
the dream through memories in Cobb's subconscious. Despite this, she displayed motives such as jealousy, and was even able to come up with intricate plans the way any of the real people in the shared dream would. She behaved as though she were a real person, even though she was a figment of the main character's subconscious mind. The reason our minds cannot access the rest of the universe, Kastrup argues, is that we are in effect much smaller dissociated alters of this cosmic mind. Chapter 2. Emergent Spacetime. But where does Kastrup get this idea of a cosmic mind? Motivating this view are the last few decades of discoveries in experimental and theoretical physics. Many people naively think that the world is composed of tiny bits of matter, floating in an empty void, and that everything else emerges out of that. However, this is not the picture that physics has been painting in recent years.
The future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with.
In 2007, tests of Legate's inequality were conducted by a group of physicists in Vienna, Austria, to test for quantum non-realism. The results falsified realism within quantum mechanics, establishing that quantum particles do not actually exist prior to measurement. More disturbingly still, the field of quantum gravity has been discovering of late that space-time itself...
And like people will know if they've been here the whole time that we have like addressed all this stuff earlier. It's like the same. It's the same with the NDEs where it's like Pam Reynolds or, you know, like this is Pam Reynolds.
Those clips were exactly the same as the ones that IP used from that interview there.
But it gets creepier.
That
because
big think one, that was the same as well.
Well, it gets creepier though because it's about how demon and yeah, same Sean Carroll quote here. Here is same zeros and ones information, but we're going to talk about how demons are encoded in the quantum information, and that's the part we want to get to. Not here. Oh, here we go. So here's
from all over the world. Despite coming from vastly different cultural and national backgrounds, the same themes and motifs kept cropping up in their dreams, as if drawing from the same unconscious archetypes. A stark example of this was the story of the so-called solar phallus man, which appeared in the dream of one of Jung's disturbed mental patients. Despite being crass and politically incorrect, this case provided an unusually stark example of the collective unconscious phenomenon at work. The dream contained a divine phallus hanging from the sun, spraying the earth below and thus bringing life to the earth. Some months later, an ancient Mithriatic text was discovered and translated, with the exact same symbolism and imagery. As the publishing of this text was rather obscure, it had not yet even occurred at the time of the dream. Jung was quite certain that his patient had never seen it before, but the identical imagery showed up in the patient's dream and was far too similar to chalk up to mere coincidence. Jung's theory of a collective unconscious, however, explains this nicely. The same archetype and other figures
and then we've got
fantasies
angels.
brought home to me the crucial insight that there are things in the psyche which I do not produce, which produce themselves and have their own.
And there's stranger things
at the collective level rather than at the personal level. And if they do individuate below the level of our personal minds, attached to our brains, then what is to prevent them from existing in a completely autonomous fashion, lurking in the Hilbert space beneath space-time, long before we were born and long after our deaths?
Hello?
So demons.
So demons come from Hilbert space? Is that what I'm getting here?
Yes.
Unconscious. Could symbols be used to entangle one's mind with one of Tholi's sentient agents living in the collective unconscious instead? If this were possible, how would we know?
Why is it the Eye of Sauron? Like, what's this guy?
Because it's a symbol from the collective unconscious, you know. J.R. Tolkien gave, and so did whatever his name is, the director of the film, obviously, but gave birth to, you know, the when we think about good and evil, it's the Hilbert space interacting with our quantum consciousness, and we realize the symbols the demons use, and Jesus.
I can't even articulate anything in response to that other than just okay then.
I mean, in fairness, I have skipped.
We have been skipping around, but I'm honestly not convinced based on what I have seen that it would be more cogent if I watched the whole thing. Maybe that's uncharitable, but this is getting a bit nutty here. So,
and if consciousness individuates minds in the manner Tholi's research suggests, then the probability of such agents already interacting in our world would be far higher than many are willing to admit or accept. Indeed, given the picture this evidence paints, there is no reason to suppose that this is not already the case.
WikiLeaks? What? And who's what? What?
What's well, this is part of a worldview where, you know, like, so you know, this is interesting as well because someone who's very different philosophically, you know, Jay Dyer, who does the transcendent, he's like way into like the Hollywood. They're all in like, you know, like demonic pedo rings and stuff like
Yeah,
that.
right.
And obviously, this woman's going to be telling us about some of this as well. But it's just that philosophically, for the IP quantum people, this is to do with Hilbert space, whereas for Jay Dyer, it's to do with his transcendental argument for God. But it's all built into like a conspiracy theory worldview. It's like, and it's fascinating that this is what people do. Because I can see how I would be inclined towards it in certain circumstances as well. But it's funny from this side, I suppose, to look at it. And
yeah, I don't know. I just find it a bit sad. This is people spend their time on this and eat this nonsense up. Yeah,
I kind of want to see what she's got to say, but then I will.
All right, let's give it a listen.
Boy who lives in me, and he says the things that I don't want to say. He was born, just a few months ago. I think he was born out of rage. He was conceived in rage. So he bashes everyone. He threatens to beat people, and he's violent.
It must be nice to have like an ignorant loudmouth who you can just sort of blame every...
He wants to be blamed. I don't want to blame him. I ask him to leave. But he can't. He's here for a reason. People have brought him out. People conjured him up. Now he won't leave.
You let us in. And now you are going to have to let us stay.
What's with all these movie scenes? Like,
David.
Are the people who make these Hollywood movies like in on all this stuff? So they like put these things in the movies so that you can.
A higher, lighter, tastier cake. Why, fresh eggs, of course. But remember, all cake mixes are not alike. Betty Crocker cake mixes are different. They call for your eggs, added by you at home. It's the only national cake mix brand that lets you add the eggs. There's a reason why there are no dried egg whites, no dried egg yolks in Betty Crocker cake mixes. When you add the eggs, you're sure to get finer cakes most consistently. 9 out of 10 homemakers in recent tests said Betty Crocker cake mixes gave them bigger, taller cakes than the dried egg cake mixes they tested. Yes, and better tasting cakes, too. Try Betty Crocker Party Cake Mix for yellow, white, or spice cakes. And try Betty Crocker Chocolate Devil's Food Cake Mix for rich, moist devil's food with genuine fresh egg goodness. Get Betty Crocker cake mixes today.
With like creepy
If you like this video, subscribe.
What's Betty Crocker got to do with it? Did I miss something?
So, I guess I'm going to have a hard time justifying what I just made everyone go through. But I guess my point is, the part of the reason to debunk some of this, like, I don't know, I don't debunk some of this, like, IP stuff, is that, like, okay, maybe, like, you might think his views are pretty tame, but there's actually quite a large cultish following of people with very bizarre beliefs, like, who, when they're doubting some of that stuff, like, imagine, it's not too hard for me to imagine because I was in that headspace like not too long ago, but thinking like, like Nicki Minaj is the way she is, or whoever that was, if it was Nicki Minaj, is because she's like possessed by demons. So then like every time a woman decides to like present that way, you think they're like got the Jezebel spirit in them or something. And like it's just this mess. And then like you're doubting, so you're going to move away from that belief. But then you go to an IP video and you watch like 10 minutes of him talking about all this stuff. And you're like, oh yeah, I'm convinced it's true again now. Like it's bizarre. Sorry,
that whole
James.
quantum demon stuff would make some interesting, could make some interesting horror stories. I mean, I think there's some material there, but like to actually believe that, it's just, why are you doing this to me at 1 a.m., Nathan? I'm struggling.
Yeah, I'm sorry.
No, that was interesting. Let's finish out by looking at Michael's opening statement in this T-jump debate. It's not very long.
Do you want to do the T-jump one or the most recent one?
I mean, I don't even know. I can't. They're all pretty similar. So I think you actually probably looked at them more recently, so you can just pick. I do recall the opening statement's pretty similar in both of them, but the T-jump debate as a whole was sort of driving me to scoop my eyeballs out with a spoon. So I don't recommend watching that. But the opening statement is illustrative of how he puts this together as an argument. So that's why I did want to look at this.
So it's worth maybe mentioning that just in terms of our document, where am I? So IP has like this opening statement that sort of combines these arguments together. So this is the first time, at least we've got in our document in February 2019 of him using this opening statement. Then we've got him in October 2019 using like the same one. Against Matt Dillahunty using the same one, and then most recently against Apostate Prophet using basically the same one. But what I will commend him on is he seems to have changed some of his later on slides, which are like to do with like formalizing the argument into some like logical form. And he's changed some of the premises so as it seems to at least make like more sense as like a valid argument. You don't have to do that interpretive work to like figure out. So I would have at one point in time critiqued the slides in this where he's like, here's the argument, because it doesn't really make sense. But now he's changed that into like some actually like valid arguments, which is good, and we don't have to do that interpretive work. So at least he is modifying and updating his beliefs.
He's responding to feedback, which was good because he says that in one of the more recent videos. So I do appreciate that. Right. Yeah, most of these debates are not good. The interlocutors don't make much of an effort to actually listen to or like research what he's saying. So I think that they did a poor job. Although the one with, which one was it? Destiny. He at least is nice and asks some decent questions, but like he doesn't really know what most of what IP is talking about, so he doesn't have much to say about it. So it's not really a debate. So let's just look at this opening statement. It just gives an idea of how he puts this together, and then we can finish up. Because again, we're going to be having a discussion hopefully in a couple of months with Michael, so we can go through some of the back and forth aspect of that. Hopefully in that discussion. So I don't actually think there's a lot of value going through these debates because there's not a lot of substance there, but the videos that Michael has done that we've been discussing for 8 hours now are much more substantive. But I think it would be good to finish out with like an encapsulated version of that to see how he's using this.
Yeah. Well, I'm going to be moderating in that debate, not discussing. And as moderator, I have a strong ethical principle of not jumping in and attacking with my personal view any of the people in the discussion. So I'll be. That
would differentiate you with some moderators that I've seen in the past.
Yeah, I will be facilitating, and I'll be making sure you get a hard time of it, James, from the questions and things. So.
Looking forward to it.
James, let me know when you're ready.
I can see the presentation.
Ready. All right. Well, I'm happy to have this conversation today because I've been turned down multiple times to debate the topic. James knows from one back in the fall. The debate topic tonight is, does God exist? Now, as a classical apologist, I'll be arguing a theistic or deistic worldview is more probable given the evidence. So I don't claim I can prove God exists. I won't be arguing specifically for Christian theism tonight. I'll be arguing for basic theism or deism, and I'll present 3 arguments that God exists. My aim is to show that deism or theism is the best explanation given the available data. So the first argument I'll present is the digital physics argument. Okay. In several of my videos, I've presented various lines of evidence. Space-time is emergent and not fundamental. So I'll go over some of that. In the hunt to rectify quantum mechanics with relativity, physicists discovered something known as the holographic principle, a theory which suggests the entire 3-dimensional universe can be seen as 2-dimensional information. So in other words, the whole 3-dimensional universe, the particles that make up reality, would emerge from underlying information in quantum field theory. In 2017, a peer-reviewed study published observable evidence of the holographic principle. From looking at irregularities in the background radiation, their team found that simple equations of quantum field theory could explain almost all the cosmological observations, is marginally better fit than the standard model, and it can potentially explain apparent anomalies. I won't go into that much right now. The emergent features of spacetime can be seen elsewhere. A study from later that year argued quantum entanglement is an inevitable feature of reality. quote directly, they say, we show that any theory with a classical limit must contain entangled states, thus establishing entanglement as an inevitable feature of any theory superseding classical theory. Thus, the information between particles does not seem to be affected by space, as it can be transferred instantly, implying space is not fundamental for the underlying world of quantum mechanics, but an emergent phenomena of the classical world that would only exist after measurement. Now, I can argue the emergent nature of matter and space-time from numerous areas, be it quantum mechanics, holographic principle, Brian Whitworth's features of virtual reality versus an objective reality, or in many other ways. But the idea of space-time as emergent is not fundamental, is accepted by more and more physicists every day. Physicist Hyein-Suk Yang says emergent space-time is the new fundamental paradigm for quantum gravity. Thus, the most up-to-date evidence suggests all of what we experience, space-time, matter, all seem to be emergent constructs of the classical world, not fundamental aspects of reality. But then the question becomes, what does space-time emerge from? Well, essentially, the classical world emerges from the underlying information or the universal wave function of the quantum realm. However, interestingly enough, the same underlying features have been seen to parallel conscious thought processes. In 2009, physicist Dietrich Ertz took this one step further and published a paper noting that our cognitive processes can, quote, be readily modeled using the mathematical formalism of quantum mechanics, end quote. In other words, our inner mental world of thoughts, quality, and emotions can be modeled in terms of Hilbert space and quantum processes, the same processes that give rise to space-time and matter. So space-time and matter are emergent from the quantum wave function in Hilbert space, and the inner world of consciousness and mind can be modeled via quantum processes in the study of quantum cognition. So this would suggest the evidence implies emergent space-time would be indistinguishable from the same properties of a mind. So the simplest explanation is the universe is just emergent from a mind. If what the universe emerges from resembles a mind, it is far more parsimonious to accept it is in fact. This is also backed by the recent work of astrophysicist Franco Vazza and neurosurgeon Alberto Felitti, wrote an article, and Vazza has written papers on this as well, on the similarities between neural networks and the cosmic web of galaxies. There they show the properties of neural networks in the brain are similar to the cosmic web of galaxies, something we would expect if the universe is emergent from a mind. So here's a formal representation of the digital physics argument. To save time, I won't go into it here, but I think I've presented enough evidence to back up the case the universe is emergent from a mind. The second argument I'd like to present is something called the cosmic conscious argument. It was named for Eugene Wigner's work. Premise one, contingent minds either have personal explanations or natural explanations. This is not too controversial. Almost all theories of mind either hold to reductionist type views or believe consciousness is irreducible as it is and would have to come from a fundamental source. Premise two, quantum mechanics and other fields of science imply the natural universe is emergent from information processing and consciousness. This is the most controversial premise. Essentially, numerous experiments in quantum mechanics imply consciousness plays an important role in wave function collapse and the appearance of material reality. We can get into more of this during the discussion section. I'm more than happy to, but essentially experiments such as interaction-free experiments, delayed choice quantum eraser experiments, the violation of the Legan inequality, and the confirmation of the Kochen-Specker theorem lead to the inference consciousness would cause collapse. Now, this is a philosophical inference, let me point it out. Now, to preempt the objection, interaction and decoherence alone is not enough to explain wave function collapse. So, for example, one book here notes that does decoherence solve the measurement problem? Clearly not. What decoherence tells us is that certain objects are classical when they are observed. But what is an observation? At some stage, we have to apply the usual probability rules of quantum theory. Maximilian Schlauhauser says in his extensive paper on decoherence that decoherence arises from a direct application of the quantum mechanical formalism to a description of the interaction of a physical system with its environment. By itself, decoherence is therefore neither an interpretation nor a modification of quantum mechanics. And thus, as John Von-Neumann, Henry Stapp, Fred Kuttner, Bruce Rosenlund, Bernard Hash, Richard Cohn-Henry, Stephen Barr, Ian Squires, et cetera, all argue this philosophically leads to the conclusion consciousness ultimately causes collapse in the long string of things. So what follow the appearance of material reality is emergent from consciousness, not the other way around. So conclusion one, the natural universe cannot be the explanation of contingent minds, since materiality emerges from consciousness. And premise three, the explanation of conscious minds is personal. This personal source is what we call God. Conclusion, therefore God exists. So unless Tom can demonstrate consciousness is emergent from the brain, and trust me, I am more than willing to go over numerous pieces of data and studies in neuroscience. I just finished reading John Eccles' book even. So unless you can show that consciousness is emergent from the brain, the most likely explanation is consciousness is irreducible, and thus contingent minds, like all of us, would most likely, not prove, but most likely be contingent on a larger consciousness that controls reality and brings other contingent minds into existence, who we call God. Third and finally, I'll present the same line of reasoning via basic philosophy through the introspective argument. Premise one, the mind exists. This one's not too controversial. As Descartes said, I think, therefore I am. Premise two, the properties of the mind are not that which matter can have. So far there has been no evidence or a plausible theory that can show consciousness or mental properties can reduce to matter. As John Seary even has to admit, how does a mental reality, a world of consciousness, intentionality, and other mental phenomena fit into a world consisting entirely of physical particles and fields of force? Colin McGuinn admits, the problem with materialism is that it tries to construct the mind out of properties that refuse to adapt to mentality. there is simply no evidence consciousness can emerge from matter. All neuroscience can show at best is correlation, not causation, and unfortunately, all materialists tend to confuse this. However, the properties of matter we experience can easily be reduced to mind, since all of what we experience is a mental world of qualia, sounds, etc. None of these are physical, they are mental phenomena. We essentially experience a mental reality, so there's no reason to posit a separate material world beyond our mental experiences. As Keith Ward says, any physicist will say that brains are mostly empty space in which molecules, atoms, electrons, quarks, and other strange particles buzz around in complicated ways. It seems as though physical objects, when not being observed, have no colors and no sounds, smells, or tastes either. Sounds, like colors, are not physical events. Neither are smells, tastes, or sensations. Things do not smell like, taste like, or feel like anything, but nobody is smelling, tasting, or feeling them. The physical world, it seems, is totally vacuous. No colors, sounds, smells, tastes, or sensations. What on earth is left? This idea can also be explained via David Hume's bundle theory, which we can get into later. Thus, our first conclusion is mind is not reducible to matter. Premise 3, substance dualism is false. I believe Tom agrees with me on this, but you can argue via Spinoza's interaction problem. If there are two substances, they have to interact via shared property, but if they share properties, they're just different aspects of one substance. So conclusion, all is mind. If all is mind, this correlates with the previous two arguments that I gave, that there is a larger governing mind that brings us contingent minds into existence to experience and operate in reality. So if Tom thinks God probably does not exist or there's no reason to believe in God, he must tear down these arguments and offer a more probable explanation, not just another possible explanation, but something more probable and parsimonious. Given what I've seen in this past debates, I will contest this cannot be done. And the best explanation, the most probable and parsimonious, is a theistic worldview. And with that, I'll yield back the rest of my time.
You bet. Well, thanks so much.
Pause that there.
So there's nothing really new there in terms of, I mean, which is fine. I'm not saying there shouldn't be, there should be, but that's all stuff that we've discussed before. It's just interesting to see how he fits it together. It's still a bit hard for me to work out the connection between the holographic argument, the emergent, well, I guess that's the emergent universe argument. Then there's the quantum consciousness argument, and then there was the quantum stuff, which I still didn't really understand how it fits in. But yeah, you can see he appeals to the same papers that we've discussed and uses similar quotes, and is trying to paint a picture here that materialism is untenable. It's interesting to me that some of the turns of phrase that he uses are, I think, quite clearly borrowed from Craig. So that there was a couple that I noticed, but one at the end there where he says he must tear down my arguments. Craig says that. I think there were a couple of others, but that one. That's one that I remember. So, I mean, again, not necessarily a problem. It's just that I noticed that. I think he's channeling Craig a bit here, which is interesting.
I noticed there were a few things he said, which were like, like he kept saying follows whatever it is that Craig says inescapably. It follows inescapably, and tying the threads together and Yeah, there were at least 3 Craigisms I think I heard throughout that kept being used, which was interesting.
Yeah, and there's just, I think in more recent presentations he's condensed that a little bit, but there's still a huge amount of material there. And the thing is that even in a 2-hour debate, there's just no way you can discuss all of that stuff. You could draw on a few threads of that, but so I don't know. It'll be interesting to see how our discussion goes when we get to chat about this. But I mean, my plan would be to focus on a few key points of that and try not to get too distracted by irrelevancies or other aspects that may be less important. But yeah, it'll be interesting to see how he how that discussion goes, and if he has anything to say about this video here. Because I don't think that he's got much of a substantive response from atheist YouTubers or commentators to his argument. As we mentioned, the debates, he doesn't get that. And I can empathize with that because in some of the, I can plug my book again, some of the stuff that I discuss in my book, particularly the novel contribution I make about the RHBS model of the resurrection. I have discussed this with some people and presented it on my blog and elsewhere, and haven't really got a lot of in the way of feedback there. So it is a bit, frustrating if you're sort of trying to develop these ideas in good faith and you don't get a lot of people, or really anyone, giving specific, thoughtful response there, because then you can't tell if the ideas are any good, right? I mean, other than your own views, which are obviously biased. So, I think it is, it's one of the reasons that I did want to do this, because it feels like that it's not really something that the sort of atheist YouTubers have spent time on. So, yeah, I hope people find this valuable. I think I'm too tired to go over and summarize everything we've talked about. So I'm just going to leave that. Nathan, anything else you wanted to add?
No, I mean, I think basically this is a popular argument, or it's becoming more and more popular because it's sort of a place that some of the natural theology stuff can hide and seem relevant because it's not mapped out by most people or it's complicated. And I think that we've shown as we go through the way in which basically on each, almost every claim that IP's making, he's either like misrepresenting the science in various places with the papers that he's putting forward, or he's sort of like begging the question of his own interpretation, which is okay, but then he doesn't really like present the other interpretations as live options or describe why his interpretation should be preferred to the other ones. And then we've seen how there's like potential inconsistencies as well between some of the arguments that he wants to put forward, or some of the ways that he wants to argue against different criticisms and objections that someone might raise, and how his kind of explanations become more and more ad hoc as he kind of responds to those objections, to the point that they sort of disintegrate into a mere kind of description of the phenomena rather than like any kind of explanation that reveals anything underlying about the nature of reality. Now, I think IP is really smart and he does a lot of hard work, but really, I'm not impressed by these arguments, especially after going through them with someone like James, who's done all that background research and understands the physics to explain and describe, what's going on at each stage there over the 8 hours as we have done. It's like, as you actually look into these papers, they're just not saying what IP wants them to. Like, he's like, oh, and here's a graph of this result. And it's like, well, the result's not statistically significant. And then it's like, well, okay, well, let's throw that one out. And then, or like the other one where he was like, well, we can debate the points, but the comparison between what we'd expect of virtual reality, and then we find out that that's just like the thought experiment of some like data scientist guy, and who's like not a physicist, and it's again like suffers from all these same problems of just being like this post-diction, but not even like a good post-diction that's like more parsimonious. Like it's literally like got all this random stuff in that doesn't like fit with the way physics works, doesn't fit with the way computers work, like doesn't make any sense. And so there's all these issues for the way that IP is like using his intelligence to form beliefs, the way that he's presenting the types of things that he's talking about in a biased manner, and kind of like selectively kind of quote mining things and presenting them. And I hope that we've showed a bit of that. And I'm sure people who are convinced by IP's arguments are probably not going to sort of deconvert maybe based off of watching this episode, but I hope we've at least left a stone in your shoe, so as next time you see IP debating some of these topics and you see him kind of confidently putting forward loads and loads of references and papers and things, that rather than just being like, yeah, brilliant, you sort of like, hang on, stop a second, let's think about this, what's this guy saying, who's this author, are these actually the conclusions that are in the paper, is IP just saying that? And I hope that this prompts a bit more of that from people who are in the opposing kind of camp to the types of things that me and James believe.
Yeah, very well said. That's a good summary. And yeah, I think that, I appreciate what Eichel's doing here in trying to develop novel arguments and, putting effort and research into his videos and not just parroting things like a lot of people do, or just following the same script every time, which can be a bit lazy and repetitive. So I do applaud that, but the misrepresentation, deliberate or otherwise, of the science, and I think sloppy interpretations and inferences made on the basis of that, and presentation of fringe theories as if they're mainstream, and new ideas as if they're established conclusions, I think is all just results in a argument that's not persuasive and is hard to follow what the logic it is. I still don't fully understand how all the aspects of it fit together, or exactly what IP's model of reality looks like and how those pieces relate to each other. So hopefully I look forward to the discussion with him in a couple of months, where maybe we can nut out some of that, and encourage those watching here, or people who might be fans of IP who come by to just sort of be curious and to use this as an opportunity to learn, which it certainly has been for me. And there's a lot that I need to still understand better and learn more about. And yeah, this includes, the physics of it, but also philosophy and the history of ideas, intellectual history, as Cam sort of mentioned way back, which feels like a week ago when he was on, about the the trajectory of these ideas and how they develop over time. All this stuff is important and is interesting and helps us to understand the world better. So I'm a big fan of that. And just a warning, I think, against using these ideas sort of first and foremost as tools to try to establish a predetermined conclusion, or weapons to hit people with, or Pokemon cards to play, or whatever your preferred analogy is, rather than as ways to help us to understand and illuminate the universe, which is what I think it should be first and foremost. Rather than using them as weaponizing science, and I really dislike that. So hopefully we've contributed to the discourse here and provided something for people to think about. I apologize for any mistakes that I made, because I'm doing my best here. I'm not a PhD physicist, so there's probably minor errors here and there, hopefully no major ones. And as I said, I'm going to keep reading up on this stuff, and hopefully we'll be able to provide a bit more insight into some of these matters when I chat with Michael in a couple of months. So I think that's all from me. Thanks everyone for coming, and thanks Nathan for keeping me company for 8.5 hours.
Thank you everyone for watching. If you've enjoyed the show, be sure to like it to just help promote it with the algorithm. Leave a comment as well, letting us know what kinds of things you want to see in Bad Apologetics and what your thoughts are. And also go over to James's channel and subscribe, James Fodor, as well, and help support him and the stuff he's doing, because he's put a lot of hard work into, especially like this and the NDEs episode, put like hours into reading all those papers and things. So
yeah, we need an easy one next time.
Yeah,
the last two were really rough. No, but it's good. I'm learning a lot, but yeah, it's it is. It takes time, and sometimes I'm messaging Nathan like, why are you making me do this? I'm like, stay up, and like, I can't. It's like, it's good and bad sort of thing.
8 2/3 hours. Thank you everyone for watching. I'll end the stream there. Bye.
Cheers.